Okay, with that, welcome. I'm really excited to be doing this. I'm really excited that everyone could come here. We have people from all over visiting us. It's really great. I'm Joe Crumpfer. I'm editor-in-chief for the Journal of Polymer Science and deputy editor for Advanced Functional Materials. I'll be one of your moderators today.
Okay, I'm also welcoming every one of you today. I'm really happy to be here. I'm also one of the moderators. I'm Ulrike Kauscher-Pinto. I'm a deputy editor for Advanced Functional Materials, Advanced Healthcare Materials, and for our Health and Bio cluster. All right, and with this, I'm introducing Kirsten Severing, our editor-in-chief of Advanced Science and head of our department. Also Sandra Kelveram, who is editor-in-chief of Advanced Materials Engineering, and Jolke Perlar, who is the editor-in-chief of Advanced Materials Interfaces.
Thank you very much. I welcome everybody to this first Advanced Summit 2024. Dear guests, dear colleagues from all over the world, dear invited speakers, it's my great pleasure to welcome you all, and I'm very glad you made this long way to come here today. We are excited to celebrate the 25th anniversary of Advanced Engineering Materials from Sandra Kelveram, Advanced Materials Interfaces run by Jolke Perler, and of course the 10th anniversary of Advanced Science that you all know. I also welcome everybody who couldn't make it today into our office. So we had 1,500 online registrations. We are very excited to have people from all over the world viewing this great event, and we are looking forward to presentations from our board members and close friends of the Advanced portfolio. And with that, I don't want to hold you any longer, and I'm excited to get started. Welcome everybody and enjoy the day.
Right, and with this, we are up for our first speaker, who is Professor Martin Kaltenbrunner. He's giving a talk on materials and methods for sustainable soft devices. So Professor Martin Kaltenbrunner is a full professor at the Johannes Kepler University in Linz. He's heading the Soft Matter Physics Division and the LIT Soft Materials Lab. He received a master's and PhD degrees in physics from the Johannes Kepler University, and he joined the Somaya Sekitani Lab for Organic Electronics in University Tokyo for a postdoctoral researcher. He, in 2019, was then appointed a full professor. So his research group specializes in soft electronics and soft transducers, in particular on sustainable elastic materials and processes for the skin-inspired electronics and embodied robotics. And with this, I give the floor to you. Thank you very much.
Ulrike, for the very kind introduction. Let me first thank all of you for being here today, and of course the editors and the great teams of the three journals that you see done here that do the 10-year and 25-year anniversary. For me, it was mostly Kirsten that invited me and Jolk. So thank you very much again for having the opportunity to speak to you here today on the first Advanced Summit. And I hope this is going to be the first out of many to come in the next years, because it's a wonderful experience to be here. I see that you can barely see my slides. I hope that's going to get better because it's very bright here, but I'll do my best to explain nevertheless what we are doing in the lab. So as you can see from nature and from all around us, most machines that are built by nature are made from soft materials, of course, intertwined with hard ones like bones and teeth and things like this. And this kind of interfacing of soft and hard materials, this inspiration by nature, this is driving some of the research that we are doing in the lab. Not only us, but many researchers in the world, because of course we are fascinated by the 3 billion years of evolution and its achievements, and we would like to do maybe similar leaps in technology that we develop. Of course, we're not there yet, but it's a very interesting materials journey to get there. So this is our main mission. My lab is situated in the industrial city of Linz, that is right between Vienna and Salzburg, in the lovely country of Austria, in the center of Europe, so to say. You see the building where my labs are in. The university is named after famous astronomer Johannes Kepler, who of course did not study in my university because The university is about 50 years old, and Kepler lived in Linz a couple hundred years ago. But he did live there, so if you come to visit, I can show you where he lived, and I can also show you the labs. We have this beautiful terrace on top of our building where you can see even until the Alps on a nice and sunny day. What we do is spanning a rather wide range of technologies from soft robotics, and here we focus a lot on bio-derived and biodegradable materials because we want to mitigate the electronic and robotic waste problem. The same is true now for soft electronic skins. My background, however, is in, well, it's both in the soft transducers but also in thin and flexible electronics when I was joining Takao Someya's lab back in the day, where we did imperceptible electronics. Those are basically 1 to 3 micron thick electronic foils with full functionality that are thus very flexible and lightweight. Coming back to Linz, we still focus on this term of technology, on this type of technology, but mostly with an eye on power generating technologies such as solar cells, and I'll have a word on this in a moment, even though it doesn't fit to the main topic. Of course, I should thank my fabulous team who do all the work. I'm just standing here and enjoying their results and being given the opportunity to talk about them. But really the hard work is done in the lab by the postdocs, by the master students, PhD students, and even bachelor students. So great appreciation to my team. Again, a couple words on the solar technologies that we are doing. Although starting originally with organic photovoltaics, we a couple years back jumped on the bandwagon of perovskites because it became super fancy. Not only because it became super fancy, but also because it allows you to make thin film solar cells on the order of a couple hundred nanometers for the active layer from a very easy to process and solution process material that is at the same time very efficient. It's not necessarily very stable, but we can also tackle this problem. And in the last couple of years, we've made quite some advances in the field. So we use these devices to power ultralight aerial vehicles because these solar cells happen to have a very high specific power per weight. They can be used for medical purposes like X-ray detection, very nice work in advanced science that we are working on a follow-up soon. So I didn't say that, but yes, of course. Of course, those devices are predestined to power wearable healthcare monitors. And of course, we're also looking more into the fundamentals, and advanced materials is a wonderful outlet to study the details of crystal growth. So very fascinating work, I must say. We even had the opportunity to work together with the team of Harry Atwater and Michael Kelsenberger at Caltech in their space solar power project, which means some of our solar cells were in orbit within the ALBA mission, and we are now evaluating the data. Some of them even survived, which is a first for a couple micron thin solar cells being brought to low Earth orbit with a Falcon 9 rocket more than a year back now. And this is the team behind from my group that did all the work. So this is super exciting because in the near future we think that this type of ultra-flexible, foldable, deployable solar cell technology may have applications in space, like the solar robot Ingenuity on Mars. It's solar-powered as well, but with different types of solar cells. But just imagine you can unroll a whole field, soccer field of solar cells in space that before have been compressed to a small cube in their volume. Until we are there, we are focusing on terrestrial applications using those solar cells to power aviation models. A couple of years back, we did the first more or less air-stable, ultra-thin solar cells that powered a little plane, but they weren't very good yet. Almost 10 years later, we achieved much better efficiency on the solar cells, much better performance in the solar cells. We have now some that have up to 40 watts per gram in specific weight. If you think of a Boeing jet engine, 777, that has 10 watts per gram in specific weight. So this is really good. And we could use a drone and recharge it with sunlight and make it fly again. So ideally, it would of course be powered entirely by sunlight during flight, but guess what? Drones consume a lot of power. So there is not enough area actually on the drone to sustain it with sunlight, even if you were to have an impossible 100% efficient solar cell. So deploying, however, those drones, charging them again makes them unfettered in a way because they don't need to return to their base station to charge. And like this, you can, for example, do environmental monitoring for forest fires and things like that. Very efficiency. Bekele and Stepan were leading this project. The same guys, together with the fabulous Wei Gao and Chi Hong Min from Caltech, developed solar cells that can power wearable labs on the skin, literally. So Weigao is developing sweat sensors that analyze all the contents of your sweat for sports and medical applications. We contributed solar cells to them that are very efficient under indoor illumination. So it happens to be that perovskite solar cells also break all records when it comes to getting power from low light environments. And this is very important if you're going to work with wearables, because you don't always want to be under one sun illumination. Again, I don't really have the time to go into the details. I really need to hurry things up. But if you want to talk about this more, I'm happy to share some more of the results. This brings me to why we actually want to do soft technology, and I fully admit that this slide was actually put together by one of my fabulous former PhD students, Florian Hartmann, who is in the audience today here and now group leader at the Max Planck in Stuttgart, not far from here. It basically summarizes what the field in soft robotics is doing. So we have this amazing inspiration from nature, like the elephant trunk or the octopus arm. And on the other hand, we have, of course, these amazing examples of engineering, like a robot that is used in automotive industry, etc., to assemble products. So both of their merits, of course. The right ones are perfect in what they're doing. However, you wouldn't want to interact with them very much as a human being. The left ones are too complicated to imitate quite yet with our technology. So soft robots kind of tries to span the gap in between, mostly for assistive devices and things like this. So think about interacting with robots in the future. On the one hand, you of course need the advances in AI for their mental capabilities. On the other hand, you need the advances in technology to embody these functionalities. And this is, I think, where soft robots have a market niche. So a couple of years back, Florian and me, we were thinking about what you need for a soft robot, and if you look at these examples from nature, you literally need everything. You need the power storage within the actual device that has to be soft and flexible and stretchable. You need interconnect, sensors, everything has to be soft and stretchable, and you need to be the actuators that actually do the work. And the octopus arm is a perfect example. If you chop one off, it actually has everything contained and it can act autonomously. So thinking about the soft robotic devices of the future, maybe this is the way to go. We're of course not the only ones to think like this. However, it's a lot of work. Doing so, people usually, I want to share some of the work that I cannot talk about today, but again, having soft actuation with something like rubber membranes can be used not only for soft robots, but even for sustainable versions of cooling. And the left paper published in Advanced Science is basically the breakthrough that led to the other ones that came a little bit later, where we figured out that you can actuate very rapidly a soft membrane if you bring it close to its basically snap-through instability. This is a phenomenon that you would have in spherical rubbers, no matter which ones you use. However, if you have a non-viscous one, then you can really within milliseconds switch from one to the other state. If you think about the entropic nature of the rubber, I could convince you that this is a perfect material to actually replace vacuum compression refrigeration systems. It works the same way as an ideal gas, especially if it also has strain-induced crystallization, which is a latent heat and a phase transition. And this leads you to very, very efficient and very high-performance cooling systems that we published a bit later on. Again, no time to talk about it. Also, no time to really talk about the activities on the soft robots that use magnetic fields or electromagnetic forces, such as the Lorentz forces. I'll just show a little video here, because my former postdoc Guiyong Mao, that is now at Zhejiang, I'm probably butchering this, Zhejiang University in Hangzhou. I visited him regularly. So he came up with the idea of using Lorentz force and U-shaped resonant activated walkers. So in the presence of a magnetic field with some electricity on top of it, you can make very, very, very fast, tiny little robots that run at around 70 body lengths per second. So this is much faster even than a Formula One car. So this is the fastest robots ever built. Of course, they're still feathered, and the unfeathered versions also exist. However, they're not that fast in terms of body length per second. So still a lot to go. Yes, I know, it's a very funny video. That's why I keep showing it. Even though I'm not going to go into the details, yeah, they can run on about like every surface you can imagine due to the anisotropic friction introduced by the feeds that break the symmetry of the device, because otherwise it would just stop and be on the same spot. That brings me to the main part of my talk. So the problem is, of course, if we create all these new technologies, we are also creating a lot of waste. And especially if you think about the revolution of polymers, they're amazing. I really love polymers, and we wouldn't be where we are if we wouldn't have them. But at the same time, almost 9 out of 10 plastic bottles ever built end up in our environment and keep cluttering, everything with plastic waste. So if we want to avoid this, with future developments in robotics and electronics, we might want to start thinking about the problem early on. And already back a couple of years, we produced about 140,000 tons of electronic waste. Not waste, but electronic waste per day. And Florian looked it up again. That's the equivalent mass of 14 Eiffel Towers, just to have a picture in mind that suits a European heart. Eiffel Towers is something we can imagine, not far from here, actually. So probably not the worst, the best idea to do so. So again, Florian and Melanie sat together and triggered by Jolk's great invitation, Poissy Lee and me were allowed to put together a special issue for advanced materials a couple of years back on materials for robotics, soft robotics. And here we tackled the challenge of the sustainability, because we need to have devices that can be useful, but at the same time degradable after they are not used anymore. And this is a really difficult thing to do. In the next couple of minutes, I want to rush through all of these contributions that we made in the last couple of years, from biogels that are soft and stretchable, durable, but yet fully degradable. They can be 3D printed, stretchable versions of energy sources like batteries, mushroom-based electronics, and soft actuators that can be both biodegradable, like the middle one, lower middle one, and also work very efficiently once you understand the physics behind them. I'm not going to make it through all of this, so let's see. Again, Melanie and Florian set out to use something very, very well known, very common to us, gelatin as a biopolymer. So people were thinking, why gelatin? It's around for at least 2,000 years. Yes, it was, but not in that form. Not in the form that is useful to be applied for soft robotics and stretchable electronics. So it had to be tuned in a way that the mechanical properties compare to those of conventional silicone materials. And they actually achieved this with natural ingredients such as glucose and glycerol for dehydration and things like this. So I can skip this, but the idea is, of course, you want to have a polymer that can, for example, be triggered by water, in this case, to be dissolved. It's just food colored here, so you can better see it. But then you end up with the polymer chains. So you also need to get rid of those ones, and gelatin, of course, as a natural material. There are enzymes that eat them, and this is what we tested on the right-hand side with wastewater bacteria. So indeed, these polymers are completely fed back to the natural cycle. They're not only dissolved, but they're also broken down to their individual blocks and used as nutrients for life. And this is the cycle that we imagine. So at the same time, of course, by using something like glycerol, we could change the properties of the material such that instead of drying out over relatively short periods of time, they could be made stable for the course of an entire year or more and didn't change the mechanical properties. So this is an important finding, I think, and with this we could go ahead and develop on-skin patches. You cannot even see that the patch is worn on the skin, but it is. Now these patches have not the functionality that we developed later together with Wegao, but they can measure strain and temperature and things like this. Maybe the video works. Yeah, there you can see the material is a thermoplast. It is self-adherent to the surface of the skin, so you need no other material in between. And actually last week we just started a new EU project, Persimmon, where we will develop these patches further into some actually medically relevant devices and hopefully commercially applicable ones. For sports medicine, I'm very excited about this. So this is just a demonstration that the sensors actually worked. It doesn't really measure anything from the skin in this embodiment quite yet. But again, this is the next step, and this is the one that we're going to be working on over the next 3 to 4 years. Importantly, you can peel it off of the skin afterwards. You see, it really sticks well, but not too well. The skin will not come off. That's important as well. Without needing any other types of adhesives. And this is quite important, I think, for on-skin wearable electronics. It doesn't irritate the skin. On the other hand, we made simple pneumatic actuators. Those are literally inflatable balloons with a mechanical restraint. And instead of being able to actuate those devices for about 10 cycles, we achieved 300,000 cycles. So that was the big advance. So this material, though being biodegradable, can be useful. Of course, one would have to, they can also glow in the dark. I don't think you need an elephant trunk that glows in the dark, but it's a cool demo. So the idea is you can load anything that's water soluble in the hydrogel. It can be dyes, but it can be also medical products that help you cure damages on the skin. Anyways, that's not enough. Andreas and David from my group set out then to 3D print these materials, and I can only show the old work because the new work is still under review in a journal that I will not mention, but I think it fits to the topic here of the conference. In any case, the idea was to not only 3D print, but to also be reusing this material, and if you're not happy with your print anymore, or if it has fulfilled its requirements, it goes back to nature. Yes, there is a pig there. Yes, we're using animal products here. If you guys stop to eat animals altogether worldwide, we might run into a problem and need to find something else. But up to this point, gelatin is basically a byproduct that we can use for cheap. And that's also good because then everybody can use it, right? So if you have a specialized chemical that costs you $1,000 per gram, you will not make a large-scale robot out of it unless you're a millionaire in the lab, which we are not. So the material is available for everybody. What was missing was basically the hardware to actually extrude them. And our first printer was a very simple one. Andreas built it. It is kind of a fused deposition molding type of device. It heats the gelatin until it liquefies, then it extrudes it and cools it again. Now we have actually capabilities of multi-material printing in the lab. The idea is that the printed samples are actually better than the mold casted ones because we don't have damages at the interfaces and at the edges of the device. You can also use them as waveguides. That's a sensor because they're lossy waveguides. If you stretch them or bend them, then you will lose some of the light that goes through, so you can read back on the deformation state. And with this, we made a multi-chamber actuator that has waveguides on its surface, so you should be able to see some of the graphs here. On the lower one, it's probably a bit better. If you touch it or if it bends, you can read back the state of deformation. Now again, this device, the actuator itself, is actually, first of all, able to recognize its surrounding. This is seen in the top video. And on the bottom part, you see that it can dissolve in water, and then you can start to pick out all the other components that are not necessarily water-soluble, though the cotton yarn that you see is at least degradable. Of course, we need to work more on the electronics part of it. Now it's more like reusable and not degradable, but there is, of course, a huge movement in terms of transient electronics, where you can do a lot quite already, but not Bluetooth chips or things like this quite yet. So again, power is a problem. You need to power these devices. We want untethered, not tethered ones. And Mahia and Doris from a group I tasked them to develop basically the first stretchable and biodegradable battery that had also reasonable power. And they did so by combining mechanical designs like origami patterns inspired by Japanese art to make otherwise just flexible electrodes like this molybdenum and magnesium foils that you see here, stretchable as in the video, by cutting them correctly. They're at the same time the active materials and the electrodes for the batteries. You have PGS as an encasing substrate and alginate as a separator, so it's an entirely biodegradable, not bioderived, biodegradable battery. Could be even implanted. We didn't test this, but others did. And it is stretchable. It doesn't produce the same power outputs that lithium polymer batteries would do, so there is a lot of room for improvement still. But again, it's one of the first steps towards this type of devices. Actually, back in 2010, still with Siegfried Bauer, my mentor and advisor, who unfortunately passed away too early because of cancer, we developed the first stretchable batteries ever in advanced materials. So the advanced family actually was very forward-looking here, accepting this works. Now it's a big research field. We can use these batteries to power wearables for now. They're not as fancy as Gauss ones, it's just a sodium sensor in this case. But there is still a way to go to develop these batteries towards the requirements of soft robotics, because whenever you have to move something, you need a lot more energy. Okay, I have still 10 minutes, that's good enough, I guess, to switch gears a little bit. Beautiful mushrooms, right? They grow on trees, Ganoderma lucidum, glänzende Lackporling, for those who understand German. It's a mushroom that's used, I've heard, in Chinese medicine, but I will not go into details here. For us, it is a mushroom that we can harness to grow substrates for electronics. And if you were to see this better here, this is actually a mushroom-derived flexible foil that has electronic circuits sitting on top. It works pretty much like paper substrates, but it's on this screen, it's beautiful. Yeah, well, you're out of luck here. Maybe the persons online can see it better. So the idea is really to have a material for flexible electronics that's not polymeric in nature, not made from fossil-sourced polymers, and also not made from paper, because it happens to be that as good as you think paper is, the production of paper requires a lot of water and a lot of energy, so it may not be as sustainable as you think. If, on the other hand, you can use waste materials from the forestry industry, like wooden chips, you can grow mushrooms on it, and you can not only, for some mushrooms, eat the fruiting bodies, but for others, you can use the skin that forms on the growth medium, and you peel it off, and then you press it and dry it, and that's it. Then you have a sheet of paper, literally. But it's not made from cellulose, but it's made from mycelium that is kind of interwoven and flat. And the advantage of this material is that it is very temperature stable. So we can heat it to more than 250 degrees centigrade, which allows us to deposit metals on top of the material, which allows us to do laser ablation and other things. We can even solder on it. And we can make a patch that even contains a mushroom-based battery here. I'll talk about this a little bit. Doris and Roland were the ones driving these advances in the lab. Again, we use the as-grown material. Depending on how long it grows, we can have a separator grid that allows you to peel off the skin from the mushroom body itself. And then we process electronics on top for all kinds of purposes. In principle, even you can make batteries where the active materials are zinc and manganese-based, but the encasing and the separator are fully based on mycelium. That's not even a bad battery. So altogether, we can use these materials as an alternative source for degradable and to put reusable components on top that you can peel off of the substrate, then you put it to the household compost only, and the mushroom materials will automatically degrade. Those are first examples that have simple sensors on it. Of course, these devices, these mushroom skins, are not super flat quite yet, and they're not quite compatible with thin film electronics, but this is the next step that we are working on. So this is going to be a lot more interesting to have even better mushroom-derived substrates for all kinds of thin film electronic devices. Okay, this brings me to the last part of my talk, maybe 3, 4, 5 minutes left. Besides the soft robotics part that is driven by pneumatic actuation and the flexible electronics part, we have also long-standing history in the lab working on dielectric elastomer or dielectric materials-based actuators. Basically, that's a topic that, again, Siegfried brought to the group 15 years ago, where it was still called dielectric elastomer actuators or, other types of actuators. Then soft robotics came around, people rebranded those ideas. But I would like to convince you that using electrostatic actuators is still a very good idea because they can produce very high power per weight. You need only mostly polymeric materials and very little metals, if at all. So you can make basically machines that are at the same time very powerful and very lightweight. So this is exactly what you would like to have for mobile appliances. If you think about the Spot Mini or the Atlas robots, from Boston Dynamics, they're extremely heavy. So the Atlas is smaller than me, but it is at least 250 kilograms. Because everything basically is based on metals. Imagine everything being based on polymers, especially the actuators. There you drop a couple orders of magnitude in the density and in the weight. But they suffer from issues. So you can imagine all kinds of these types of actuators, be it the famous Piano Hazel by Christoph's group at the Max Planck in Stuttgart, or electrostatic bellow muscles by Marco Fontana's group, Hexel devices by Herb Schia's group, or SEEP lenses by Florian Hartmann, who is sitting here. So all these devices rely on the same concept, but I will first show you a video that Ellen Ramley from Christoph's group did for a common paper of ours, where we actually made biodegradable embodiments of these actuators, but they also tell you how they're made. So they're rather simple. They're pouches of polymers that have electrodes on one side and dielectric liquid in the middle. If you apply a voltage, you make them zip, displace the dielectric liquid in the middle, and have a contractile motion. So the way that you make them is you use, in this case, a biodegradable polymer foil. You use gelatin as an electrode that you blade cast, and then you use FR3, or in other words, vegetable oil, to fill those pouches, as seen here. And then you have one element of your artificial muscle. This can be done with regular polymers, or this can be done with polylactic acid-based ones, or other biopolyester-based ones used for carrot packaging, as you have seen. And they're entirely good in performance, better even than the BOPP ones in some cases. However, they're entirely biodegradable. if you use industrial composting facilities. So if you throw them in your normal household compost, they're not going to degrade, but if you use industrial composting facilities, you can actually degrade these devices. So all of them are based on the concept of a deformable capacitor. However, a capacitor that has more than one dielectric. It has a solid dielectric and it has a liquid dielectric. And it is exactly the interface between those dielectrics that causes problems. Because usually if these properties, let's call them properties of the dielectrics, are not matched, what happens is you get a charge density accumulated at the interface that literally kills the electric field in the liquid part of the actuator, which means it kills the force of actuation. So you apply a voltage, your actuator will actuate, and then it will relax again. Something you don't want to have. So Dan showed this with an electrostatic bellow muscle. It's actually showing a stroke here, as you can see. And within mere 10 seconds, the stroke goes back to zero. So it's really something you don't want to have. You apply a voltage to this device, it actuates, but then it just relaxes again. Not very good. Why is this the case? Well, again, it's the interface of the dielectrics that you need to look at, and we studied those in great detail with a homemade setup, and we found interesting behavior. So for some very often used conventional polymers, you see this decay in the actuation force over reasonably short periods of time, but for others, you don't observe this decay, and that's of course interesting. So you look into this in more detail. Yondan and David did that together with Nikita Arnold in my group, who is a theoretician. And they figured literally that it's the time constant of the dielectric, so the ratio of the film conductivity to the permittivity. People usually forgot about the conductivity in those films because they're insulators. So you don't usually care about their tiny conductivity. But it's actually the crucial part, because the force after a certain amount of time of applying the voltage is actually determined by the ratios of the conductivities and not the permittivities of the material. So they actually are the key, and if you have the right combination of materials, you will have the case where no charges accumulate at the interface. If for this case, for the right case, the positive charges accumulate, you kill the electric field. You can switch the thing around. If you have negative charges accumulate, you can actually increase the force at infinite time because you have more field, and if you make it right, you have no change in the actuation force over time. And this is exactly what we did. This is matching of dielectrics. It works interestingly for a bio-derived polyester material because it's a tiny bit more leaky than your regular polymers. And with this, you can actually consider this matching condition as being the most important in this design of these types of actuators, where after some mechanical wiggling, these devices are perfectly able to hold their force indefinitely. So you apply the voltage, it actuates, and it stays actuated, exactly what you would like to have. With this, the last word will be on the power consumption, because people would now say that, okay, you have an actuator, you apply a voltage, current is running through, that's bad for you. Well, in fact, the current is very tiny. The only other way to keep those actuators actuated at a constant force is to switch the polarity of the device. And this dissipates just a lot more energy than this tiny little current that runs through the layers. So what we show is that depending on the materials you use, of course you cannot see this here, but the dissipated discharge for an AC-driven device is orders of magnitude more power consuming than our a little bit more leaky devices, and if you use a fancy PVDF tear polymer, you can at the same time even reduce the power consumption. With this, it is 9:34, and I'm happy to thank you for your attention.
Thank you very much for this really cool talk. I'm sure there will be questions, and there's going to be a microphone coming from the back. There's a question there in the back.
Thank you very much for this very inspiring talk. It was amazing. And I have one question, or more precisely, I would like to hear your comment about the myceliums, because
Absolutely.
we know that they are more like human beings, or like animals compared to the plants. So meaning that regarding respiration, they produce CO2 when you deliver the mycelium. So, and therefore, I think they are not so CO2 neutral. And considering that you use them as a sustainable derivatives, and how you can prevent that they generate so much CO2 or minimize the amount of CO2 when you deliver the myceliums and utilize them for such a processes?
That's an excellent question. Yes, you're absolutely right. Mushrooms are their own kingdom. They're not animals and not plants. They actually set free some CO2 when they decompose organic matter. Well, I would argue that the amount of CO2 that they set loose is much less than from the animal industry. And if you cut down a forest to produce paper, you're basically also releasing this saved CO2 again. My biggest argument here is that we are using waste products from already existing waste flow streams. So imagine that you use the wooden chops to burn them to get energy, you release the CO2. So set a step back and grow the mushrooms first. Then you have a product, and you can actually use the composite material that is innovated with mycelium fibers as a thermal insulator for construction energy. So instead of getting rid of basically all the CO2 that is in the waste product, you store some of it as a value in a building, for example, and as a value in your flexible electronics. So yes, some CO2 is produced, but I would argue that if one looks at the whole cycle, that it's going to be probably a lot less than with conventional materials. But you're absolutely right, this is a concern.
Right, another question there in the back.
So I wonder for the first few tape actuators, how precise can you control the motion with? Have you considered like the force dynamics in other systems instead of the capacitive ones? And it's worth like maybe integrating kind of sensor in those actuators, then
Absolutely.
you can provide immediate information to tune the stimulators.
Absolutely. You're talking about the pneumatic actuators right now, yes? So the very first kinds that you have seen, they do not have any sensors embedded, so there is no feedback. That's not good. The second type, the 3D printed ones, have the feedback through the optical strain sensors. So we made them with optical sensors. Yes, they have a feedback loop. We show that they can keep a trajectory, pre-programmed trajectory, based on the feedback that you get from the actual sensors. Now, this is not the only approach. Of course, you can put other types of strain sensors in there, and this is what people are doing. So obviously, you would like to have the actuator together with the sensor and the feedback loop. So the sensor and the actuator, I think you can make rather straightforwardly sustainable. The electronics part probably is not going to be that easy. So you want to keep your electronics and just exchange the actuator. This is actually our first use case because many of these actuators are used in industrial processes for pick-and-place applications. They will be worn down and have to be replaced. But the actual control unit you will not replace. So you just keep it and exchange the actuator. But you're absolutely right. You don't only need the actuator, you also need the sensor. The capacitive ones have some self-sensing because they're deformable capacitors to some degree, but the other ones need additional sensors. For example, waveguides or other types of strain sensors.
Right, thank you very much. Again, thanks for this talk. Thanks for being here today.
It's a pleasure. Thank you, guys.
All right, and with this, I would like to welcome our next speaker. This is Professor Pavel Levkin. He's going to give a talk on functional surfaces and micropatterns from superhydrophobicity to drug discovery. And Professor Pavel Levkin is a professor and head of Department of the Functional Materials at Karlsruhe Institute of Technology, KIT, at the Institute of Biological and Chemical Systems. He's a co-founder of two spin-offs. The one is ScreenFact, the other one Aquarate. His group has published about 165 papers and submitted 20 patents. He actually received the ERC starting grant and 2 ERC proof of concepts for the EU and the Heisenberg professorship from the DFG. He also received a Heinz Meyer-Leibniz Prize and the Ewald Wicke Prize. And well, he also serves for the editorial advisory for several Wiley journals. And with this, I would like to give the floor to you. Thank you very much for being here today.
Thank you. Thank you for the nice introduction and good morning, ladies and gentlemen. Thank you also for inviting me here. Second time, I guess. It's really nice to be here. I apologize from the beginning for my coughing because I haven't recovered completely from a cold. Today I will talk about functional surfaces and micropatterns from superhydrophobicity to drug discovery, but I want to focus on kind of the importance of functional surfaces, interfaces to accelerate drug discovery through miniaturization of biological and chemical experiments. And the best way to show the importance of miniaturization is by showing this plot, which is the famous Moore's law, which shows that number of transistors per microchip has been doubling every 2 years over the last 50 years. And this is basically miniaturization in combination with parallelization, throughput, and integration. This resulted in this drastic reduction of costs of microchips, which in turn led to the democratization of the technology of the microchips, personalized computers, which in turn resulted in the extremely positive impact on society, and from which all of us benefit in every day by using cell phones, computers, internet, cars, and so on. And the same should be true actually for life science, for biological experiments, for chemistry, for medicine, diagnostics, for drug discovery. And in fact, scientists have been working in this field to trying to miniaturize biology and chemical experiments. And on this graph, you can see the number of papers increased from few hundreds of papers citing or mentioning lab on a chip and microfluidics in 2000 to tens of thousands of papers in this field per year nowadays. And in fact, there are some success stories, and probably the most important success story is the drop of costs of genome sequencing, which dropped from hundreds of millions of US dollars in 2000 to less than $1,000 per sequencing this year. And I would argue this was only possible through these four things, through miniaturization, parallelization, high throughput, and integration of different parts of the process in the same technology, in the same system, which resulted in the reduction of costs first, then which led to the democratization of the technology, and we will see positive impact from this technology yet. And by seeing this, it's even more surprising than to see this plot, which is so-called Irum's law, which is opposite from Moore's law, which shows that the number of drugs that have been developed per 1 billion US dollars has been constantly decreasing over the last 70 years, which is, in other words, the costs for drug development have been constantly rising over the 70 years, despite of all of the miniaturization, lab on a chip, microfluidics technologies. And I would argue this is not actually despite miniaturization, this is because we actually failed to miniaturize biological experiments and chemical experiments. And here you can see the first attempt to miniaturize biology, which was done in 1950. This is a 96-well microtiter plate, which was introduced at that time, which was already a huge kind of success in terms of miniaturization. People went from Petri dishes and milliliters to 96 tiny Petri dishes and using just 200 microliters. But then the next kind of wave of miniaturization happened only 30 years later when the 384 well plate was introduced. And if you ask biologists nowadays, most of the biologists still use 384 well plates or even 96 well plates. So this doesn't really follow the famous Moore's law in life sciences. So there's basically zero miniaturization over the last 40 years. Of course, on average, there are good examples. But to please biologists, or probably also here, in chemistry, the situation is even worse. We still use the same hardware, glassware that people used 100 years ago. We still use milliliters, hundreds of milliliters for doing chemical reactions nowadays, and not even microliters, and I'm not talking about nanoliters. So I would claim that we can achieve the same kind of breakthroughs as in the case of semiconductor industry or in the sequencing, but we still have to further miniaturize biology to go beyond the limits of microtiter plates, to go to nanoliters, and at the same time we have to miniaturize chemistry to the same scale and the same throughput as biology because it's essential to integrate chemistry with biology. It will not work if chemists still use hundreds of milliliters, and then finally biologists are trying to do millions of reactions and experiments in nanoliters. And this is what sorry, we have been trying to solve in some of the projects in my group by developing so-called open droplet microarray technology, which is basically a glass slide with immobilized thousands of nanoliter sized droplets in precise locations where these droplets can be used for both biological as well as chemical experiments, but using 1,000 times smaller volumes. And this brings me, connects this important problem with the field of surface science, surface functionalization, patterning, because without this, it's not possible to solve this problem. So what is droplet microarrays and how do we make them? So in my lab, sorry, we have developed different methods to functionalize surfaces with, first of all, such superhydrophobic coatings, which are based on micro nanostructuring and surface functionalization, which are extremely water repellent. And on the other hand, the opposite of superhydrophobicity is extremely hydrophilic or superhydrophilic coatings, which is also based on micro nanostructuring and surface chemistry, but has completely opposite highly adhesive properties. And then we also have been working on methods to create these surfaces using photochemistry based on UV lights. Here are some examples of photochemical methods that we have introduced. And the advantage of photochemistry or UV light is that we can control spatially where we can get the superhydrophilic spots and superhydrophobic backgrounds, because we can use a photomask and we can pattern surface with these two important properties. And if we use these methods to make an array of hydrophilic spots on a superhydrophobic background, then this leads to completely new, interesting functionalities, like shown here, the effect of discontinuous divetting, where if you just roll a droplet of water, you feel these thousands of compartments in precise locations with nanoliter droplets that can be used for individual experiments. And then again, by using the controlling geometry of hydrophilic patterns, it's possible to control shape of these droplets, size of these droplets, location on the surface, density, and so on. Then the new technology that has been developing over the last years for liquid dispensing also allows us now to precisely deposit controlled liquids and volumes of cell suspensions or reagents into precise locations, and we can control the volumes down to sub nanoliters. So the technology is there for these applications. With different liquid dispensers, as shown on the left-hand side, it's possible to print cells or single cells into these compartments, or bacteria cells, or other types of microorganisms and reagents. So with this technology, what we have been doing over the last few years, we have been demonstrating and optimizing biological applications, high throughput applications using nanoliter-sized droplets, which is 1,000 times smaller already than what people usually use in biology. So we have shown, for example, drug screens using cancer cell lines, using primary cells, which is important for personalized medicine, where there are not enough cells, where miniaturization is also important. For stem cell screening, single cell screens, we recently screened several thousand compounds with bacteria to search for new antibiotics, and also showed the possibility of using this miniaturized high-throughput screenings of cells in three-dimensional microenvironments like hydrogels. But today I want to show you some examples of novel applications of droplet micros where which are not possible in microtiter place because of the kind of design and the features of droplet microarrays. And the first one is adhesion versus gravity. Microtiter plates and the common biological and chemical experiments, they are based on gravity. So this is how we confine liquids in the well, so just use gravity. But if you reduce volumes to sub-microliters, then adhesive forces become much stronger than gravity, so you cannot actually use gravity. That's why you cannot miniaturize microtiter plates, basically. In our case, we actually use adhesive forces to control and confine and manipulate liquids at this scale, but at the same time, they become also much more stable on these droplets, on these droplet microarrays. And you can basically do biological experiments, cell experiments in any orientation of these slides, which you wouldn't do with microtiter plates, probably. And this is interesting because if you culture cells in the inverted orientation, you form cell spheroids in these droplets using the hanging droplet method. So cells organize into three-dimensional architectures. In every single droplet, which you can see here, these dots, these are actually multicellular spheres. And this is important because cells in these 3D spheroids, they feel closer to the physiological conditions, and they respond to drugs also in a different, more physiological way. So then we used this method recently in a collaboration. Sorry, the colors are still missing. But we used it in a collaboration with Seven Turkan from Heidelberg, who is working on brain tumor, on glioma, which is aggressive brain tumor. And we used patient-derived and also drug-resistant glioma cells to form tumor spheroids on the droplet microarray and then screened them with 2,200 FDA-approved drugs for repurposing. And in total, it was 20,000 experiments with all the repetitions. It was only possible through miniaturization. But importantly, the screening resulted in 20 hits from these 2,000 compounds, and new compounds that were active against these drug-resistant glioma cells, and 3 hits were validated in vitro and in vivo, and also a new mechanism of action was shown, and hopefully this will lead at some time to new therapy against this bad disease. Another interesting difference of droplet micros from microtiter plates is that there are no walls around the droplets like in microtiter plates, like plastic walls that you cannot remove. And this means that you can merge neighboring droplets because there is no wall by liquid dispenser, and this brings, for example, cell spheroids together, which you can see on the left, into the same compartment. And then if we continue to culture these 2 spheroids in this compartment, they start to fuse, they start to interact with each other, and this leads to the formation of such a kind of giant cell spheroids, 3-dimensional architectures. And here you can see, so we can merge 2 droplets or 3 droplets or 4 droplets, and this leads to 3-dimensional multicellular constructs with very interesting architectures composed of multiple spheroids. And all of this is done in an automated and kind of high throughput way. What is also interesting here is that you can then culture different types of spheroids from different cells and then merge them, and they form also this type of complex 3D cell structures with interesting geometry, but also composed of different cell types. And what is also interesting here is that the fusion process doesn't lead to mixing of the cells. So we end up with such architectures where the boundaries between different cell types are still visible. And this is important to mimic natural like tissue architectures where you have different cell types, obviously, and interfaces between cell types. It's also important for making more physiological drug models for drug screenings. And here are some more images. So this is such a so-called cell assembloid from 2 spheroids with a clear boundary. from 3 spheroids. Again, you can see very nice boundaries, and even from 4 spheroids, that leads to this formation of 3D giant spheroid with clear boundaries between different cell types. Another interesting difference of droplet micros from microtiter plates is the following, and it's based on the fact that in microtiter plates you have liquids that are confined in cavities or in wells like here, so they're inside of the cavities. In the case of droplet microarrays, the droplets are actually above the surface, and this makes them accessible for parallel manipulations using just another flat surface in a single step, like shown here. And this is unique because if you have like thousands of droplets, their manipulations or compartments have become very, very difficult. But since they are above the surface, they are addressable from the surface in parallel. And this can be used, for example, for copying a library or taking samples in parallel from all of these thousands of compartments, or for adding reagents in parallel to all of these compartments. And we used it recently to demonstrate in simple but important application for medium exchange, because if you culture cells for more than 3 days, you have to exchange the mediums, otherwise cells die. And how would you do this if you have like 10,000 of droplets of 200 nanoliters or compartments, and it's even hard to see them? How to exchange the mediums? Because usually biologists use pipetting robots and pipettes, but here it's not possible. But with this sandwiching method, it was possible to like remove part of the medium and then print fresh medium, and this resulted in on the right-hand side, you see it's without medium exchange, so cells start to die, and you have the last bar. So these are dead cells, these are viable cells. And with this medium exchange, you see increased proliferation and improved viability after 7 days of culturing of cells in 300 nanoliters, and all of this was done in parallel. Another interesting application of the sandwiching method is to do parallel addition of spheroids or transfer from one slide to another. And so here's a scheme. So if you do the sandwiching between 2 arrays containing individual cell spheroids, during this sandwiching step, when the liquid bridges are formed, spheroids, they kind of precipitate to the bottom slide, and when you open it, they will become trapped in the bottom droplets in parallel. And here you can see on this video, so initially there is just one spheroid, and then the sandwiching process, the second spheroid is added to the individual droplets in parallel. And this is another, like it's an image of droplet micro with individual spheroids. So these dots, these are cell spheroids in every single droplet. And then after sandwiching, you see that each droplet contains now 2 cell spheroids. And what is kind of cool that you can repeat this process, and then you can add a 3rd spheroid to the same droplets. And of course, you can then change spheroids and cell types and so on. So this opens a lot of possibilities for applications. But it's still kind of exciting because this is a single-step process where you can address literally thousands of compartments that are so small that are difficult to see. And then at the end, you see such a accuracy that every droplet has like precisely 3 spheroids. So it's kind of exciting. So now I come to the last part of my talk, which will be about miniaturization of chemical synthesis in these droplets. And this is, again, essential because if we don't do this, it will not be possible to integrate chemistry with biology. And this is important to achieve this integration step and to kind of try to realize the same promise as with semiconductor industry, with miniaturization, and with sequencing, because integration of components into the same system is essential. But how to do synthesis in 100 nanoliters, that's also not trivial. First of all, because usually chemists, and I'm a chemist, we do chemistry usually in organic solvents. Only green chemists probably work with water. And organic solvents, they have low surface tension, and low surface tension is not good for superhydrophobicity, because superhydrophobic surfaces are also known as oleophilic. And to confine organic solvents with low surface tension, the surface, again, it comes to the importance of surface functionalization, surface chemistry, but knowing how to functionalize surfaces and change their physical properties, it was possible to to make a different type of patterns that enables to confine even hexane with very low surface tension in precise droplets, but also other organic solvents. And I want to show you one example of an early study where we wanted to demonstrate all the advantages and to go from kind of drug discovery, go from organic synthesis, library synthesis on chip to characterization on chip and to biological screening using exactly the same platform. Sorry. And for this we designed a chemical synthesis to synthesize this type of lipids, cationic lipids, using 3 component reactions using amine, thiolactone, and pyridyl disulfide that react together to form a cationic lipid, and we can then use different building blocks to make a library of lipids with different structures. And cationic lipids are important because they are the main component of vaccines, for example, mRNA-based vaccines, corona vaccines, or cancer vaccines that have been developed by pharma companies. And the right structure, performance, toxicity, activity of this cationic lipids is essential for the next generation vaccines. So the synthesis then was done on the droplet microwave by basically adding all 3 components for the chemical reaction into the individual droplets using also sandwiching method and the discontinuous dividing method in this case. It was done in DMSO, then reaction happened overnight in DMSO, and then we had at the end droplets, each droplet containing a different type of lipid. Then these lipids were also characterized basically on the same platform and using the advantage of droplet microwave that we can stamp it basically on a MALDI plate, which is used for MALDI mass spectrometry analysis, and we could analyze all of the lipids then in parallel on the same slide. In the next step, we took this library of lipids and then sandwiched it with another slide containing aqueous buffers with plasmid DNA to form lipoplexes or lipid nanoparticles. So lipid nanoparticles complex with nucleic acids. And at the end, we basically got a library of LNPs formed from different types of lipids in this on this array. And the last step was basically just printing cells to this LNPs on the surface and then incubating this droplet microwave for 1 or 2 days and then analyzing by fluorescence microscopy the number of transfected cells that express GFP and comparing to a control. And this screening already resulted in some lipids that were more efficient for cell transfection than commercial control. But what is essential here, I think what I'm always trying to emphasize, that in this early study we did on-chip synthesis of 75 lipids, on-chip characterization of all of these lipids by MALDI, on-chip lipoplex formation, on-chip screening with cells. And all of this was done within just few days at the end and just using 1 milliliter of solvent. And this is, I think it's a good example how miniaturization, parallelization, high throughput, and integration is important and can actually lead to drastic reduction of costs for example, early drug discovery, and eventually should lead to democratization of this technology and positive impact on society. And with that, I would like to thank all of my team members who contributed to this work. present and also alumni, our funding funders, and I also want to use this opportunity to congratulate you guys for these 3 wonderful journals, and thank you for your attention.
Well, thank you for this wonderful talk, and with this, the floor is open for questions. Over there.
Thank you for this fascinating talk. I was just wondering, when you talk about very small droplets, to which extent actually volatility of the solvents play a role?
Yeah, that's important. Of course, the evaporation of liquids, I'm sorry, becomes an issue. But when we go to really small volumes, then we have to control the environment and the temperature, humidity. But this is solvable. So, let's say, it's not the big issue. It cannot be done in the same way as microtiter plate. We just open it and kind of walk around. So it has to be done in a closed environment, and students have to work quickly. But for water, is down to 200 nanoliters is not a problem. Yeah, you have to be skilled, but going below 200 nanoliters, then it would have to be done in a controlled atmosphere, and then it still works. For organic synthesis, usually we have to work with, in this case, with low volatile solvents like DMSO, DMF, and NMPs, which work for most of the chemistries. Or we have to, again, do it in a controlled environment, yeah.
Thank you for the beautiful talk. I wanted to ask how you control which side the cells go to when you do the sandwiching and then you pull the plates apart. Can you control to do successive operations?
How can we control
which side the cells stay on after if you separate the plates?
In this case, so if you talk about the sandwiching of
this one.
spheroids, that's a good question. So this is actually very simple. Cell spheroids, they're relatively big, and once we have this sandwiching step, which you can probably see better here. Yeah, so there is a liquid bridge, so the 2 droplets, they're connected, and spheroids, they basically precipitate to the bottom slide. When you open it, they're all trapped at the bottom slide. So you can actually, if you invert it, you go to the other side. You can transfer it to the other slide as well, yeah.
So I wonder how the effectiveness of this technique for when it goes to in vivo. I mean, you screen some drugs, then you probably have to test it in vivo. And how, I mean, as a consideration on the real, conditioning, comparing with in vivo testing.
So if we talk about early drug discovery, where the first step is the screening, usually huge libraries of compounds with cells or proteins to find binders, and then you identify hits. Then they have to be further improved. They have to transfer to lead. Structure should be improved, and this is done in parallel with in vivo applications. But this is the next step, the preclinical tests, and then it's going to clinics. So the first step is always in vitro, and the chemical space is enormous, and even pharma companies that have millions of compounds, they're still covering just like tiny portion of compounds. Of course, there are other methods, DNA tagging and so on. But still, it's important to increase the chemical space that is accessible to all these biological models to find initial hits, and then they will be improved and they will go to in vivo. But we don't do in vivo in this step, so focus on the first step.
I think we have to continue with the schedule. I'm sorry. I actually also have a question. I will find you later to ask it. So thank you again for this really nice talk.
Thank you.
And with this, I would like to welcome Professor Nanfang Zhang, who had a bit of a farther way to come here. So thank you very much for being here. So Professor Nanfang Zhang received his bachelor's from the Xiamen University in 1998. In 2005, he obtained his PhD from the University of California, Riverside. And then he worked as a research associate with California Santa Barbara University. And then he moved back to Xiamen to be a full professor. His research focuses on the surface and interface chemistry of functional materials, targeting applications in energy, catalysis, and biology. And yeah, I'm really excited for it.
Thank you. Thank you for the kind introduction and also invitation to be here. Today I'm going to talk about how to precisely control the chemical reaction on metal surface. I think at least it need to be at the molecular level. And we realize that at the molecular level, maybe it's not enough to really achieve the precise controlment. So surface and interface is really important for chemists because we really need to work carefully. And I will give you some example how important of surface and interface. And here is one example. I think everyone here, we all learn from our textbook. Copper is more inert than nickel. But in our real world, we use nickel to protect copper. Why? Because on the surface of nickel, they can form dense passivation layers. That's the only reason. So that's why if we look at our elemental tables, as you can see, copper is a really great metal because its conductivity, electronic conductivity, and also thermal conductivity is next to silver. But once it gets oxidized, it loses all its excellent conductivities. But for the nickels, you see, it's really great as a catalyst. But if the nickel gets oxidized, it loses the chemical properties. So how about can we really switch their surface properties, which will be very amazing, right? If we can have a dense passivation on copper, then we can turn copper into silver, right? So that's what we did. And actually, this can be done really simply. For example, by introducing fomate as a surface modifier, which must be really surprise you, right? And this also surprised me, because in 2017, one of my PhD students, he already finished the defense and prepared to leave the group. He knocked my door. Because the copper nanomaterial he prepares, you see the thickness is only 1 nanometer. In most of the cases, after you take it from the solution, basically they will get oxidized immediately and will get dark. But after 3 years, when he tried to clean his sample, he realized that this sample is amazing. It's still shining. So I asked him to continue his postdoc in my group, but he denied it. So I actually have another postdoc working on this project, and basically he just used this copper powder and treated it with fomate solution under the temperature of 200 Celsius. And he realized that actually the fomate is not simply function as, because in our synthesis of these copper nanomaterials, it just functions as reducing agent. But it turns out it can also function as a surface passivation layers. So we spent more than 3 years, and by working with Professors Yin Jiang at the Peking University, who are working on Q+ A-frame, and we realized that actually fomate, they form dimer structures with copper-2 species on the surface. And these units, basically, they can form really dense passivation layers on copper, which is quite amazing. And the thickness of this passivation is only 0.5 nanometer, so it won't influence the electronic conductivity. So which is really surprised us, because we use it just as a reduction agent, right? So, but in our real sample, as you can see here, it's not really single crystals. There are so many steps. So for those steps, if we use the SIO to passivate further, and then basically we can increase the stability of these nanomaterials for a really long time. So this technology is really, totally unexpected. But after we know the reason, years have already passed. Now we spend another several years trying to develop copper paste technology. Because with this copper paste, then we can use screen printing, all the other techniques to have this copper to really replace silver. So fortunately, in past several years, we have tried to push the application of this copper paste into solar panel, for example, because more than 10% of our silver is currently used in solar panels. So the price has been significantly increased in past several years. But as a chemist, I think this kind of passivation sometimes not so great, particularly when we're doing catalysis, right? We want to increase activity, but for the anti-oxidation, we want to decrease. So how about the other direction? Catalysis, right? As we all know that heterogeneous catalyst has been widely used in our industries. But the problem for this type of catalyst is that they are not really well defined, like homogeneous and even biocatalysts. They have well-defined structures. So the mechanism is really clear. But for this heterogeneous catalyst, it's just like black box. So we should not complain our chemical industry produce pollutants, right? Because they are so ill-defined. So that's why here I would like to show you one example. When we talk about nanomaterials, everyone talking about, like, for example, gold nanocatalyst. When we make a small gold nanoparticle deposits on different support, they can exhibit really nice catalytic performance. So, and as you can see from this TM, this is a typical supported gold nanoparticle, for example, on iron oxide, using our TM, a conventional TM, with no such high resolution. Okay, so each white spot here represents one gold nanoparticle. Okay, for the same example, as you can see here, we use abbreviation collected TM. Besides this big particle, we also see the deposition of this mononuclear or even several gold atom coming together to form cluster. So if we use cyanide, we all know that cyanide can etch out the zero metallic gold in zero valence, right, in airs. So basically, if we treat it with sodium cyanide, then we can try to etch out all of these gold nanoparticles because they are in the oxidation of zero. So if you consider those gold nanoparticles is where the catalytic active site located, then we are expected to see nothing, right? Because all those gold nanoparticles has been etched out. But it turns out, actually, after etching, the material just keep the same activity. Okay, so should we believe our eye? Definitely no in this case. So what kind of feeling we have? Right? It's red, Brightman, and elephant, right? Because we don't have good eyes at the molecular level to really see what happened on the surface. So what can we do? So which means that we really need to study all those chemical reactions on surface at the molecular level. On metal surface, which means that it's really important to investigate all these reactions from the viewpoint of coordination chemistry. Then the challenge is, how can we get the real structures of those active sites? This is very challenging because the material is well defined. And our characterization tools, in most of the cases, is an average result. So can only give us average signal. So this creates a lot of problem. So how can we solve this problem? So one solution, which is obvious, is to develop well-defined and even atomically precise nanomaterials, right? And then if we use this atomic precise material as the catalyst, basically we can use, for example, we use atomic precise cluster as the catalyst. We can use a molecular approach to really identify their precise structures. Then we can do the correlation easily, right? So here I just like to give you one example. And for these clusters, we have isocahedral gold 13 in the core. And on the surface, as you can see, we have basically 3 mononuclear gold +1 species on the surface. And one is individuals, the other 2 are coupled together. And this cluster is quite amazing. You see, it's even can be 2 order magnitudes in their activities than a mononuclear complex, or even those clusters without the surface mononuclear unit. So this is quite surprise. Because the structures can be identified by single crystal crystallographies, then basically we can also use other molecular approach to really see what happened on the surface. It totally surprised us, as you can see here. Actually, we only see the individual surface. You see, we have a ligand which can be replaced by our reactant, which means that this individual unit is active for the reaction. And the pairs units, they are not active. So you see, their structure is so similar, but one is active, the other one is not active. Okay, so which means that actually for these structures, we need both the core and the surface gold +1 work together to have this reaction taking place. So if we can have another cluster, as you can see here, basically it has quite similar structure to the previous one, but we have 2 individuals and 1 paired. As you can see, we really see the increased activity. Okay, so which means that actually if we can modify, for example, this is the gold nanoparticle supported on carbon without any surface modification. It's inert for this reaction. But after modification, you see, highly active. So basically under TM, they are same. So it's really important to really to get those molecular surface structures. So that's why during the past 15 or even 17 years, I think my group has spent a lot of efforts in the initial years, basically doing something not useful at all. Just try to understand the structures. And in past few years, we try to make it useful. So typically, we have 3-step approach. So we make beautiful materials. Why we want beautiful materials? Because they are very uniform, as I mentioned. For the to get their structure, normally we get those spectroscopy approach. Normally, just give us the average signal. If they are uniform, then basically the average is pretty similar to the average signal, right? So that's why the material need to be uniform, need to be beautiful. But sometimes, if we want to make the beautiful material like this, it's going to be very expensive, right? So we need the materials which used in our industry, they should be ugly, easy to make. Okay, so that's why to bridge beautiful and ugly stuff is the mechanism. So we need to catch which element is the most element for the properties we want to achieve. So here is really an 8 years example. So 3 PhD students working on this project. But I'm really proud of this research. So basically, we have the palladium nanoseeds, which is only 5 atomic layers. After we deposit different amount of the copper, as you can see here, both the activities and the selectivity in the hydrogenation of this alkyne basically get increased with the increasing amount of the copper. So which is quite surprising because in catalysis, normally the selectivity is decreased with the increase of the activity, right? But in this case, both get simultaneously increased. Why? Okay, basically, after detailed study, because we have really nice model materials. So we can use, for example, X-ray absorption, spectroscopy, and even using STM. We realized that actually, with the deposition of different amount of the copper, these coppers can be in different form. If we only have small amount of the copper, they will get into the palladium lattice, so they form alloys. So it will change the electronic structure of palladium surface. So in this case, for example, if we want to do the hydrogenation, the activated hydrogen atom, the bonding of this hydrogen atom to the palladium actually get weakened. So they are easy to transfer. So that's why we can increase the activity. Okay, and then how about the selectivity? We found that if we have more copper deposited on the surface, basically they can only locate it on the surface. These metallic copper, once they get oxidized in airs, they will form copper oxide. If you get familiar with inorganic structure of copper oxide, basically they have the diamond lattice of double lattice of diamond. They are interpenetrated together. So in this case, by using STM, we found that actually this copper oxide, they just form porous layers on palladium. You see, basically we divide this palladium surface into small islands, right? So all the reaction need to be confined in this small island. So that's why we have the selectivity. Because for the double bond species, this island is too small. So they cannot have interaction with the surface. Okay, then the trouble for this reaction, for using this catalyst for hydrogenation, particularly at a high temperature, because copper-2 oxide can easily get reduced into metallic, okay, at high temperature. So how can we improve the stability? We found that because if we introduce alkyne, we all know that alkyne can form really stable copper alkyne complex, right? So with the formation of these alkynes make a copper complex, basically we can stabilize the copper oxides on their surface, the overlayers copper oxides on palladium. So which means that the copper have totally different three roles. One is to form alloys with palladium, change the electronic structure, form the copper oxide, porous layers to divide the palladium surface to achieve high selectivity. The third role is to form the really stable coppers 1 and alkyne complex to stabilize the copper oxide. So after 8 years study, everything is known in textbook, but the combination is really, really surprising. So it's not important to have those nice, really beautiful nano seeds, really expensive to make. You just use this. You see, we have a star company can make this catalyst in tons of years, really cheap. You just modify it with copper, you didn't see much change. And then with the alkyne modification, and then you can have the good catalyst for the semi-hydrogenation of alkyne to double bond species. Okay, so with this example, hopefully I convince you that actually it's really important to have deep understandings on how those species change the surface properties. So in past few years, we spent a lot of time to understand how surface organic modifiers change the chemical property of metal, and also how the inorganic modifiers, in many cases, in homogeneous catalyst, they function as a support. Okay, so we try to understand what kind of function they have for different support. And we found that actually in many cases, if we use reducible support, and actually they can help us to facilitate the electron transfers. And because the acidity and basicity of those oxide material can also manipulate the proton transfer behaviors. And in some cases, we can even use the support to have the activated species transport on the surface. Okay, I will give you one example in the later slides. So I really enjoy to investigate the mechanism. 8 years, 10 years, I think it's fine. Because once we really get a deep understanding, then we have the key element. Everything will be simple. So I think I'm going to maybe skip this part. Okay, for example, these phenylene diamine is really important precursor for high performance polymers. And in old days, if we use other methods without having very high selectivity, normally their purity is pretty low. By using our catalyst, as you can see here, actually their purity has significantly enhanced. So that's why actually with such increased purity, basically right now we can get high performance polymers easily. So in our group, we have been focused a lot on hydrogenation reaction because for hydrogenation it's really simple. So in my group, I spend can be 1 million RMB every year to buy deuterium, because I can use this isotope to identify how those hydrogen transfer. It's quite interesting. Actually, we get a lot of surprising results. For example, for the semi-hydrogenation of alkyne, this can be easily done by linear catalyst. But the problem is that the palladium loading is pretty high. They only small amount of this palladium is active for this reaction. And in principle, for the hydrogenation of alkyne, for this triple bond, we can add 4 hydrogen atoms, right? If we want to get the double bond species, basically, you can prevent the addition of the 3rd hydrogen, or even the addition of 4th hydrogen, right? Actually, there are 2 approaches. And indeed, we will be able to achieve that. For example, I'm going to use this example. How can we prevent the addition of the 3rd hydrogen? So, for example, we can deposit palladium single atom, the blue dot here, and we use this palladium to activate hydrogen molecule. They will be activated into hydrogen atom. And this hydrogen atom can spill over onto copper. The yellow dot you see here, they are all made from copper atom, so they can spin over. As we all know that, for copper, they have good interaction with the triple bond species, right? But for copper, basically, they are not good to absorb double bond species. So if this hydrogen atom can spill over to copper, then Basically, if we can use this copper hydrogen atom for hydrogenation, then basically we can stop the reaction at double bond species, right? Because our copper don't like double bond species, so they won't absorb on the surface, right? So in this case, basically, I think I'm going to skip all this evidence. Okay, just give you the result. Now, we can have this palladium loading as low as 50 ppm. Because the only function of palladium is to activate hydrogen molecule into hydrogen atom. And the copper can be used now for the hydrogenation. How many minutes I still have? Done? 5? Okay. So as I mentioned, the second pathway is to have the third atom added to the double bond, which means that this double bond will be open, right? Because it will become single bond, and they can do the rotation, right? So how can we prove that? Actually, it's rather simple. We can use isotope again, okay? So you can have the third hydrogen atom get added onto a double bond, and then if we, at this moment, we change the atmosphere into D2, then you can see the HD exchange, right? Okay, so indeed, that's what we see. And we can also, because the double bond is open into single bond, then should be, the rotation should be allowed. In this case, they can do 6-to transformation. Okay, I think okay. Okay, another example is regarding the hydrogenation of nitroaromatic. This is really simple to make a bean, but if we don't modify the metal surface, any functional group on, for example, on this benzene ring, they can also get activated. So, for example, if we have hydrogen on benzene ring, they will get cleaved. Okay, they will get removed. So how can we prevent this kind of dehydrogenation? So we can modify the surface. In this case, the molecule won't have direct interact with the metal surface. And we found that actually, if we select appropriate ligand, the electron and proton can still transfer to our nitro group. So which means that we don't need to have this nitro compound directly absorb on metal surface. So we can prevent a lot of side reaction, right? Okay, so with this kind of approach, I think this was just published in Angle 1 Chemise, and basically, even for the hydrogenation of nitroaromatic, we can achieve the selective production of all 6 products, including a bean, and niso species, and hydrolyzed aniline, anything you want. So actually, this is even a better nitrogen reductants than natural ones. And more importantly, this process already been applied in Chinese chemical industry already for the production of this useful drug. So, and with this, I think I'm going to conclude my talk. So basically, with this understanding, now we can produce really high quality precursors for different drug and even polymers, precursors, and the waste the production has been minimized. For example, in this case, the production of solid waste reduced from 4 tons to 50 grams, which is amazing, right? So, and it's so fortunate, actually, Chinese government has listed this technology as an encouraged technology for chemical industry. And hopefully I convince you that the surface and interface modification is very important. And with this, actually, I realized that even at the molecular level, it's not enough to really understand the whole process. As I mentioned, the chemical reaction can be proceeded without have the molecule directly contact with the surface, which means that the transfer, the electron and proton should be very unique. We found that actually. The transfer of those electron and proton can be in the tunneling, quantum tunneling pathway. So a lot of interesting finding here, but because of time limitation, I think I need to stop here, and hopefully, I think our next step research is try to expand our investigating region from just on surface to above surface, because this is really important to couple the weak energies into the reaction. So we need to really take the quantum tunneling the mechanism into the reaction. With this, I think I need to stop my talk and thank my collaborator for their contribution. Thank you.
Thank you very much for your talk. It was really nice, enthusiastic, really cool. I think we have time for one quick question there in the back.
Thank you for your talk. Do you see an influence of surface orientation, surface energy, on your chemical reactions?
Sure. The orientation. What do you mean the orientation? Is the arrangement of the atom?
No, for example, you presented most of the works on 111 surfaces. So
Right,
when you go for 100, 110, 112.
Yeah, depend on the reaction. Okay, so if we don't have the chemicals direct contact with the surface, then actually it's not important. But in the case of the, in the examples, I use a single atom of palladium to reduce the amount of the palladium. In that case, the surface is really important. Only copper 100 can work for the reaction, because the absorption, the bonding energy of the reactant on the surface is totally different. Depend on the orientation. Yeah. Thank you.
Right.
Sorry, I didn't.
No, you did great. Thank you very much.
Thank you.
So now we have a little break. We cut a bit on it. We're going to make it until 11:05. So please be back here at 11:05 for the next talk. Thank you.
Has gotten back into their seats and enjoyed their break and all the conversations. Sorry to have to end that. We can continue when we break for lunch. So this is session number 2, and it's my pleasure to introduce Martin Heimeyer. Martin is a professor at the Materials Science and Engineering Department at the Institute for Applied Materials in Karlsruhe Institute of Technology. His research is mainly targeting integrated materials development guided by thermodynamic modeling, leading to material synthesis via various methods, and ensuring scale bridging characterization techniques. In 2020, this is very impressive, he received 10 million euros in funding for the development of materials for extreme applications and conditions, which just got extended, I heard, so congratulations. He has mentored over 100 students, including postdocs, so very welcome to have you, and the floor is yours.
Good morning, everybody. So I hope I need not cultivate my cough. Like this seems like to be a Karlsruhe disease now. I had it 3 weeks ago, so I hope I can present without any interruptions like this. But just in case, I apologize. Now, so I decided to switch the topic a little bit because I wanted to bring some link in towards one of the journals which we celebrate here, namely Advanced Engineering Materials. You will see in a minute what I mean by that. So the topic I have chosen is high entropy alloys, or HEA, and my specialty is to focus on refractory high entropy alloys. Refractory metals and alloys are high melting metals like tungsten, molybdenum. One of my predecessors has talked about molybdenum trioxide. This is actually probably beneficial for his applications, but in our case it's very detrimental because this oxide evaporates already at 600 degrees Celsius. So if you want to develop a structural material which should withstand severe environmental conditions beyond 1000 degrees Celsius, of course this is not a good choice. I will show you how we can handle this. Before I go into the details, there's a number of authors here, as you can see listed. Most of them are from my own group, but some of them, Pramanik and Chauhan, are people who were before at KIT but are now working at Indian Institute of Science in Bangalore, with which we collaborate. So, high entropy alloys challenge the classical alloy design paradigm with one base element and minor additions of other elements. Like many of you know that steels consist mainly of iron. Then there is a little bit of carbon, which changes the world completely, and some other alloying additions. But the main element, 80% in atomic or whatever, is probably iron. And the same holds for aluminum alloys and so on and so forth. So what high entropy alloys, or what the hypothesis and the approach of high entropy alloys was, is that we take multiple elements with equimolar concentrations and look into the properties, how these might perform as compared to these classical alloys. And I like to draw your attention to one paper, one seminal paper in Advanced Engineering Materials. In fact, it was a communications only. This is a short paper. And these guys from Taiwan, Yinwei Yi, I hope I pronounced the name correctly, had really severe troubles getting it published in a high-impact journal, high impact factor journal, because many of the reviewers said this is completely bullshit, you know. I mean, and the editor at that time, I think it was Jörn Ritterbusch, probably. He decided he would accept it for review, and finally it got published. And since 2004, so this is now 20 years, pretty much, it has been cited over 10,000 times, which is probably the highest cited paper in advanced engineering materials ever. I mean, I didn't check that, so the guys, the experts should do it. So this is how it can happen, right? Okay, good. Of course, they have developed it over the years, and I will give you a brief glimpse of what the hypothesis or the theory behind high entropy might be. Whether it's correct or not is a different story, but at least it has ignited the field. It exploded our design space. This is the last bullet point down here, because while you were working in phase diagrams just at the borders of these phase diagrams, now you jump immediately into the center, which is of course completely unexplored, not only from experimental point of view, but also from thermodynamics or theory point of view. So any extrapolation from the corners, I will show a slide in a minute, towards the center of this phase diagram, of course, is to a first order approximation totally wrong. Yeah? But this is of course exciting because we find a lot of new materials with interesting properties. Actually, Ye was not the only one in 2004 to publish a paper on this. Brian Cantor from, at that time, Oxford, published also a paper in Material Science Engineering A, but he did not invent the term high entropy alloy. He even didn't know what he has found, you know. But he published it, and then everybody forgot about that. And later on, of course, we jumped on this because we found it, and then a guy from the US, a good friend of mine, Iso George, he actually termed the alloy which was invented or first found by Brian Cantor as the Cantor alloy. I will also show that in a minute. So, what is the specialty about high entropy alloys? As I said, usually you would have a material like this. So one element, iron atoms in gray, and then some special alloying element, maybe tungsten, because this is a big element, which now is placed here in this body-centered cubic unit cell somewhere in the center. And this big alloy would lead to a lattice distortion. Now, you can imagine if you play around with this and add more of these elements, which all have different atomic sizes, you would create severe, very severe lattice distortions. And these severe lattice distortions were claimed by Professor Ye to cause very strong solid solution strengthening. I'm a classical physical metallurgy guy, so I'm interested in improving mechanical properties mainly. We have heard a lot about functional properties in the past session, so here this talk is about mechanical properties, to promise what I will talk about in the next few slides. So this was one claim. The second claim was that if you make such a random solid solution, this would also impact diffusion. Diffusion is atomic mobility in the material. So if you have a big atom next to a small atom, they may like each other very much, so they would not like to diffuse a lot. So that would give rise to an extraordinary thermal and mechanical stability. So these were the two most important claims by Ye, also in this paper already. We will see that that might not be true. So this is the basic idea, very simple, everybody should know it from textbook. Not only material scientists, also chemists and physicists should know, will know this. So the free energy, G, is determined by the enthalpy, delta H mix, the mixing enthalpy, minus this entropy term. And the entropy term comprises the change of order when phases are formed. Literally, the entropy term was emphasized by Ye to stabilize disordered homogeneous solid solutions in favor or over intermetallic compounds, which usually form when you go into some weird compositional space in the center of a phase diagram. So, to give you an example, and this is this famous Cantor alloy, which Brian Cantor did not call after him, so we should not give credit to him with respect to this. So if you would calculate the configurational or mixing entropy, as you can see here on the left side of this first equation, you would end up when adding 5 elements in equimolar concentrations, you would get a mixing entropy of 13, roughly speaking, 13 joule per Kelvin and mole. If you compare this to engineering alloys, so in Karlsruhe we have a favor for 42 chrome molybdenum 4. This is a classical steel, so we investigated that a lot. You can see that this is a huge difference, 13/2. Yeah. And if you would take an aluminum alloy, it would be even lower. So the claim was, if we mix this, we get a high mixing entropy. And this high mixing entropy, because it will be subtracted from the mixing enthalpy, would probably stabilize solid solutions over intermetallic compounds. And this is what I mean by that. This is the phase diagram I promised to show. On the left lower corner, you see classical superalloys. I will talk about superalloys in my research, which comes next. Nickel or cobalt-based superalloys or refractory-based superalloys. And on the right-hand side, you see this gray shaded area is the classical steel corner. But nobody knows what is in the center of this phase diagram, the green area. And of course you can play around with the whole periodic table. This is again nice because it keeps us busy for decades now. Yeah? You can put aluminum, titanium, manganese, and so on and so forth, right? And check what you will find in the center of or roughly speaking, in the center of this phase diagram. And this is what you usually find. Not necessarily a random solid solution as shown here. You know, the atoms are now symbolized by 5 colors because we do not know which atom sits on which lattice side, and this is the random mix. Usually what you would see in this phase diagram, you would get intermetallic compounds like the famous sigma phase. I just want to address one of these. The sigma phase is the iron-chromium phase. You see already from the unit cell that this might not be very ductile or well deformable. This is a brittle phase, so if I talk to steel guys and say, well, we have developed an alloy which has a sigma phase on the grain boundaries, they say, go away with that. That's not good, you know, that's kiss of death, you know, we don't want to deal with that. So these intermetallic compounds are not good, and that's why the interest was so strong on these high entropy alloys, because of favoring the random solid solutions instead. So to cut a long story short, 20 years, this concept was now also expanded to other materials classes, not only metals. There are oxides, high entropy oxides, as many of you may know, glasses, polymers, and so on and so forth. I will concentrate on metallic materials though. And the problem I want to tackle now is that we want to get mechanical property combinations in a way that we want to have high strength. Everybody wants high strength in structural materials, but at the same time also good ductility. You need to deform the material to a certain semi-finished product or even a finished product. And second point, high temperature stability. So you also like to have very good oxidation resistance and a very fine, a very stable, not necessarily fine, but a very stable microstructure, because if the microstructure changes, then the properties will change. Good. So this is state of the art, with which I want to compare now our research. So nickel-based, so some of you, probably the guys from China, will have flown into Frankfurt. So if you by accident were on a 747 with the newest releases of aero engines, then you would have flown with an aero engine which is called the GE, General Electric NX engine. And the first two blade rows in the high pressure turbine section, as indicated by the blue arrow, are made out of single crystalline materials, so no grain boundaries, and these are nickel-based alloys. CMSX4 is the name, yeah? And this is state-of-the-art. They can withstand temperatures of 1050 degrees Celsius, metal surface temperatures, not necessarily combustion temperature. This is much higher. I don't want to tackle this. Now, the microstructure, which gives you this beneficial combination of high strength, ductility, and also decent oxidation resistance, together with the chemical composition, can be seen on the right-hand side. You need a multi-phase microstructure. A single-phase random solid solution would never make it. It would be too soft at high temperatures, no matter what kind of lattice distortion you create by throwing in hundreds of different types of atoms. So this is a gamma phase, in bright, which is the ductile matrix phase, and in greenish, the gamma prime phase, which is a coherent particle embedded in the gamma matrix. And this material benefits from this two-phase microstructure because this two-phase microstructure is able to withstand plastic deformation up to very, very high temperatures. So this is state of the art. Everybody flies with that. And you need not worry about that. That's really safe. Yeah? So you can see here that this is basically what we could claim is this is kind of a high entropy alloy, because you don't have just nickel, you have chromium, cobalt, molybdenum, rhenium, tungsten, all kinds of chemical elements which are sometimes also very expensive, like rhenium. That's why now currently people try to avoid the rhenium, but then the material gets softer, so you don't want to have a softer material, and so on and so forth. I don't want to go into details here. If you want to make a breakthrough, or if you want to break this current state of the art, you have to think a little bit outside the box, still in the metallic materials regime. And now we come to the refractory high entropy alloys. Why are they so interesting? Because they have melting points or solidification temperatures typically beyond 2000 degrees Celsius. And this is due to the fact that all these elements, look at the red or the blue alloy composition, niobium, molybdenum, tantalum, tungsten, and so on, all of them have melting points beyond 2400 degrees Celsius, some of them even 3000 degrees Celsius. So what you see is, if you plot the strength, sigma O2 is a kind of a measure for us in engineering disciplines for the strength of the materials. If you plot strength of the material versus temperature, you can see on the x-axis, then you would see that all these nickel-based alloys, the gray data points, fall off at 900 C and then remain on a very low level. This is because this two-phase microstructure I showed on the previous slide disappears. So the gamma prime precipitate phase gets dissolved, and then you end up with a solid solution single-phase material. And this is very soft because it's down here, right? Okay, so in comparison, these two alloys, single-phase, solid solution, show a plateau in strength and then fade away maybe at 1600 C. So if I would put that in an engine, I could save 20% of fuel easily. There's one problem. If you, and I mentioned this before, molybdenum trioxide, remember? These alloys oxidize like hell. They don't survive in minutes. I need not go into this. I just skipped that because I wanted to address the oxidation. So if you would just play around with tantalum, molybdenum, niobium, tungsten, you would end up with examples like shown here on the right-hand side. Catastrophic oxidation, the upper picture is molybdenum basically, so you get yellow powder, very nice, yeah? But useless. If you play around with niobium and tantalum, you get bulky oxides formed on the sides of these metallic particles, and if you would inspect them after 1 day of oxidation, you would think, well, the material is still intact. If you would make a cross-section, there's no more metal inside, it's just oxide, yeah? Totally gone, right? So these two, or these refractory metals, would not make the job. You have to do something against it. So first you want to make use of the high melting temperature, that's why you add tantalum and molybdenum, but then you need passivating elements, like chromium, titanium, and aluminum. Aluminum forms alumina, and this is a very protective oxide. So besides that, titanium and aluminum, of course, lower the density. I didn't talk about density, but if you would make a turbine blade out of tungsten, I'm not sure whether this airplane would ever take off, you know, because of weight issues. So you have to keep that also in mind. So this was our starting point with this equimolar high entropy alloy, 5 components. And this is how we compared it to state-of-the-art CMSX4. This is shown on the lower right-hand side. CMSX4 oxidized at 500, 1300, and 1400 degrees Celsius, compared to our equimolar alloy in blue, 530, and so on and so forth. Even at 1500 C, after 12 hours, this material is protected by an oxide scale, by a mixed oxide scale, which we discovered unusually. We didn't know that up front, so this was kind of trial and error. And at 1400 C, still also very fine, and this alloy is already partially melted. So that's an unfair comparison, you know. You cannot compare an alloy which has a melting point of, or melting range of 1300 something degrees Celsius with an alloy which has a melting point beyond 2000 degrees Celsius. So we could claim, and actually I want to make this side comment, I was asked by the chief editor of Advanced Engineering Materials, by Sandra Calveram, to submit a review article about these oxidation issues, and so the details can be found in this review article, and I'm very happy that we got it published. So it's also cited already. I just checked it more than 100 times. I will not reach the 10,000 times though, I'm sure. Okay, so now all problems solved. We have oxidation resistance, yes or no? Of course not, right? Because this is a complex issue. We want to tailor a two-phase microstructure. This one was still a single-phase microstructure, so it would not be strong enough. Two-phase microstructure, I don't want to go into the details, but just briefly, this is a schematic sketch of the phase diagram, and you can see here that you have to have a solubility gap at lower temperatures, which is now here designated as A2 plus B2. For those who are not familiar with crystallography, A2 is body-centered cubic unit cell, disordered. B2 is kind of the derivative of that, it's an ordered structure. So we play around with exactly the same microstructure as in nickel-based alloys, which have a disordered FCC, face-centered cubic matrix, and a ordered L12, also face-centered cubic. This is strictly speaking not correct, so if anybody here in the audience is a crystallographer, he would beat me up now, but just to explain it in simple words. So we want to play around with this coherent two-phase microstructures. And that means, because we want an A2 matrix, because of ductility issues, we need to go along line 2. Not along line 3, because we can then get the reversed microstructure, a B2 matrix, which is probably presumably brittle, and we confirmed it that it is brittle. So we have to go along A2. So we had to find an alloy composition which serves this issue. And this is a calculation from thermodynamics databases, in-house developed, partly also used from commercial suppliers, which, however, because of the unknown chemical compositional space, is strictly speaking not correct. You will see it in a minute, but just give you a note here. So this two-phase region, which is predicted here, A2 plus B2, which we want to have, shows an onset temperature of around 600, 700 degrees Celsius. this is the prediction. The experimental result is different. I will show you in a minute. So concentrate on the green line, green vertical line, as compared to the orange vertical line. So you see that this is just nearly the same composition. Chromium was fixed to 8 atomic percent, but we played around with the aluminum content, 10 versus 15, on the expense of the other 3 elements. So this is no longer an equimolar composition. So we moved deliberately away from the equimolar strict high entropy alloy definition because we wanted to form a two-phase microstructure. And this is what we got. Again, I don't want to go into details. This is the 10 aluminum alloy, so the alloy which should form an A2 matrix plus B2 precipitates. And in fact, this is what we got was correct. Namely, look at the left diagram, micrograph. You see that you have a bright phase and a dark phase, and the bright phase is the A2 matrix, which is enriched in tantalum and molybdenum now, because they have the highest melting point, whereas the B2 precipitates are the dark phase, and they are enriched in the lighter elements, titanium and aluminum. Yeah, this is because of solidification through arc melting and cooling down. I don't want to go into these details now. And we confirmed everything by HAADF in the TEM. One really important note I want to make is look at the scale bar, 500 nanometers. So this microstructure on the left-hand side is extremely fine. So our first fear was that this would coarsen like hell if we subject it to 1000 degrees Celsius or not. I will show some examples in a minute. And I skipped deliberately now the right diagram. This is a differential scanning calorimetry investigation, which gives us an idea about at which temperatures the reaction sets in. And you can see here that these triangles, these reverse triangles, are by no means at around 600 and 700 degrees Celsius. They are between 1000 and 1100 degrees Celsius. So the prediction by the thermodynamics database is really wrong. Yeah? But this is due to the fact that nobody has done experiments before. So now they have to adjust the thermodynamics database and everything would work well. Now we have confirmed that this is really a nucleation and precipitation reaction by deliberately going to 1200 degrees Celsius and rapidly quench the alloy. Not slowly cooling like you do normally in manufacturing, but rapidly quenching, you know, by throwing it into water, for example. And then you see a single solid solution on the right-hand side. Here, no features can be seen, at least on a single-digit nanometer scale. So that's really a precipitation reaction from a single-phase solid solution. So this strategy is correct. Now, we can go to the 15 aluminum alloy composition, and this is, of course, then the reversed microstructure, which shows up. Now you can see here that we do not have a bright matrix phase anymore. So the major phase is now the dark phase. We get a B2 matrix and A2 precipitates, and also the signature by DSC is different. I don't want to go into details. You can ask me later on if you want. I can just assure you this alloy is of no use. If you let it fall down on this floor, it would break into parts. So it's dead brittle. Good. And here is my slide on the coarsening behavior. As I said, as quenched, you end up, just look at the upper row, if as quenched, it would be a single-phase solid solution, and then you anneal it at 1000 degrees Celsius for different times, and even after 1000 hours, the scale is still pretty fine. Only 250 nanometers, so you get some kind of directional coarsening, which is also well known from these nickel-based superalloys. I also don't want to go into details because of the time issues. But if you look at the lower row, you see that you get similar, maybe different microstructures, but the reverse in contrast. So now the dark phase is the matrix phase, and the bright phase is the precipitate phase, which we don't want to have. We want to have the bright phase, the A2 disordered solid solution, as matrix phase. So we then did some, of course, high application at high temperatures requires creep studies. mechanical deformation at these high temperatures. It's of no use to state that you have a material which is very strong at room temperature and ductile or not, because you don't apply it at room temperature. If you fly, even in idle condition at 9,000 meters altitude, the engine is hot. 1,000 degrees or more. So we made these alloys with arc melting, and then we checked for the lattice misfit, and you see here that both faces do have not exactly the same lattice parameter. They have a so-called lattice misfit, which is in this case positive. Is there anybody in the audience who is working on nickel-based superalloys? This would be a slide for an expert on this field, because most of the nickel-based superalloys have a negative lattice misfit. Here it's the opposite. I also don't want to touch this. Now we did the creep behavior. Creep, just to explain briefly what has to be done, is you apply a certain stress or load, mechanical load, and then let the sample deform at high temperatures. In this case, 1,000 degrees Celsius, 125 megapascals. That's a pretty high stress. It's actually a stress which is realistic for a turbine environment. And then you check the strain on the y-axis, which develops over time. You can see here, this is of course a lab scale experiment. This is only 2 weeks. So some of the PhD students have to do longer creep experiments. When I did my PhD on creep, actually my longest creep experiment was 3,000 hours. This is 4 months, 5 months, then I couldn't wait anymore. I wanted to inspect the sample. Anyway, so we did 3 times the same test to check reproducibility, and you see that, well, you are no experts in this field, but this is already a pretty good creep response. And then we checked different temperatures. We started with 1,000 degrees Celsius on the previous slide. We increase the temperature to 1030. So here the strain rate is plotted, which is even more important than the strain. Strain rate means how fast the sample elongates while subjected to a load. And typically, you might wonder why we just plot 1% of strain here. Well, 10% of strain would make the blade be in contact with the casing of the turbine engine. That would lead to failure, and then you don't want to sit in this airplane, So there's not a lot of strain allowed, And then when we changed further, we saw that just changing from 1030, so 10 degrees more would raise the creep rate quite dramatically. So something must be going on here, and 1050 and 1060 is even higher. But this is the important issue. What happens at 1040 degrees Celsius? And this you can see in a different type of plot, strain rate versus stress. So we did different stresses because, the turbine engine not always goes on full speed or full power. They also reduce. Once they have reached the high altitude, they reduce the power of the engine. And so you want to see the whole characteristics with respect to stress and temperature. That, again, keeps us busy as engineers because we need a lot of experiments. I'm nearly at the end. We need a lot of experiments to be made, and this is, of course, expensive, so the industry pays a lot of money on this. So we further analyzed this. I don't want to go into details here now. Let me just conclude with a final slide. If you now plot our data in this high creep resistance regime, the blue data points at 1030 degrees Celsius, and compare that to the orange data points, which are the single crystalline CMSX4, you see that we are already at a stage where we can compete with those commercial alloys. But they have been developed over the last 70 years. They started development of nickel-based superalloys at the end of World War II. This alloy development, which we did, and we have used only 5 elements instead of 10 or more, has been a matter of 3 years or so. So I think this is very encouraging, and I could, of course, explain a lot more on this. I will skip this slide and start with my conclusions. We can show that at certain chemical compositions, we can reproducibly form a disordered solid solution, A2 matrix and B2 precipitates, which mimic the microstructure of the very successful nickel-based superalloys. These precipitates are ultra-fine, have an outstanding thermal stability, although you might know this from textbooks, Open crystal structures like A2 or B2 have a much higher diffusivity or diffusion coefficients than close packed structures like hexagonal or FCC, face-centered cubic microstructures. And then there are some additional specialties which I don't want to address now. And with that, I thank you for your attention, and I acknowledge the German Science Foundation for financial funding. Thank you.
I think we have time for one quick question.
Martin, thank you for that talk, very interesting. What I would like to know is, many experiments you need, and for looking at these alloys and characterizations, do you use machine learning or AI-based experiments, or do you plan for that in the future?
Not yet, but of course this is an obvious issue, especially when you do not have the database at hand to predict material compositions which might be useful. At the moment we more rely on our intuitive knowledge on physical metallurgy to at least focus or minimize the compositional space, you know, not to go all over the place. But this is an obvious issue. Yeah.
Okay, let's thank our speaker again for the sake of time. It's my pleasure to introduce our next speaker, Professor Eva Blasko. Eva received her doctorate in chemistry at the University of Zaragoza, and she is an Alexander von Humboldt Fellow, like myself. She also did research in the groups of Professor Chris Barner-Krolik in polymer chemistry and Professor Wagner in physics at Karlsruhe Institute of Technology. So there's a very strong KIT element in this room today. She was appointed a junior professor in Heidelberg, and she was appointed a full professor in January 2023. And with that, I would like to introduce Eva, and the floor is yours.
Yeah, thank you very much for the kind introduction, and I would like to start also thanking the invitation to be here today, and also I would like to congratulate all the advanced team for the anniversary. And perfect, so now should be my second slide, but it doesn't matter. So it's my pleasure, as I said, to be here today to present our journey in the development of new materials for 4D printing. So we are coming from really nearby. So our team moved in 2020 to Heidelberg, and I really recommend the beautiful city of Heidelberg. And I think the pointer is not working. Okay, so here is an overview of what we are doing. As I said, our group focused on the development of new materials for 4D printing, and our strategy is to shape these materials on 3D with high precision, and for doing so we use light as a tool. So that's why we are very interested in the photochemistry behind the processes. You will see in some examples that we also use self-assembly. The core of my presentation will be 4D printing, and I will try to use my last minute also to show you the work we have done with sustainability. So, as I said, we print with light. Photochemistry is very important, and I would like to start explaining very basic the printing technology we are using, and for that I will start differentiating between one photon and two photon absorption. So in the case of one photon, you all know we can excite one molecule from the ground state to the excited state by the absorption of one photon. This can be exactly the same by the absorption of two photons. You already see that we need different energy, but what is more important, we will use higher wavelength, but also is the probability of the event. While one photon absorption is a relatively probable event, that's not the case for two photon absorption processes, so we will need femtosecond strong lasers, and this process, it will only happen in a very, very small volume. This is well known also in microscopy, and here is the visual example that I always show the students. So if you have fluorescent dye in a cuvette, as you see in the image, if you do one photon absorption, you see the emission of the dye in the whole irradiation path. If we do the same by a 2-photon absorption, you see we move towards the infrared regime, but actually we need even to zoom in to see where this process is happening. So now you see the example for the fluorescent dye, but of course we can also use for polymerization that bring us to how we can use these processes for additive manufacturing or 3D printing. So 1-photon polymerization is using conventional techniques such as stereolithography or DLP, or maybe you know CLIP, that is commercialized by Carbon 3D. And if we move to the 2-photon polymerization, then we can access very, very small features, and that will be the focus of today. So in case you are not very familiar, I have here an animation, how it looks like. So we have a transparent substrate, we have our material, and we will talk later much more about which material we use. We focus the laser, and as it will be as a pen, we photopolymerize really precisely in small volumes. With that, we achieve sub-micron resolution, and in principle, we can print almost any arbitrary geometry. An application of these techniques started in the field of optics and photonics. Lately, it's also moving towards microfluidics, soft robotics, and life science. And I will try, as I said, to really show you today our journey and how we are using this technology, and also how we develop new materials. So here's a timeline of the, I would say, also a bit more technological part. So the first structure, or microstructure, better to say, printed with this technology was in the 90s, 2000. And of course, the key was 2010, roughly, when this technology was commercialized. So at the moment, you can see in the right side, we really go to fast printing, really smooth. So now it really, I would say that the technology is getting into the mature phase. But you have seen that there are many opportunities, many applications, and as a chemist, I really believe that along with this development in the technology, we need the development of new functional materials. So here, how it looks like, we say a conventional ink. So we need photopolymerizable material, so active. In contrast to the macro scale, as I said, we really focus the photopolymerization in a small volume, so it's very important to have high density of photocross-linkable groups. A good photoinitiator, here are examples of multi-functional acrylates, because acrylates, we all the polymer chemists, we know the kinetics are fast, so are a good system for working. But of course, this doesn't fill all the criteria for all the applications, and this is what we have been doing during the last years to really incorporate functionality into this micro and nano scale. And one of the functionality that is usually desired for many applications, such as robotics or life science, is response, and that brings me to the 4th dimension. So what do we mean with 4D? So we mean that we have a printed structure that is not static, but dynamic. The 4th dimension is time, so we can, with external stimulus, change properties of the structure. For example, one property can be shape. And for that, we combine 3D printing technologies, in our case, 2-photon laser printing with responsive materials. And the first example will be with some conventional responsive polymers, hydrogels, liquid crystal elastomers, and shape memory. Of course, very different materials in a way, but the mechanism or the fundamental that we use for achieving this change of shape or change of the 4th dimension is very simple. We rely on a transition. In the case of the hydrogel, we rely on a transition from a hydrophilic to a hydrophobic material. In the case of liquid crystal elastomers, you will see it will be a transition from a more ordered material to disorder, and the same in the shape memory polymer. So let me start with hydrogels. So hydrogels I will start with a very simple one, but I like very much the example because it shows all the capabilities of the technology. Polynipa, very well-established thermoresponsive polymer. So here that was done by Mark Hiplam at the KIT, my time at the KIT with Professor Martin Basmeier. So the idea is we have the monomer, a cross-linker, so we print hydrophilic hydrogel, and when we go above the low critical solution temperature, it becomes hydrophobic, it shrinks. So that, of course, if you don't just polymerize, it shrinks isotropically, but one can play with the laser and print some simple microactuators, as you see here, just playing with the printing conditions. So you can use high laser power to have a more cross-link material, that is the post, the blue post, that it won't respond, and then a beam that is printed with lower and higher power. So the part with lower power is lost cross-link, so it responds more. It will like shrink more, as I said, and then you will have a bending in direction when you go. Of course, you can go more complicated. You don't need to do just a straight. You can combine the segments. And as you can see, we can experimentally and numerically really control the actuation of hydrogels. Later, at the time at the KIT, we also, together with Christine Selhuber-Unkel, use these active materials for incorporation in microfluidics, for having active parts. Also, array of pillars can act as kind of size sorting. So there are plenty of opportunities. I'm not going to go into details, but only to tell you that one can play with other chemistries, for example, host guest. And this is another example together with Professor Basmeier, just to show you that this technology also allows you to have multi-material microstructures. So for example, here you can combine stiff structures with adhesive that are the orange one, and then you can manipulate and stretch cells. And our very last example that it was recently published in Advanced Science. Sorry, that's a typo. Actually, it's advanced. One is Science Advanced and the other is Advanced Science. Sorry for that. This one, we are particularly proud because we went to really living systems. So now we can have this fish embryo inside the printer and really print inside. I'm not sure if you can see it, but here we print inside the eye some spheres and stars. That's a first proof of principle, but we believe that that may be game changers for like living organism and implants printing. Okay, so we have talked about hydrogels, which are, I would say, standard material for soft and living systems where we have a water media. But if we want to have actuation at ambient conditions, one of the favorite choices are liquid crystal elastomers. And as I said, in this case, we rely on this liquid crystal transition. These materials have been explored at the macro scale really for many years. We have tried to really go to the next level at this scale. Then very important for the controlling the actuation in this material is the order. If you are not able to order the molecules, they won't actuate in the direction you want. Very often, people use for the macro scale surface rubbing, but that limits you a bit with how many actuations actually you can have only one per substrate. So here what we did, also again starting at my time at the KIT, was to have our liquid crystal monomers formulation in a system that we can control like per voxel, so per in 3D, the orientation of the molecules by applying an electric field. And this way, this allows you to print this complex actuator. So here you can see all the orientation of the liquid crystal until 9, if I don't remember wrong. And you see that now we can really go to define printing and also actuation. So if you have a look of the temperature, it's rather high. This is the result that we have a highly cross-link material. but we are a big fan of light, so the next step was, can we use light instead of temperature for actuation? And that was the work of Li Yun, a PhD in my group. So that sounds simple. We need light, then we use a photoabsorber, then we will have light actuation. But you remember we are using light also for printing. So that I'm not going to go into the details, but there was a lot of tricky development until we find dyes that on one hand, they are not competing with the photonization and also compatible with the liquid crystalline. So that way, we have now developed the methodology. We can use almost any dye in the whole spectrum, going from visible to more infrared light, which is maybe beneficiary if we don't want to use UV light. And now we have actuators that we can decide which kind of wavelength we want to use and even mix of them. And also some metamaterials were printed like that. And the last type of polymers we explored in this 4D printing were safe memory polymers. For the sake of time, I'm not going to detail, but here the idea went to miniaturizing this safe memory effect, also using two-photon polymerization. Okay, so that was the first, I would say, steps in the journey of 4D microprinting. And what next? So if you may remember, I showed you a slide with all the mechanism. I said that they are different materials, but they rely on a transition so that you can see like kind of an on-off. So they are good for actuation on and off, but still far away from sophisticated function or movements as we know from nature. So the idea was, can we, as very often, take inspiration from nature to go a bit step further and incorporate more lifelike behaviors? And you know that living systems, they can grow. They also change the mechanical properties the same. We grow, at some point it goes a bit down, but now we focus on growing and getting bigger. And how can we do this with synthetic? So we started with a simple that was done by Christoph, also here in the audience. We know diacrylates work very nice, so PEG diacrylate. And here we incorporate a new component, is this tempo with a polymerizable group. So you know tempo is sometimes even included in some formulation as a stabilizer. And here what we did was to push a bit the conditions, so to trap the tempo. And now we have a network with alkoxamine trap, and now we can play with the alkoxamine chemistry. We can, on one hand, use these alkoxamine units as an initiator, so we can use nitroxide-mediated polymerization for expansion, for this growing. And we can also, in theory, use a dynamic covalent bonding opening if we have an excess of tempo. So now we have 2 degrees of freedom. We can change size, but we can also fine-tune in parallel the mechanical properties. And here's more the chemist. As I said, the idea was to trap this nitroxide into alkoxamine to use them as either exchanging or extending. We selected styrene as a monomer for the extension for 2 reasons. On one hand, we have a bit of contrast on the mechanical properties to prove the concept from soft polyethylene glycol to more stiff. And on the other hand, also styrene is a monomer that usually due to slow kinetics, you cannot print by alone. Okay, so here is the optimization. I won't go into the details, but I said that the tempo is usually a radical quencher. So that means that we really need to take care that it's not completely quenched the polymerization, so the printing is efficient. We follow all the processes, both the incorporation of the tempo and also the extension via IR and TOF sims. And here is the result. So Christoph printed this micrometric gecko, and we add an excess of tempo. And then you see, in principle, not many chains. Reason is because we have still a lot of covalent covalent bonds, I can tell you that we are already there in a system that this is more dramatic. We see a slightly decrease of the Young modulus. But what happened when we do the extension with styrene? So we start with our gecko at 0 time. After 2 hours, gecko grows. After 4 hours, grows even more. And it's not only growing, it's also stiffer because of the incorporation of this styrene. So we can really dramatically change, increase 2 orders of magnitude the Young modulus. And here is not only the gecko, also Christoph printed beautiful flowers and octopus. And here you can see the effect in the stiff image. Okay, so now I have shown you in the first part of my presentation how we went from more conventional responses towards playing with macromolecular engineering. So the micro scale, we have it under control, we can have some control response, but again, far away from nature. And one of the reasons is, as you know, all the natural systems, they have hierarchical order, so it's really under control, all that is also at the nano and macromolecular level. And this is what we have been also trying, of course, again, far away from the perfection of nature, but trying to control also the nanostructure and the macromolecular level. So let me give you some example how we are able to control the nanostructure. So there are some examples already in the literature from Cyril Boyer. Also, this strategy has been nicely explored by Pavel Levkin for the preparation of nanoporous structure. So here the idea is to have 2 systems that when they polymerize, they become in 2 phases. So then you have phase separation, and then you can have a kinetically trapped morphology. So that works very nice, but of course it has the limitation in terms of long-range order because it's a kinetically trapped process. So our approach was I went back to my old friends, block copolymers. I made my PhD in block copolymers, and they have been also, again, many, many years explored for soft lithography in 2D. Can we bring this to 3 or 4 dimensions? So that was the work of Britta. She prepared a library, a very, very long library. Here there are some examples of block copolymers based on polystyrene and PMMA that we know that they phase separate. And the PMMA block, we incorporate groups that can be polymerized just to allow this printability. So we play with the composition, blocks, length, and here is the workflow. So very important, we need to make sure that we have already self-assembly in the ink. Then we check all by Sachs, and the selection of the solvent was very critical. We print them, and now, of course, it's not enough to have a nice SEM where you see if the structure is printed or not. We really want to know if this nanostructure is also inside. So that was very crucial, the collaboration with our colleagues, where we literally slice our micrometric printed ducts to see inside. And here are the result of 2 cases where one polymer is roughly 50-50 into the lamellar and the other in the cylinders. So you see the array of ducts. I think you can even see the silhouette that we have a slide, and then you see that this self-assembly or this nanomorphology is really inside the printed. Okay, so now we have shown the nanostructure. We are also now working on other type of polymers and biopolymers. Let's go 1 level down. Macromolecules, again, we think of natural polymers, DNA, proteins. They are sequence defined. And in our case, we were at the moment always relying on this radical polymerization of acrylates. So that was the work of Samantha. The question is, does the monomer sequence have an impact on printability? So we started with a simple exercise, 3 oligomers of 8 units. So 4 units are just an alkyl chains, as you will see later, non-functional, and 4 units are printable. Then we prepare 1 alternating, 1 in a what we call block, and 1 3 block that it has the photopolymerizable part on the side, and the non-functional in the middle. Here is the synthesis. I won't go into the details. It's like solid state synthesis where you just add the chain extender. In our case, the photocross-linkable group was, of course, protected at the beginning. And when we end up with the 3, that you cannot distinguish neither by NMR or mass. They are identical, but now we are also sure that each molecule has exactly these 4 acrylates. So now, that has an influence in printability, and the question is yes. So let me guide you through the slide. So what you see here is what we call a dose test. We use the buckyball as a benchmark 3D structure, and we print the buckyball with different conditions, different laser powers, different scanning speed. And you see that in what we call alternating, we have a larger regime. And in the 3 block, it started a bit later, and also in the block. So that gives you the information that the printable regime is way larger. Also, or Samantha actually made a great job in exploring all the conversion of the acrylate, the mechanical conditions, and at the end also used the 3 of them for printing. And we also saw that the one with this alternating structure is the most suitable one, also having higher resolution. I think I don't need to tell you where it's coming from with these structures. And now I would like to change a bit the topic, but use the last minute to talk about sustainability. So at the moment, we have invested a lot of time and efforts on incorporating functionality, but long term, if we want to use 3D printing in real life application, we also need to take care of sustainability. And first steps in these directions were done. We started with a macro scale formulation, and very often you just order your monomer from Sigma Aldrich, or then you made some synthesis in the lab. And here we changed a bit. So Clara went to the supermarket, went to Rebe, and bought all the possible vegetable oils commercially. And then we tried to use them as a feedstock for the formulation. Unfortunately, you cannot print them directly, so they have double bonds, but it's not active enough. But then she functionalized the double bonds with acrylate in a solvent-free way, so as green as possible. And then adding a bit of photoinitiator, we could really print macroscopic structures in high resolution. We really check them in terms of resolution, mechanical properties, and compare with a commercial one that you can see. And we selected actually sunflower and canola oil in terms of price and performance. Of course, price changed a bit since 21, but still that's a valid statement. And as you can see, we can print nice structures just starting from vegetable oils. So I don't want to claim that this is the solution. We don't want to compete with food, of course. There are already some publications. For example, one group in the US reported the use of vegetable oils, that they were just the residue of literally McDonald's frying, and they work for printing. So one can think also on using the residues, but we went also a bit further thinking on alternatives. And Clara is coming from the Canary Island, and then we had some contacts there in the algae bank. And actually, microalgae are a nicer alternative in terms of sustainability. They have a lot of triglycerides accumulated in comparison what you get from the crops. And we selected 2 very promising strains that allow us to extract triglyceride that we can again functionalize and use them for printing. And here we had really a nice surprise. When we extract this triglyceride, we extract also the chlorophyll derivative from the algae. And then we got a very green ink that at the beginning was a bit suspicious, like, yeah, that's too dark. But then at the end, turned out that we can use the chlorophyll also from the algae as a photosensitizer. So that's even more sustainable because we don't need additives, we don't need photoinitiator, which very often is the component that is toxic for cells. So we could prove nice biocompatibility also of the material, and we have printed also some scaffolds. And then I would like to show you the very, very last example where we are trying. Of course, now we start with something bio-based, we print, but what about the end of life? Ideally, we should be able to recover the material, so still is not the perfect system, but here is based on lactate esters, and with this process, doing some aminolysis, we can recover the cross-linker and reuse. So you see that after a couple iterations, resolution is very good. Also, it's always a struggle to print very nicely the Heidelberg logo, but there we almost get it perfect. And with that, I hope that I could show you a bit broad overview what we are doing in the group. I would like to thank again for the invitation. A big thank you go, of course, to the wonderful team, the funding, and all of you for your kind attention. Thank you.
Thank you, Eva. I think we have time for 1 or 2 questions. Okay.
So concerning the sustainability, you most work on ink side, right? I wonder how is the development of the technological development concerning printing device, concerning the cost of the power or probably time efficiency, such kind of thing.
Yeah, exactly. That's a very good question. Of course, sustainability, it has many dimensions. We have focused on trying to, I wouldn't say solve, but contribute to the problem on the material side. But of course, there is many things in the technological part. The good news is that all this printing, and we will hear also in the afternoon Stefan heads. So this is becoming, with all this volumetric and all these new processes, faster, more scalable. So there is a lot happening in this regard. I haven't mentioned it, but what we are also trying is not only optimize the synthesis and the process, also one thing that you use a lot of solvent is in the development. So for example, the one with the vegetable oils, we don't use any organic solvent at all. You can just develop with water and soap, as you do at home, which also contributes to less organic solvent. But yeah, you are right. The materials is one part of the big picture.
Is there any other questions? I think we have time for one quick one. If not, let's thank Eva one more time. Thanks. Next up, we have the talk of Professor Zhiyong Tang. Professor Tang is a professor and director at the National Center for Nanoscience and Technology in Beijing, China. He received his PhD at Changchun Institute in Applied Chemistry. His research interests are centered on the fabrication and application of functional inorganic nanomaterials. Unfortunately, Professor Tang was unable to join us in person, but he did provide us a recording of his talk, so we can all enjoy that. So with that, let's please start the recording.
First of all, I must apologize for my absence in this symposium due to the delay in my visa applications. I also want to congratulate the milestone in the Chinese advanced portfolio, including the 10th anniversary of advanced science, the 10th anniversary of advanced materials interfaces, and 25th anniversary of advanced engineering materials. Today, the topic of my talk is biomimic chirophotonic crystal. My name is Zhiyong Tang. I'm from the National Center for Nanoscience and Technology, China. It is known from the very small scale, like the electric spin around the nucleus, also to the small organic molecules, to DNA double strands, to the artificial screen, even to the large scale, like galaxy. So chirinity is universal at all scale, except for the convention chiral organics, systems. Recently, scientists pay a lot of attention on the chiral inorganic nanoparticle systems because they show very exceptional optical properties. We also call as optical activities. Such chiral inorganic nanoparticles, including Up conversion, rare earth nanoparticle, semiconductor nanoparticle, plasmonic low metal nanoparticles, perovskite, the twisted graphene structures, or even the metal oxide. About 2 years ago, our group summarized the recent progresses on inorganic chiral assemblies. We found the higher similarity with the traditional chiral organic system. For instance, if we select different types of inorganic nanoparticle as a building block and construct the T2 structures, actually this structures is very similar to the chiral organic molecules. We also can fabricate the twisted and the helix structures, use inorganic nanoparticle as a building block. All these structures also are very similar to those of conjugate molecules or even DNA structures. Furthermore, we also can fabricate the more complex inorganic chiral assembly, which structures is similar to that of chiral liquid crystal. Talk about the optical property, actually, with the long-term evolution, a lot of biologic systems have developed the effective method to manipulate their light properties, including scattering, reflection, and interference. So that is why our world is so colorful. So, for instance, some beetle shells, like the rim and the long force, actually they shows the bright colors. If we check the shell structures, we found the three-dimensional orderly arrangement, either the pearls or the nanospheres. So we call as a three-dimensional photonic crystal. We also can use the man-made nanosphere as a building block and fabricate the artificial photonic crystal structures. For instance, if we select a different size nanosphere, maybe the size from several hundred nanometers in the range, and then we can fabricate the three-dimensional orderly structures. And furthermore, if we change the size, actually we can tune the photonic band, and we can obtain the different structural colors. And what is our idea? We think if we filter the chiral mediate in this three-dimensional photonic crystal, we may see the strong coupling between the chiral mediate and the photonic band. So following this idea, we use the silicon nanosphere as a building block and sever them into the three-dimensional orderly structures. Then we filter the chiral polymer precursors into this three-dimensional photonic crystal. After polymerizations, we use HF to etch the silica template, and we obtain this three-dimensional orderly hollow structures we call as the chiral inverse opals. From SEM image, we found when we change the size of the silica nanospheres, actually we obtained the different diameter of the nano cavity inside of inverse opals. We studied the optical properties of this chiral inverse opals. Actually, we found two very strong absorption. One adsorbance is below 400 nanometers, and this one belongs to chiral polymer matrix. So we also found a new and a clear CD response above 400 nanometers. We found that this wavelength actually is well matched that of photonic band. Moreover, when we increase the size of silicon nanospheres, actually we found that the CD response peak will get the red shift. To further confirm the CD response and the absorbance above 400 nanometer, whether they come from the photonic bands. So we immerse the opals into ethylene glycol solvent. The reason why we select ethylene glycol solvent because its refractive index is very close to that of chiral polymer matrix. As a result, we found that after we immerse the opals in the ethylene glycol solvent, the CD response and the optical absorbance above 400 nanometer are totally disappeared. We also use the non-chiral polymer as a matrix to fabricate the opal structures. We can see in the range of 300 to 600 nanometers, we still found a very strong adsorbance from the photonic band. However, we didn't see any CD response in this region. In other words, we are make sure the CD response about 400 nanometers comes from the strong coupling between the chiral polymer matrix and the photonic band. We also use a console simulation to understand the origin of this CD response. From fig B and fig C, we can see for right-handed secular polarized light, RCP light, is more focused or more concentrated in the polymer matrix, as shown in the triangle part. However, for the LCP, the left-handed secular polarized light, it is concentrated in the elbow. In other words, the band gap for RCP and LCP lights are separated. This is the reason we can clearly see the CD response about 400 nanometers. In addition to three-dimensional chiral photonic crystal, there is a lot of one-dimensional chiral photonic crystal in nature. One example is a specific type of the beetles we call as the scrap. So we can see the shell of the scrap can selectively reflect the secular polarized light, as shown in figure A and B. With the help of the right-handed secular polarizers, actually we see the bright yellow color. With the help of the left-handed secular polarizer, we only see the dark or the green in colors. So this result shows for these beetle shells can selectively reflect the right-handed secular polarized light. The reason is the special structures in the shell. As seen in figure C, actually this shell formed the periodic arrangement along these perpendicular directions. In detail, in the body, the cellulose malrod firstly align to form the one layer. So for the secondary layer, actually to rotate to a certain angle. As a result, they form this helix arrangement. Furthermore, from the Bragg diffraction equation, we can see the refractive color is determined by the periodicity or also the pitch length. As we see here, when we increase the pitch length, actually the reflected color should get redshift. Encouraged by the structure of the beta shells, so we use the Langmuir-Sheffer method to biomimic one-dimensional chiral-photonic crystal structures. So we use the molybdenum nickel calcium oxide ultra-thin nanowire as a building block. The diameter of these ultra-thin nanowires is less than 1 nanometer. Then we disperse these nanowires at the interface of air and the water. Then we use the horizontal bars to compress this ultra-thin nanowire to force them alignment to form the one layer. So then we deposit ultra-thin nanowire layers onto the substrate such as glass, silica, or also quartz. So before the second layer deposition, we rotate this substrate at a certain angle. Finally, we can fabricate these helix arrangement structures. So as shown in the AFM image, actually in the layer, such ultra-thin nanowire are well aligned. The thickness of one layer is about 21 nanometers. Furthermore, by changing the rotation angle, actually we can obtain the 7 examples of the different periodicity, means the different pitch lengths. We also found for these 7 examples, they show distinct optical properties. For example, with the help of left-handed circular polarizer, actually we see the reflective color from the purple ones to the red ones. They cover the whole range of the visible light. On the other hand, with the help of the right-handed circular polarizers, we found that all these 7 examples only shows the gray colors, the same color. We also use reflection spectroscopy to study the optical property. We found that for these 7 examples, they shows a very sharp reflection peak. Moreover, with the increased periodicity or increased pitch length, actually this reflection peak get the redshift. The similar phenomena can be observed in the CD spectroscopy. Important things we wanted to point out is this CD response is quite strong. So the optic anisotropy, also called as the G-facts, can get to 1.5. For the ideal chiral photonic crystal, the largest G-factor is 2. So 1.5 is very close to the maximum value of the ideal chiral photonic crystal. We also found such one-dimensional chiral photonic crystal are very stable. After the placing in L for 1 month, actually the CD response shows no any change. Such excellent stability comes from the robustness of inorganic ultra-thin nanowires. Except for molybdenum nickel tetroxide, we could use other inorganic materials like gadolinium oxide, hydroxide nanowires as a building block. When we use the gadolinium oxide, hydroxide nanowire as a building block, actually we can decrease the layer thickness from 20 nanometers to 15 nanometers. As a result, we can switch the CD response from the visible region to the UV region. This result also shows the generality of this method. We can summarize the advantage of our CD response of one-dimensional chiral photonic crystal, including such as the CD spectroscopy can be both negative and positive. These are different with the convention UV visible absorption or photoluminescence spectroscopy. They also shows the relatively lower peaks, the ultra broad wavelength ranges, and the independence between the adjacent peaks. So this advantage encourages us to use them in the CD buckles. So we fabricate one samples. They contain it contains 6 peak positions as shown here, and 10 peak intensity, including 5 positive ones and 5 negative ones. And this sample easily afford a coding capacity of 1 million. Beside the CD absorption, we also obtained the chiral photoluminescence from the chiral photonic crystal. So we fabricate one sample that is the quantum dots of the chiral photoluminescence crystal. The preparation method is quite simple. Firstly, we mix the cadmium cyanide quantum dots and molybdenum nickel tetroxide ultrasonic nanowire together, and we disperse this mixed solution at the interface of air and water. Then we follow the Langmuir-Sheffield method and fabricate this chiral photonic crystal. The result shows this sample has very strong CD absorbance, also has rather, maybe it's not so strong, but it's still very clear chiral photoluminescence response. Moreover, from this picture, we can see both the sign, positive and negative, the position from 400 nanometer to 700 nanometer, and also the intensity of the CPL peak can be precisely controlled by rotation mallet, interlayer angles, and the layer numbers. We also found the relative position between the photonic bandgap of chiral photonic crystal and the luminescence of quantum dots plays a crucial role in the final CPL response. We can get the different shapes of the CD response. We did a theoretical calculation. The result tells us the unique optical activities of inorganic chiral photonic crystal doped by quantum dots originates from the peculiar reflective characters near the photonic bandgap. As shown in this quantum dots doped one-dimensional chiral photonic crystal structures, we found the optic anisotropy. Also, the G-factor is quite small. So how we can further improve the CPL response? So we learn from the traditional polarized method. We developed a two-layer construction method. So we use combine 2 layers. One layer is the polarized fluorescence layers, and the other one is the quarter-wave plate layers. So the linear polarized luminescence from the polarized fluorescence layers is easily transformed into the circular polarized luminescence by using the quarter-wave plate layers. Also, compared with the traditional polarized method, our inorganic assembly method can largely prevent the giant optical loss, because we can combine the light source and the linear polarized into these layers. We call them directly polarized emission. So as for the first layer, to construct the polarized fluorescence layer, we mixed the quantum nanorods and the ultra-thin nanowire together and disperse on the interface of air and water and compress it, and then we get the multiple transformation, multiple transfer. Then we get this as we showing fig C and fig D. This polarized fluorescence layer can emit the higher quality linear polarized light. As for the second layer, to construct the biorefringent layers, we still use the Langmuir shifted method, but the building block, we rather than use the mixture, we use the pure ultra-thin nanowire of molybdenum nickel tetroxide and get the multi-layer structures. For these multi-layer structures, we can find this as shown in fig C. This phase retardations can be tuned by changing the numbers of the layers. So then we combine these two layers together, we obtain both the high symmetry factor and the high luminescent cornea as shown in fig C, actually comparing with the very weak CPL from the common dots of the chiral photonic crystal. Here, these two layer structures increase the CPL intensity from 20 to more than 1,500 milli-degrees. Moreover, we use a figure of merit to evaluate the strength of the CPL response. And this figure of merit is the product of defect and cornea. We can get up to 0.2. It's much higher than previously reported result. Then we did a theoretical calculation by use Jones matrix and Jones vectors. Our result also tell us at the positive 45 degree and the negative 45 degree angles, the left-handed and right-handed circular polarized luminescence are obtained. This result well match the experiment result. We can also integrate the three types of quantum rods, the blue emitting, the yellow emitting, and the red emitting quantum rods in the same layers. Finally, for the first time, we observed the so-called circularly polarized white luminescence with visible difference. We appreciate this work is also by highlight by advanced science news. Why we want improve or why we want to obtain the giant CPL response? Because we want construct the CPL based three-dimensional display devices. As we know, the space that we live in is three-dimensional, and due to the parallax displacement, the two images seen by the eyes are superimposed in the brains to create a three-dimensional space. So the traditional polarized three-dimensional display technique is realized by linear polarized multiplexes. They have a lot of intrinsic disadvantage. As we go to the cinema, we watch the movie. So every people maybe feel these drawbacks. For instance, the narrow film under the poor contrast and the brightness lost and colorful offset, the CPL-based 3D displays technique can perfectly overcome these disadvantages. So we try to use the Langmuir shifted method to construct the circular polarized light emitting diodes. This is the structures as we construct the device as we construct it. So we also studied the electric luminescence property of this device. as shown in Fig C, driven by electricity, we obtained very strong electroluminescence, both in the blue, green, and red regions. The EQE values of these three devices can get up to around 10%. We also check the circular polarized electroluminescence property of these devices, as shown in Figure A and Figure B. We can see, driven by the electricity, these three devices actually emit a very strong CPL response. And as shown in Figure B, the effect of this CPL response can get up to 1.5, very close to the ideal value of 2. So as a result, comparing with previously reported value, so our examples, including the blue star, green star, and red star examples, is much better. And for so-called figure of merit is 1 or 2 magnitude higher than the previously reported values, because the greatly improved performance actually with the help of circular polarizers, we can clearly see the difference in the left-handed and right-handed CPL response. This result also encourage us to fabricate the 3D displays areas, and for this reasons we design some program to realize the electric-driven different patterns, as shown in Fig C with the help of RCP glasses and LCP glasses. We can clearly distinguish both the left-handed and right-handed CPL response. For instance, with the RCP glasses, the first rows get shining, and with the help of the RCP glasses, we found the second rows get shining. So when this 2 shining CPL light goes into our eyes, actually we can obtain the 3D dimensional image. Moreover, driven by the electricity, programmed electricity, actually we can get the different patterns. So we can get the different image. A large, big advantage of the CP LED is the anti-glare effect. The glare effect is very common in our daily life. For instance, if we use our mobile phone and the strong sunshine, actually we cannot clearly see the image on the screen, because the strong sunshine will get a reflection on the screen. As here shows, if we use the normal, like a linear polarized light, we can see this strong glare effect. However, with the CP LED, and this is totally shows very good anti-glare effect, we can clearly see the patterns from the strong CPL response. Finally, we draw conclusion. We got the tunable circular polarized luminescence from the cathode crystal. More importantly, recently we realized the 3-dimensional displays of electricity circular polarized light emitting the diodes areas. I also want to thank you for your attention. Thank you.
Thank you, Professor Tang, for that great talk. With that, we end the first half of our summit, as it's going by so quickly. We're going to take a quick lunch break, and I ask everyone to please come back, be in their seats by 2:10, because we will start the next session at 2:15 promptly. The next speakers, if you could come a little bit earlier, that would be great. And so everyone here in attendance, there's lunch provided out in the lobby, and enjoy.
So welcome back, everyone. Thanks for coming so promptly here. I get to introduce our very own José Oliveira. He is going to give a talk on an exclusive preview, what is next for the advanced portfolio. José has been with Wiley for over 20 years. He got his PhD in organic chemistry in South Africa, did then a postdoc in mass spectrometry in Belgium, and then he actually escaped the lab to work with us, with Wiley. He started off as an editor in Angewandte Chemie, and then he was at Chemistry and Asian Journal, and then he moved towards the material science team, where he was an editor for Small. He spent 5 years in China, where he actually built up the editorial team, and then he returned to Germany to lead our materials and science and physics teams, and then he landed his current role as the senior director for our physical sciences program.
Thanks, Ulrike. Alrighty, so just tech check. Can everyone hear me? Perfect. So firstly, thanks, Ulrike, for that kind introduction. And you're right, I could not wait to escape the lab. But at the same time, I'm still doing something I love, and that's talking science, talking about science, communicating science, and I'm with the perfect audience here to do that. We, of course, here this event mostly to celebrate 3 very special anniversaries. So you've got the journal names up here, and of course I'm going to call out the main current architects behind them. So for Advanced Materials Interfaces, it's Jolke. For our, almost the grandfather in this setup, Advanced Engineering Materials, but by the very young Sandra Calvaram. And then the editor-in-chief of our magnificent Advanced Science, our equally magnificent Kirsten Severing. But of course, there is a strong team behind these 3 leaders, and I'd like to thank all the editors that have contributed to the success of these journals, but especially to the community behind us. We are basically the voice, and we interact with the community who has been the real success behind the journals, contributing the work as authors, as editorial board members, advising us about the direction of the journals and the science. As our referees, you do tremendously valuable work for us and the community, and everyone in this room and online are tremendously important for the success of these journals. So please give yourselves a round of applause. So, of course, we're celebrating these anniversaries, but there's a lot more to celebrate. So I think this was prepared for me. I said, wow, this looks like a game of advanced chess. So for marketing editors, I think there's something in there. But this is a tremendously successful portfolio. The high-impact journals disseminate the best science from well-established as well as from emerging researchers. And as we celebrate these milestones, we're also excited to build on the strong foundation that we have. We've got the physical sciences community behind this portfolio, but of course we now have much grander plans for the journals, and we are going to take a big step further into the life and health sciences. And so for the people online and for the people here, we have a sort of very exclusive special preview. It's almost like being at the Cannes Film Festival. And we're just going to have a very quick preview of a video that kind of gives us an idea of the direction that we want to go in. And I need to press that twice.
You know, when people get together, new ideas emerge and new opportunities and new research frontiers develop.
Advanced journals embrace exclusivity, diversity, and inclusion. Who you are does not matter. It's the science that matters.
Advanced Science is a selective journal. We are only looking for the best research. I think where we differ is that we're focused on the science. We want to take away as much of the other aspects of getting published from the research as possible, those things that researchers find really frustrating.
You think of science as being sort of this abstract, non-personal thing, but in fact, it really is about people.
Publishing in advanced journals has been a big part of recognizing my work, and also it helps me reach out to a global audience. We can build up the international collaborations after the publication.
It's highly cited and it's well known. It's been around for a long time. We also want to find a journal that brings together chemistry, biology, engineering, and merges the physical sciences with the life sciences.
Over the last 10 years, advanced science has been building a toolbox of technologies that are now poised to help us understand life sciences and health sciences more effectively. What's super exciting about this new initiative is that we're hoping to expand that community, bring in new players. And I think this sort of cross-disciplinary exposure is going to liberate a lot of new science. When you have people in relationships and non-transactional, magic happens. I mean, people will continue to build new research protocols that are interdisciplinary, and working together is just a fun process. It's a creative process, and being part of that is super cool.
Super cool indeed. The people who produce this, so Alexis and Alison, are in the audience. So if anyone here is looking for a break into Hollywood, you can speak to our colleagues about that later. But on a more serious note, advanced science is going to act as our doorway into this expansion. It is already a very multidisciplinary journal, publishing highly interdisciplinary, really cross-subject research, has a very selective, rigorous, but fair publication process, something that we want to maintain to ensure that we are always presenting top quality science. And this is really a global platform for collaboration in the scientific community, and this is something that we want to continue to take forward. So advanced science is very well known in the physical sciences community, so there's no one in this audience that is not familiar with the advanced brand. But for researchers in some of the life science and health sciences community, it's only now starting to take hold. There's a German expression that I'm going to come back to, Zukunft braucht Herkunft, and there's no direct English translation for it, but basically what it means is that if we want a great future, we need to have a strong, solid foundation. And these journals are indeed that strong foundation for our future plans. And so although advanced science is already publishing work in these fields, the brand itself is really going to take a bigger look and a greater acceptance and greater penetration into these subject areas. So as you saw in the film, neuroscience, oncology, plant science, food science, cell and molecular biology are sort of the first areas that we're going to go in with a more dedicated focus. Of course, we have several exciting initiatives underway, but part of this exercise and why we have people here and online is we hope that and encourage you to share with your fellow researchers the news and the fact that we are expanding into these areas and that there's greater opportunities for collaboration between subject areas and your researchers in those areas. It's not all about expanding into life and health sciences either, so I'm very excited to announce the launch of 2 new journals that are going to be open for submissions quite soon. So you can see the covers there, Advanced Robotics Research, Advanced Intelligent Discovery, and we already saw some great presentations. Martin, hopefully some of that work is going to be featured in our very first issue of Advanced Robotics Research, but tremendous opportunities and great journals that are being planned, as well as a advanced synthesis and catalysis that is going to be brought into this family of journals as well. So our expanded portfolio presence is officially going to launch October 1st, so there will be a new look and feel to our website and to some of our branding. We're previewing this today, so a special release with this audience. You know, share the news, please contribute, and please be aware of the new journals that are being launched. But really, the goal today is, and I can't stress this enough, it's to celebrate, but also to thank you for your continued work, your continued dedication to our journals. Without your support, without the tremendous work that you're doing in the labs, we wouldn't be as successful as we are. So again, thank you very much. Yeah.
Thank you very much. And with that, I get to introduce our first speaker, second speaker, first scientist, Professor Paolo Samori. He gives the talk on engineering all interfaces and 2D materials and devices. Professor Paolo Samori is a distinguished professor at the Université de Strasbourg, an emeritus director of the, bear with me, Institut de Sciences d'Ingénierie Supramoléculaire, my French is very bad, and director of the Nanochemistry Laboratory. He's a member of the Executive Advisory Board of the Advanced Materials and Advanced Sensor Research, and a member of the editorial advisory boards of Small Chem, Nanomet, Chem Plus Chem, and SmartMet. He has published over 450 papers in the fields of nanochemistry, supramolecular science, materials chemistry, and with a specific focus on graphene and other 2D materials, as well as functional, organic, polymeric, and hybrid nanomaterials for the application in optoelectronics, energy, and sensing. Thank you very much for being here today, and we're really very much looking forward for your talk.
Thank you very, very much for the kind introduction, and also it's a great honor to be here back in Mannheim. So thanks for the invitation, and happy birthday to the Advanced Journal, and looking forward for these 2 new ones. Now, what I'm going to do today, I'm going to share with you some of the results that we obtained in Strasbourg, in my group, and we are chemists, but we try to play interdisciplinary, and so we try to work at interfaces between materials and between devices. And yes, so essentially I focus on 2-dimensional materials, which beyond graphene, there are quite a number that have been already exfoliated. Quite a number doesn't mean much. Well, they have different colors, they look very nice. They share some properties like the atomic thickness, the flat surface, the large surface to volume ratio, the outstanding physical and chemical properties. And actually what is most important, that these properties are highly susceptible to the interaction with the environment. Now, theoreticians are always very optimistic. They claim that one can potentially exfoliate 3,000 different layered material. Experimentally, we reach 100 more or less, and so there is still 2,900 to prove. And that actually is the reason why European community has put quite some money on exfoliating and producing two-dimensional materials, the one that they call the two-dimensional materials of tomorrow. Now, if I want to be provocative, in my opinion, two-dimensional materials, they have outstanding properties, but these properties are hardly tunable. And that is where actually the molecular science comes into the game as a manner to tune and improve the physical properties of two-dimensional materials and also to impart new property to these materials. And so this is a way to go towards multifunctionality. And it's more or less what I'm going to show you today. Now, the interaction between these two different, let's say, materials, so the two-dimensional materials and molecular materials, can be done using different types of forces that are pretty well known. So from the weak force that are the van der Waals interaction to the other extreme is a very strong force that are covalent forces. Let's say the one from the center to the left can be used to create mostly continuous film to cover the surface of two-dimensional materials. The one from the center to the right are more to tether isolated molecules. And I will show you an example of all of them. Now, but all these kind of approaches, they work more or less in the same manner, that you need to have these 2D nanosheets somehow that can be already physisorb on the basal plane of a surface or can be existing in a dispersion. Then you have this interacting with specific molecules that have to be designed. The molecule is represented by a triangle that is anchoring group that preferentially interact with either the basal plane or the edges of the two-dimensional materials. And then there will be a kind of red dot that is a new function that is imparted to the two-dimensional materials. So you create this kind of airy disks, and then this airy disk, if this is done in solution, they can assemble forming this kind of porous structure. And then depending on the type of application you have in mind, you choose a red dot. So you choose the kind of functional unit they want to impart. For example, application can be thought to be in electronics, in responsive coating, in sensing, and so on and so forth. Now, in this framework, actually, I will use let's say, the example of the prototypical electronic device that's the field effect transistor as a kind of guideline to go through our results. And in particular, you have very fundamental properties in a field effect transistor that you have to control and optimize. That are the charge injection between a metallic electrode and a semiconductor. So actually here you don't see very well, but on the monitor and the 1,500 people that are on the web, they can see better than you. So there is this kind of two-dimensional materials here. So charge injection and charge extraction in red. There is the charge transport through the two-dimensional materials and the rate modulation from the dielectric into the semiconductor. Now, let's try to analyze one by one these kind of properties at the interfaces. And so we start with the charge transport. And so actually, this discussion starts from a very simple concept that forget about having perfect crystals. Two-dimensional materials, and now I'm going to talk in particular about transition metal dicalcogenides, they are defective rich. So the best thing you can do is to try to bring to your advantage the defects that you have. In other words, if you have the most perfect, also the less defective rich kind of two-dimensional materials can be the CVD or Scotch tape, every 10 by 10 nanometer, you will have a defect, okay? So you cannot get out of this kind of trap. So you have to bring to your advantage. This is what we started doing together with Simone Bertolazzi when he was a postdoc in my group. He came with a PhD in device physics from EPFL. And so the idea of his postdoc project was one of making a transistor based on two-dimensional molybdenum disulfide CVD flakes. And actually, the idea is that we wanted to increase the number of defects because the more defects you have, the more reactive it will be your surface to any kind of functionalization. So we have bombarded with ion beam, argon beam of the XPS, the surface of molybdenum disulfide. Of course, the more you do that, the more you lose the interesting optoelectronic properties of two-dimensional materials. You can see how the current with increasing number of point defect, they decrease, or you can look this in terms of field effect mobility as a function of the increasing, let's say, sulfur vacancies that decrease exponentially. But as I said, you increase more and more the number of reactive sites, and these reactive sites that are missing sulfur in the lattice, they can easily be healed or replaced with a thiolated molecule. So of course, this opened the door to the use of all the thiolated molecules that have been developed to interact with gold. And in the Aldrich catalog, you can find a couple of thousand. And so in other words, you can, let's say, fill this vacancy with the thiolated molecule. In this case, we did it with butanediol, and recover to a great extent the electrical characteristic of the pristine material. So that, of course, is something that you can use given the high sensitivity of the two-dimensional material. You can use it for doing sensing. For example, we used this recently by Anne Bean in order to discriminate isomers. That, of course, isomers are quite complicated to be discriminated using chemistry analytical techniques because of their similar properties. What we did here, we focused on a thiolated benzene, which has two fluorine atoms that are either pointing towards the thiol unit or opposite direction. And in this way, we could, while we fill the sulfur vacancies on the lattice of the molybdenum disulfide, we can actually have a dipole moment that is either pointing out of the surface or into the surface, depending on the orientation of the fluorine atoms. And in the first case, we have a very strong N-doping effect. And on the right case, in the second case, we have a very strong p-doping effect, which you can read by Raman, you can read by XPS, you can read this electrically. And so, for example, you can see that with the 3,5 derivatives, you are lowering the electrical characteristic of the device. This is what you can see here in the IV characteristic. This is a pristine in black. And the 3,5, you have lower electrical performance, whereas you have much better electrical performance in blue when you have functionalized with the 2,6 derivatives of our isomer. So I think this is quite interesting because it opens the door really to isomer discrimination, also of more complicated molecule with a thiol unit, using the surface of the two-dimensional materials. Now, you can also, I presented you before how you can use a molecule with a single anchoring group, but you can also use molecule with two anchoring groups, so bidentate molecule. Here, the anchoring groups are in green, still the triangle. And again, the game is the same. You have the red dots, that is the function you want to impart. In this way, what you create is a network of two-dimensional materials. And now, of course, creating a network means also that you might have a price to pay in terms of processability and solubility. Now, but you have something much more robust. And so depending, again, on the red dot, you can have some function that allows to host ions that can be interesting for energy application, like supercaps or batteries. You can have groups that are interesting for electronic or electrical application. You can use this for application in catalysis or in desalination and sensing. So you just have to decide which kind of functional group you want to embed there. And now this activity started actually in collaboration with Johnny Coleman in Dublin. And the first series of works in this direction was done by Stefano Ippolito when he was doing the PhD in my group. And the idea was pretty simple, that let's say when you exfoliate in liquid phase two-dimensional materials, you have this kind of isolated nanosheets that you can disperse on a surface and are like pieces of the puzzle that are dispersed and they don't electronically crosstalk one another. And so the idea that I proposed to Johnny was to combine this with the complementary piece of the puzzle in order to make a network. So actually here, unfortunately, you don't see the colors. If you look more chemically, we have done this kind of work using, let's say, molybdenum disulfide, tungsten disulfide, rhenium disulfide, and combine this with a very simple molecule that is benzene dithiol. Now, the benzene dithiol has a dual effect. On the one hand, it bridges adjacent flakes, and on the other hand, it heals the sulfur vacancies. Okay, so that, of course, it allows to create percolation pathways for charges to go from one to the next flakes. Now, the way we prepare these kind of films was very simple. Now, I use the term film when the flakes are isolated or not connected, and the term network when they are connected through the covalent bridging with the benzene dithiol. So anyway, we started with the ink coming from Johnny, and then a pre-patterned gold electrodes on silicon dioxide. We deposit the material making films, and then we put this in control atmosphere, and we have in this way applied drops of benzene dithiol in order to link adjacent flakes. And now this is kind of the cartoon of what we obtain. We have the sulfur vacancy. The true story is that most of the defects in liquid phase exfoliated flakes are at the edges more than on the basal plane. And so you connect covalently adjacent flakes, and so charges, and they can flow from one to the next flake. And I have no time to show you all the characterization. I would like to show you only the electrical characterization that we use. We fabricated transistor, liquid gated transistor, and we decided to use this kind of device geometry because we have the electric liquid that penetrates the free volume of the semiconducting film. So we can use volumetric gating, in particular because it's a very thick film, it's about 600 nanometers thick. To make the long story short, upon network formation, we can increase the mobility of tenfold, the ion-off ratio of tenfold. We are not doping the film because the threshold voltage remains the same. And the device switches 10 times faster. Now, what's next? What's next actually in this kind of race of going from 2D to 3D? You can, of course, diversify in terms of the two-dimensional materials you want to use, but you can also use a different bridge. I mean, nature is always a source of inspiration. You look around, you have beautiful bridges that can be more and more functional. And so now, if you look at this from a more chemistry perspective, what we thought in a work that we published last year in Small was to use this kind of approach for sensing heavy metal. And so we took the very same molybdenum disulfide flakes, and then we combined this with a very well-known kind of chemistry to have selective, let's say, receptor for heavy metal for divalent ions. So we use the terpyridine. So we start combining this with the preformed complex of terpy, a zinc complex of terpy. And then, of course, one of the tile, this should be a rigid molecule, one of the tile connects to the first flake. The second tile connects to the second flakes. I will show you how we construct stepwise using a microfluidic approach, this kind of network. And therefore, we arrive to something like this. And then we have to protonate to get rid of to empty the cavity, which now becomes empty and ready to host any other type of ions. I don't want to lose much time. This is a microfluidic chamber. So it's a small chamber of about 2 by 2 centimeters square. And the idea, unfortunately, here you don't see much because of the screen, but we have what is missing between the inlet and outlet is a microfluidic chamber. And then so we insert two different components stepwise, that is molybdenum disulfide and the terpy dithiol. After each injection of low concentration, we also inject the pure solvent to get rid of anything that is not chemically strongly absorbed. And so you see, first injection, just a few flakes of molybdenum disulfide. Then the next injection, we kind of put the hairs around the molybdenum disulfide. Another injection, we bridge with new molybdenum disulfide, and stepwise we grow the network. After each injection, we have actually 2 electrodes, one here and one here, and we measure the current when we have the electrons that can flow from the source to the drain. That means that the device is constructed, and then we can start using this for sensing. And more or less, this is something that we can do with a 70% of coverage. And now, without entering inside detail, this allows us to minimize the thickness of the film compared to spray-coated or spin-cast film, and actually allows also to deposit multi-components. For the application in sensing, we have a for cobalt 2+, we have a very high sensitivity that is on the picomolar regime, that is below the limit of detection imposed by the European community. And we also have very high selectivity. Actually, the only other divalent ion that is a bit in competition is iron 2, but we don't care because in air it oxidizes as iron 3. So that gets out of the race. So selectivity is reached. Now, we can insert in the microfluidic chamber multiple components, which means also multiple two-dimensional materials. I thought it was a way to create lateral heterostructures. Of course, heterostructures is an approach that allows to diversify, let's say, the composition and to boost the functional complexity. But this is typically done using very sophisticated and expensive slow tools like CVD type of approach. And the idea that we developed with Antonio was pretty simple, that indeed in the microfluidic chamber we insert stepwise a P-type, then the benzene dithiol, then the N-type, then the benzene dithiol in a cycled manner, and again with the 2 electrodes that allows us to stop when the circuit is closed. And then at this point we can do a lot of light matter interaction studies about this kind of heterostructure. So the message here is there is a way to fabricate lateral heterostructure also from solution processed films in this stepwise type of growth. Now let's go to another property, the charge injection and charge extraction. And now this has to be optimized in any kind of electronic device. And typically what people have been doing, again, if you consider the field effect transistor, you take a metallic electrode. So you take this device in a bottom gate and bottom contact configuration, and you functionalize the metallic, typically gold electrodes with thiolated molecule in order to optimize the work function of the electrode. But this, of course, is not the best type of configuration, because the area of injection of charges in a bottom contact is not maximized. And so everyone would love to have the top electrodes functionalized, but this has not been proven yet, except 2 years ago in this paper that we published in Advanced Materials was a work by Bin Han again. And the idea was pretty simple, that he evaporate with the mask some gold pads. He chemisorb on the top 2 different types of thiolated molecule, one that is fluorine atom rich, that allows to lower the work, to higher the work function of the gold, and the other, the amino functionalized, that allows to lower it. Essentially, you can see we can higher of 0.7 eV or lower of 0.7 eV, more or less, the work function of gold. And so at that point we can, and then he is taking this kind of pad that are coated with the self-assembled monolayer, and one by one, by hand, he put upside down very gently on the basal plane of the molybdenum disulfide. Now, this is something that he can reproduce in thousands of measurements with a precision such that is reproducibly, he can put electrodes at 90 nanometer one another. In this way, we can optimize the injection and extraction of charges such that when we use the case of the amino functionalized molecule, we have a mobility that is about 30, which is doubles of the one of the pristine gold electrodes when it is used for the injection. Then what he can do more, he can selectively, he can, let's say, deposit one electrode coated with one type of molecule and the other electrode with the second type of molecules. And so in this way, he insert asymmetry in the injection and extraction of charges, so he could fabricate essentially a diode with a very high rectification ratio of 10 to the power 3. So I think that is something that can be used with any type of electronic device. It can be used, for example, for a perovskite device, can be used for organic electronic device, where the asymmetry would be interesting to, for example, look at light-matter interaction. Now, the last part of my presentation will focus on hybrid van der Waals heterostructures, and the idea here is to grow, to exploit the top layer of the two-dimensional materials and grow, let's say, super lattices on the top of it. This is something that we have started thinking about these approaches, and we report in 2016, 2017, a progress report in Advanced Materials with Marco Gobbi, how to make hybrid organic, inorganic van der Waals heterostructure. Of course, we are inspired by the extensive work that has been done on inorganic heterostructure by Andre Geim and his community, by overlapping different types of two-dimensional materials and, for example, rotating one on the top of each other and looking at Moiré pattern. Now, that is the approach of the physicist. If you are a chemist, what you do, you typically take any kind of two-dimensional materials and you literally deposit on its surface either an electron-donating or electron-withdrawing molecule in order to controllably dope the surface of the two-dimensional material. Now, I like to spend a couple of words about the mechanism of doping of two-dimensional materials using molecules. And there are essentially 2 different types of mechanisms you can think of. The first one is about placing on the surface of the two-dimensional materials molecule with a high dipole moment and align all the dipoles. And then at this point, you will have the electric field is emanated by the dipole that will act as a local gate and will shift the work function of the two-dimensional materials, inducing the doping. Or the second one that is about charge transfer, and this is all about the energy levels alignment that determines the doping by favoring the transfer of electrons from the two-dimensional material to the molecule or vice versa. I have no time to talk about the first one, which of course implies to have as many as possible dipoles all aligned. I will discuss about the second one that is much more easy to apply. We actually, to demonstrate this, we continue to work, in particular together with Stefan Echt, on photochromic molecules that is synthesized in Berlin. We have been focusing both on azobenzene diarylating and spiropyran. Today, I will focus mostly on diarylating and the peculiarities because the 2 states, they are both thermodynamically stable, so that is great for electronics, and also they have different energy levels. And so that allows us to play with the electron transfer process. So our idea is to use photo switching molecules as gate to translate an incoming light input into the change of the material's properties in a digital fashion. And so now there was a PhD thesis of Aixin, that now she's back in Shanghai, under supervision of Zhao Yang, that now is back also in Jilin University. And the idea was pretty simple. As I mentioned before, the diaryletin, they have different energy level depending of the isomeric species. Now, so we start, in this case, with tungsten diselenide. This is an ambipolar, can be ambipolar type of transport material. And, but depending on the thickness, it can also operate as an N-type derivative. And so in this case, we just focus on the conduction band that is 3.5 eV. And together with Stefan in Berlin, we have designed and synthesized some diaryletin whose LUMO, as in the closest phase, is inside the band gap of the tungsten diselenide, and in the open state is out of the band gap. What does this mean? So if you have a dopant that has a level that is inside the band gap of a semiconductor, it will behave as a trap for the charge of a semiconductor. Whereas if the levels are out of the band gap, the interaction with the semiconductor will be pure electrostatic. So the idea is that we have to interface these two different types of materials, and by changing the state of the diaryletin, by irradiating with UV invisible light, we can change the way it electronically interact with the tungsten diselenide. So that's the overall idea. And so the device was fabricated in pretty simple manner. We exfoliated, so Scotch tape tungsten diselenide. We transferred this to the silicon dioxide. Then we fabricated a backgated device with a laser writer. We annealed to get rid of all the resist that we had around. We spin coated a diaryletin film of about 4 nanometers, 3 to 4 nanometers. No need to be ordered. And then we irradiated different wavelengths to change the state of the diaryletin. Now we start with a bare device with a mobility about 16 centimeters square per volt per second. Then we physically solve the diaryletin in the open state that is non-trapping, and we have a lowering of the mobility of about 20%. We irradiate with UV light, so we close the diaryletin. That becomes a trap for the electrons. In fact, the mobility goes down to 52%. And then at this point, we irradiate with visible light to reopen the diaryletin, and you can see that the mobility went back to 13, as well as the threshold voltage that from the doping, we go back to undoping case. And so this is highly reversible. We can make cycles, but we can also use the fact that depending on the thickness, tungsten diselenide can be either N-type or ambipolar. And so ambipolar means that in a different study that we published later in Advanced Material, we have physical on the surface of the tungsten diselenide, a blend of two different diaryletin. The first one, that's the one I just showed you, that given its energy level of the LUMO, are responsible for the trapping and detrapping of the electron transport. And the second one, given its HOMO level, is responsible for the trapping and untrapping of the whole transport. And so I have no time to show you the result. This was also applied on devices that were supported on flexible substrate, and bending cycles were done showing the robustness of our device. Now, the very last few minutes, what I want to discuss is the fact that two-dimensional materials are structurally very, very well defined, which is great. And you have two surfaces, so you can think about putting a given, exposing to a given environment the top surface and a different environment, the bottom one. And so this is a kind of asymmetric functionalization of the two surfaces of the two-dimensional materials in a kind of Janus approach as a way to boost let's say, the functional diversity. So the idea we used in this series of studies was pretty simple. So we built up on the concept of photochromic layers as a way to optically control or modulate the electrical characteristic of the tungsten diselenide device. So we put the diaryletin layer underneath the tungsten diselenide because it can be addressed without any contact through light illumination. And then we cover the top surface of the tungsten diselenide with a ferroelectric layer. So in the first case, we have the optical response. In the latter case, we have the response to electrical stimuli. We did not invent any new ferroelectric material. We took a very well-known case. Paul Blom and Dago Deleuve have been publishing a lot of papers on this when interfaced with, for example, P3HT. And the idea is very simple, that if you apply an electric field, you can swap the fluorine atom orientation, so they can either point down towards the tungsten diselenide, or they can point up, let's say, out of the surface. And now, and of course, we use a very basic concept of ferroelectricity. So if you apply an electric field inside the coercive field, you will start aligning the dipole, and so you can have, let's say, intermediate states with a partial alignment, or you can arrive also to, given the voltage, you can arrive also to the total alignment of the dipoles. And so that's the device architecture, essentially. Diarylithin on the bottom layer, supported on silicon dioxide. This is just a spin-coated, disordered layer. And then we have the tungsten diselenide and the ferroelectric layer and with a gold electron on the top. Now, what I like to stress is that this ferroelectric layer, we learned from the organic electronics, has to be very thick, about 500, 600 nanometers thick. So I was not sure that I could have photons that were passing through all this. And actually, so the first test was to check about the optical switchability of the diarylithin layer, which turned out to work very well. So essentially, we can start from the open state. We irradiate with UV light, and we can close all the diarylithin, so create traps, and then with the visible light, we can go back to the initial state. And so that is highly reversible. So at this point, we also separately like to check whether we could address with the electric field the ferroelectric material, and by applying, shifting from plus 60 to minus 60 volts. Plus 60 volts allows to align all the dipole pointing down. That is the highest current possible. And with minus 60 volts, all the dipole are pointing up. With the difference in current is about 68%. Then, of course, we start to try to apply together the two stimuli, one by one. So we start from the highest current possible, where all the diarylithin are in the open state, so they don't trap, and all the dipole are in red pointing down. Then at this point, we irradiate with UV light. So we close the diarylithin, we create optically the traps, and all the dipoles are still pointing down. Then we apply minus 60 volt. We reorient the dipoles. So this is the lowest current possible. So with the diarylithin in the closed state as a trap, and the dipole pointing up. Then we illuminate with visible light. We reopen the diarylithin, so we regain the optical trap that is not there anymore. And then we apply plus 60 volts, and we go back to the initial case. So you can see we have total reversibility. We can make cycles. And then the question is, how many information can you store there? And so depending on how fast is your laser, for example, this was done in my lab. They were not very much equipped. If we start from all diarylithin in the open state, each pass, as fast as it is and with low powers as possible, we have a finite number of diarylithin that will close. So you create more and more traps. So here I could show you that we have 84 distinct levels. When we did this in collaboration with Nova Gorica, this 84 became 256. So it's a kind of 8-bit memories. Likewise, depending on the voltage that you apply, you can align partially or totally the dipoles. Okay, so here I could show that we have 9 different types of distinct levels that are addressed electrically. And so essentially you can combine the two and first use one stimuli, then the other one. The bottom line is that by summing up the 9 levels you can achieve electrically 84 optically, you have 756 levels. That is a kind of 9-bit memories. If you use a fast laser, this can become up to 11 to 12-bit memories. And so essentially our approach, the approach in my lab is the one of trying to pursue the multifunctionality by diversifying the function in our device, so according to a more than more approach. And so the idea that we develop is the one of trying to use not only photo switches, but as many as possible of the stimuli responsive molecule. They can respond to any kind of input you want. Chemistry has been developing this over the years, so everything is our availability. Now, all this allows you to develop some interesting logic operation that can also emulate some neuromorphic type of operation. And that is what we have been doing very recently. And so, for example, we're trying to emulate the type of memory that you can have in the brain, the memory that diversify in terms of how long they last. So you can have the short-term memory, the long-term memory, the permanent memory. The first two are obtained in the brain through ion flux, the latter one by protein synthesis that is a bit more complicated. And actually, since we have all the switches that have been developed by chemists and supramolecular chemists in the last 50 years, then we can use all of them. Because, for example, we have diarylithin that can be used to have permanent memorization. You can have isobenzene, depending on the experimental condition. You can have fast or medium length of, let's say, duration of a given state, and so on and so forth. So that is what we did in this last example I want to share with you, that we have fabricated a molybdenum disulfide device that was on the top, there was ionic gel in which were dispersed ferrocene molecules. On the bottom, the isobenzene. Ferrocene, actually, depending on the voltage you apply to the ion gel, you can have either the oxidation of the ferrocene to ferrocenium, and this is something that can be used to emulate a short-term memory, because as soon as you eliminate the voltage, then it goes back. Whereas with higher voltage than 2 volts, each pulse, you increase the number of ferrocene that are absorbed by the interface with molybdenum disulfide. And that is a much longer lifetime, with this fine-tuning coming from optically with the isomerization of the azobenzene from the trans to the cis. Having said that, if you're interested about our approach, you can read this paper here. I'd like to acknowledge my sponsors, and finally, I'd like to acknowledge who made the work. So this is my team, which I'm very proud of. There are a lot of chemists. We are missing physicists. We have some physicists. We need more. And I think we really need this kind of interdisciplinary team in order to perform this kind of research. And with this, I'd like to thank all of you for your attention.
Thank you very much for this fantastic talk. Is there any questions? I think we have time for one quick question. Yes, Dodo.
So thank you so much for supporting our journal. I saw a lot of you. And also a beautiful combination of 2D and the supermolecule. So from the electronic device aspect, I think reliability and durability is very important. So when we report some device performance, do you get kind of a statistic distribution of the parameters? Or how would like the temperature, humidity, or even radiation affect the device performance?
Well, it really depends on the material type, okay? So of course, for example, molybdenum disulfide, that is the workhorse of the community as a semiconductor, that is not very stable in air, okay? But in fact, that's the reason why I totally embrace the idea of the European community to kind of develop new 2D materials. For example, another workhorse is black phosphorus, which everyone knows that oxidizes in air very easily. And for example, we developed very recently a new allotrope of phosphorus, that is violet phosphorus, that is much more stable with higher performance. Okay, so there is a need to continue to innovate on the material side in order to solve some of these problems. Because of course, the device, they have to survive and be used in our, let's say, environment without need of being too much encapsulated and so on. So that's a true problem. I totally agree. But I have a question. I don't see the Italian flag. I was looking. With all the Italians that are at Wiley. Yeah, here it is. Okay, thank you. All right, sorry.
Okay, thank you very much for being
Thank
here
you.
today. And now it's my pleasure to introduce Professor Tanja Weil. She has been director of the Max Planck Institute for Polymer Research since 2017 and managing director from February 2020 to 24. She studied chemistry at the TU Braunschweig and then she went to the University of Bordeaux where she received her PhD. Sorry, that's wrong. And then she went to the University of Bordeaux, and then she received her PhD from the Max Planck Institute for Polymers in 2002 under Professor Klaus Müllen. From 2002 to 2008, she was at Merz Pharmaceuticals and held several leading positions. In 2008, she accepted a position as an associate professor at the National University of Singapore, and since 2010, she went to the Institute of Organic Chemistry at the University of Ulm. Her scientific interests are in the field of biomaterials research and material-cell interaction, and today she's giving a talk about materials talking to cells. Thank you very much for being here today.
Yeah, many thanks for the kind introduction. Thanks a lot for giving me the opportunity to speak here today. And I just realized it's already the second birthday I'm celebrating with advanced science in the past 2 years. So there was the first birthday, was the 75th birthday of Klaus Müllen, where we had some kind of composition of papers on carbon-based materials. So, and this is basically, so today I will talk about some more bio stuff, and this is in the second birthday, which is dedicated to the 10th birthday of advanced science. And I just realized, so basically, looking into all the presenters and also presentations we've heard today, so I mean the field is pretty broad. So I will now move a bit more towards bio. There was Paolo giving a beautiful talk towards materials, and I think it also nicely shows the topical breadth, yeah, that you have in advanced science, and where you're publishing. And I think this is really a great pleasure, yeah, to be also from part of this big family. So also from us, a happy birthday applause. And please continue. Let me briefly introduce the general topic of my talk. As I said, we will move a little bit towards bio and material-cell interactions. And I would like to quickly introduce to you the smallest entity of life, so the cell. And what you can see here, I don't have a pointer, unfortunately, but I would like to show you a bit on a schematic fashion on the right-hand side. So a view to the cell, how chemists basically imaginate how cells could look like. So you have many different compartments, and in these compartments you find different reaction conditions. Yeah, so it's like a reaction vessel. So you have many different flasks inside the cell, where you find a different pH, different oxidation potentials, and so on. And we thought whether we could make use of these diverse conditions you find in the cell and really do chemistry in a programmed fashion, and in that sense also contribute to biological processes, so to be able to also control processes by chemistry that we do. So it's in principle the opposite to what biotechnologists are doing. Yeah, they are expressing enzymes, and then this has an impact on the cell. So we are trying to bring in chemicals from the outside that react in a defined fashion. And the big inspiration came many years back. Yeah, I think Caroline Bertozzi is really also a role model for us in organic chemistry. And so she received the Nobel Prize for work that is naturally already much older, and it clearly also inspired me. And she could really perform controlled reactions in this very complex cellular environment. Yeah, and I thought personally, as a young scientist, this is not possible. Yeah, I mean, you have so many different molecules; it's really very dense in a cell. But then the chemistry she and later also others have developed allows to do precise reactions in a biological environment. But then you need two components, and it's based on two compounds meeting each other in a catalyst-free environment. So we thought that we make use of specific environments the cell basically offers. So if you look into the cell, I already mentioned, yeah, you have mitochondria where you have reactive oxygen species. So in principle, you could do oxidation reaction there locally. Then glutathione is present, and there's a gradient from the outside to the inside, but also in a cell type specific fashion. So for example, in cancer cells, yeah, you have, so in many cancer cells, you have much more glutathione than in healthy cells. Yeah, so the cell, due to cellular metabolism also, is being able to control certain reaction conditions, and they also change from cell to cell. And naturally also pH and enzymes do change inside. So by knowing what are the particular reaction conditions, we thought we can bring molecules in that then enter these different compartments and react in a predictable fashion. And today I would like to show you basically two examples, and then one direction we are also currently pursuing. And everything is in this anniversary paper, so review paper that we have just published in Advanced Science. And so I would like to show you how we can activate drug molecules in a very controlled fashion inside the cell by making use of these reaction conditions inside the cell. Then I would like to explore together with you how we can produce small molecules in a defined fashion that then can assemble and form nanostructures in a cellular environment, so bringing into cells new synthetic structures that also have an impact on cellular function. And the last part, that's very quick, I would like to show to you how we are also using AI to identify new nanostructures with unexpected bioactivities. So this is a little bit of a busy slide. It's also taken from the review. And what I thought was, I just show this briefly because here it clearly depicts the different environments that are particularly important also for us for doing chemistry. So you have pH gradients inside the cell. So you, for example, in early endosomes, you have slightly acidic pH conditions, but then in the lysosome already that's quite acidic, so you can also control chemistry that responds to pH. And here on the right-hand side, Dominic and I, we have also added some reactions or some groups that can be cleaved at acidic pH. Then, as I said, so reactive oxygen species, so there are also functionality that respond to the availability of reactive oxygen species. And so this chemistry has been summarized in this review article. So this is the first this was the first model system that we have published some time back, where we said, can we now combine different functionalities that respond not only to one stimulus, but to two stimuli. So this chemistry goes quite away from prodrug synthesis, where you just bring in a drug molecule, one group is cleaved, and then you activate a drug. So we thought we combine different stimulus-sensitive groups in order to then be more controlled and more precise. And this was Max Segota in his thesis, and he has combined, and so this is shown on the left-hand side, different peptides that are where amino acids carrying a boronic acid group and a catechol group are brought in vicinity, so they interact and so, they form boronic esters. And if you have two boronic esters, the complexes are also more stable. And then we have an inner disulfide that can then form if you pre-orient and bring them in close vicinity. And at the end, there is a long, actually a long bond between the two thiols. On my computers, it's beautifully visible. I heard it's also visible in the internet. It's not visible here, I'm very sorry. So there's also bond between the two thiols. It's nothing I forgot, it's on my slides. And it really shows how these two dynamic covalent linkages are connected. And the idea here is to control so that you have two different stimuli under which basically these bonds break. So then we thought we bring this chemistry to its application. So we thought that maybe we can embed drug molecules into these these structures. And here you see camptothecin. That's an anti-tumor drug that is pretty badly soluble. It has a low IC50 value, so it's quite potent, but it's very it's difficult to handle due to this low solubility. It has a very high binding to plasma proteins, which is also not so good for applications. And so we thought we use this kind of chemistry, bring this drug molecule in, and then based on two different stimuli, we can release the drug in the intracellular space, so in the cytosol. So this is how the concept looks like. This was the chemistry. So here, basically, we have a targeting group via click chemistry, so it's not the full beautiful structure has been synthesized, but what is important for you is the drug molecule shown in red, and then basically one side where the salicyl hydroxamate is binding to the boronic acid, and then basically this yellow linker where you have a group that is cleavable under reductive conditions in a self-immolative fashion. So it's a ring-type structure that forms quite nicely, and a cell targeting group. This compound here, it's quite big, but it's nicely soluble, and it has cell type specificity due to this cell receptor targeting group, and it's non-toxic. So in this complex form, it's you can dose it quite high, so cells tolerate it very well. So, but then if this molecule enters the cells, so via the cell targeting group, then basically a cascade of reactions is initiated, and what you can see here is basically, so at lower pH, so during endosomal uptake, so in these vesicles that are acidifying, then what happens first is the boronic acid and this is salicyl hydroxamate, so the bond is cleaved, both groups are generated. And then next, intracellular glutathione, and the concentrations are high, in particular in cancer cells, yeah? So they also cleave the disulfide, and then we have a self-immolative attack, so from the thiol, and basically a cleavage, and the drug molecule, not exactly, so the boronic acid derivative of the drug molecule is liberated, which then oxidizes in the presence of high amounts of reactive oxygen species that you have, particularly in cancer cells. So after oxidation, the phenol derivative is formed. That is also pretty active, and I'll show that on the next slide. So this is basically a cascade of reactions and of conditions that need to be present in order to liberate the drug molecule. And I hope you can also agree that this is different to the classical classical prodrug kind of chemistry. So what we could first show also outside the cell was that you need glutathione, that you need an acidic pH in order to be able to liberate this drug molecule. It goes nicely into cells. This is the red color you see underneath. And then inside the cell, you see a dramatic inhibition in growth. And this is very much different to the non-cleavable analog that I'm not showing here, but you need to believe me here, that inhibits cancer cell growth much less efficient. So we thought that this is basically a nice possibility to maybe impart more selectivity to the generation of active drug molecules. So if you really tune the chemistry to a certain cellular microenvironment, for example, to an environment that you find also inside cancer cells. Since I don't have endless time, so I move over to the second part of the topic, where I would like to show you how we use also this kind of chemistry in order to control whether a small molecule can form nanofibers, so nanostructures inside the cell or not. And what we do is, and this is work from Sarah and from David, that we use a bioresponsive molecule. And this molecule is also uptaken into cell. And then there are cellular stimuli that change the molecule, and at the end a self-assembling structure is formed locally that forms fibers, and these fibers you can visualize, you can see them inside the cell, and they also affect vital cellular processes. So first of all, and I would like to, so normally there's a small video which is now not playing, but that doesn't matter. I just would like to show you that amphiphilic peptides are a good platform here. So you have basically one hemisphere that is lipophilic due to a phenylalanine, and the other hemisphere is hydrophilic, and they assemble very nicely into so-called amyloid-like nanofibers. And they are pretty stable. They can be degraded, but they are, at first instance, quite stable, and they are quite precise in their structures. So we thought that this is a nice system. The only problem is, once this molecule is exposed to aqueous environments, then fiber formation takes place. So it's hard to control this. So Jasmina started this first. This was still from a PhD thesis in Ulm, where she introduced depsipeptides, so structures where you have an ester group that can be attacked by a primary amine. And what is very special about this depsipeptide is that you have a kinked structure. So once you have a kinked structure, it's not assembling, it's nicely soluble. But the information for assembly is already in, because you see that they are lipophilic and hydrophilic amino acids, so in the short letter code, but then also in the full structure. So what happens is, once the amine is at a certain pH value, so if you move towards neutral conditions, then there's the attack of the primary amine, and then basically there's a ON-acyl shift that occurs at pH 7, and the self-assembling structure is formed, and you can see soluble moves to like fiber-forming peptide. This is still outside the cell. But we thought that this is a very nice system now that we can use in order to control structure formation in a cellular environment. So the amine is not so easy. So this pH switch to control just pH, it's a bit more difficult, because outside the cell there's also neutral pH. So we thought we lock it, and then we have a second piece of information. And so that means on the one hand side we have a lock, and if we unlock, and we have a localization sequence. So we introduce all kind of information, chemical information, into this molecule so that the molecule behaves in a very controlled fashion in a complex environment. So on the one hand side, there's a group for cellular uptake. So the information, please enter the cell. Second, the green part unlocks the molecule under specific conditions, for example, reactive oxygen species and pH. And then there is a pro-assembling isopeptide, so this kinked dipeptide structure that at a certain pH linearizes then to the linear peptide. So and you can then make this molecule responsive to different triggers. External triggers such as light, I'm not going to show that, we published a bit there, but also cellular triggers such as pH, reactive oxygen species, but also enzymes. And everything is there in order to do what nature does to control when does a structure form inside the cell, when and where. So this is the chemistry, and we call this conditional transformations. Yeah, so if the pH drops below neutral, yeah, then this dynamic salicyl hydroxamate boronic acid group is cleaved, and only then the boronic acid group gets oxidized if reactive oxygen species are present. So you need first a certain pH, next, and this is also the sequence is important, next you need to oxidize the boronic acid. Then again, the pH needs to be neutral. Yeah? And only under these assumptions, you form the linear peptide and the nanofibers. And then what is nice is we can also add dye molecules so that we can also image this nicely. But these conditional, so where the chemistry is important, but also the sequence in which the chemistry proceeds. Yeah? This allows us to then move over to the cells. But here is just like to show that I'm not just drawing pictures, but this is something that we are doing, and that this can be also controlled outside the cells quite nicely. So you can follow these reactions. You know how much reactive oxygen species, for example, you need. Does this pH switch really work? And this is something normally with a pointer. Yeah, I would point a bit better towards this, but I hope you can see that this red curve, yeah, this is a curve where 2 is ramping up, the blue one, yeah, that means 1 is consumed, and you can see this is quite fast, yeah, and then basically ISO 2, so this intermediate, you can see how it's ramping up, but then also consumed, and 2 is formed also relatively quickly within a window that we can observe nicely. So now we are bringing the system into cells, and this has been done by Michaela Shishwen and also David. So the structure that I've just shown you with a transport peptide, the TUT sequence that also viruses are using, such as HIV. Yeah, it's a cationic peptide, so this allows cellular uptakes and endosomal compartments. This dynamic covalent bond is cleaved. Then a reactive oxygen species in cancer cells allow oxidizing the boronic acid group, and then you are in the cytoplasm, pH is neutral, fibers should form. I thought maybe very complicated, might not work, but then Michaela was very brave and really got this up to work, and we were only successful because we could team up with Katharina and Ingo from our institute, because they're equally were very active in being able to image cellular structures. And on the left-hand side, you can see where the red arrows are. So these structures that are formed there, they are only formed if our molecule is present. We also isolated them later on. You can see these nanostructures close to mitochondria. And what we could also show was that if you have a peptide that assembles very quickly, so we have different peptides with different speeds, I don't have time, but just to show you, here you see the endosomal compartments to our mind, where at the interface the fibrils are being formed. So if you have systems that are assembling very fast, so you have others that are forming the structures inside the cytoplasm, and again others where assembly happens quickly. And Jong is here, who's an expert in the field. I will also show his work here in this paper, where where he was really looking into the assembly processes inside the cell by doing lifetime measurements and then basically studying where in the cell do I have monomer, where do I have oligomers, and where do I have a polymer, in order to really understand how these processes function at a cellular level. So now what happens to the cell, and maybe this is something where you can switch on the video, I would be very glad, because that shows you now, so in red the cell, the mitochondria that are stained, and in blue the fibrillar structures that are being formed. And what you can see here in cancer cells, and I'll come to that also in a moment, is, so red turns to blue. So a healthy cancer cell actively dividing turns into a very dead cancer cell. And on the right-hand side, you see also the mitochondrial network. So mitochondria are not alone, they are connected with each other, and the connection is important. And you can see within minutes, how this network is basically being disintegrated. And this has a dramatic effect, and this is something that we can also measure with time. So we can measure with time how the cell is breathing. So how much oxygen does the cell use? And this is something that we measure. And then we can see so that upon addition of the sample, that respiration, there's a strong impact on respiration, there's a strong impact on the production of ADP, and there's a concentration-dependent cell toxicity in a very efficient fashion, and we tested this for triple-negative metastatic breast cancer cells that are not responding anymore to chemotherapy. So cells that have been treated but that are not, that have become metastatic already, and we have a very strong effect here. So, and this is something where we also believe that this is maybe a possibility, so to use a microenvironment, tailor it to cancer cells, and then have a strong effect by these artificial cells that we are building. So if you bring this then also to 3D tumors, you can also induce quite efficient apoptosis in 3D tumor models, where so tumor cells have already produced their own microenvironment. They are growing, and here in red you can see how the cells are basically how the cells are also dying in these 3D tumors. And one of the reasons might also be that the small molecules can also diffuse maybe deeper into the tumor. But this is something we have not published yet. We are preparing for publication and also continuing to study this. So I think I finished showing you what's happening with these fibrils inside the cell. And according to my watch, I should still have 3 minutes or not? No, maybe 2, then I'm faster. So I would just like to highlight, it's not all about inside. So what is also quite interesting, to bring these fibrillar structures to the surface of the cells, and then you can, for example, you can also change what kind of molecules or what kind of, or whether viruses can uptake into cells and then induce different processes. And this is something, and therefore I just put it here because I wanted to show you that with Tristan Bereau from Heidelberg together. So we have a library of many, many peptide sequences. They form fibers, and but they have all different properties. So we investigated the chemical space, and we tried to link basically activity to morphologies. And to cut a long story short, so we were able to have a flip chart that allowed us to understand which peptide fibers, I only said always peptide fibers, it's not really true. So there are some fibers that are very active, there are some fibers that are not so active, and we could show very recently, so this was Kybra's work, that only those fibers that have hydrophobic patches at the surface, that they are able to aggregate, and only those ones that have microscopic aggregates, they can, for example, bind virions, they interact with cells and attach to cell surfaces. And so that was nice, and that was an output of a data mining and machine learning approach we did together with Tristan. So Maybe just to show you, so one of these structure is basically able to interact with cells, also with neuronal cells. And what we can do now, and this is my last scientific slide, so we can pattern cells in 2D now with these structures, because we can control whether cells adhere to these structures or not. It's not the last slide, so the very last slide comes now. So it's even possible in 3D to use these materials and print them. And I think this is a nice opportunity maybe to move towards printable biogels and optimize them via these machine learning approaches, what we are doing. So with this, I would like to stop my talk. Thanks for listening to me. So I showed you we can do a lot inside the cell. This was the focus of my talk. I was very brief, maybe too brief. Please excuse myself, please excuse me for that, but there is a lot also happening outside the cell, and this is also an important area in our group to investigate and profile materials that stimulate neuronal outgrowth and interact with cells and allow virus uptake. So I've mentioned some of the people who have contributed from my group, not everyone naturally, but there have been many more. Some are here, Celine is here, Yong is here, and can answer to questions. This is the group on a group retreat to the Lake Tegernsee, and here are our cooperation partners and funding agencies, and thank you for your kind attention.
Thank you very much. It's a really, really cool talk. Uta.
I take the question now, Dodo. I hope you're fine. Thought as a healthcare editor, I also have to ask the healthcare question. Impressive talks. I really like those fibrils that are actually integrate in cells. I was actually wondering the soluble kinked structures that enter the cell, are they actually toxic to the cells themselves? And would then actually the fibrils then kill more cells or kill them quicker or anything?
No, we did a lot of controls, and we also synthesized isopeptides that also do these reactions. So everything with a targeting compound, also these controlled reactions, everything. But then the peptide that is formed is non-assembling. So we've also synthesized this in order to really show that this effect that we see stems from the self-assembly. And Yong, in his paper, he could also already show that it's in particular these are these mature fibers that are formed, that have this effect. I only showed you how we kill cells. We have also one system that is actually introducing a new function. So it's acting on T cells and changing the nanomechanics in T cells, making them more active towards cancer cells, so bringing in function. We have not published this yet. I won't show it at the moment, but so you have, to my mind, with these structures, you have a portfolio to control. So with the extent also of fibril formation and where these fibrils form, so whether you might kill a cell or you might impart a new function. We are interested in both.
Okay, that actually answers the second question I had, like where do you see the applications in cells? But the immune thing sounds really promising.
Yeah, thank you.
Thanks a lot.
Another question in the...
Sorry? Bacteria.
It's also kind of similar platform. How to compare with them? Do you think you can extend this to bacteria because they reproduce much faster?
Yeah, so I think one can make use of this. We haven't done this, because we work a lot on cancer cells, on now also on T cells, on immune cells. And I mean, if you have everything next together, so you don't want to then mess with bacteria cells, in this environment. So at the moment we are not doing it. But I think if you have a tag that brings the compound into bacteria cells, you are in, I mean, there will most likely be also a similar effect, but we haven't studied this yet. Thank you.
Okay, maybe one last question and then we really have to continue.
Yeah, so peptides are I mean, they are really good in producing different kinds of structures. So you can have these fibrillar structures that I showed. We also work with honeycomb-like structures or peptide nanosheets. I mean, the problem is a little bit, it's then not so easy, therefore I didn't show it also here today. So, for example, if you produce nice nanosheets outside the cell, you bring the same molecules in that form the nanosheets, and inside the cell you don't form the nanosheets, you form the nanofibers again. Yeah, so this is something that responds very strongly also to confinement. And you might simply form also other structures then, but peptides are very diverse. You can form all different kinds of structures outside cells, but then inside the cell, it's again, always, one needs to be a little surprised, what might happen there, and how you can image this. Imaging is difficult.
All right, thank you very much. Really, really cool. And with this, I would like to welcome Zhijian Zhang. Professor Zhijian Zhang is currently a professor of soft materials and devices and the chair at the Department of Applied Biology and Chemical Technology at the Hong Kong Polytechnic University. He studied chemical engineering in Tsinghua University and received his PhD in chemistry and at the University of Cambridge, followed by a postdoctoral position in the Northwestern University. He has published over 200 papers in top-tier journals and also in Advanced Materials and Angewandte Chemie. His research interests include surface and polymer science, nanofabrication, flexible and wearable electronics, and energy conversion and storage. Thank you very much for being here today. I'm very excited.
Thank you. First, I would like to thank the organizer to have this great summit, and certainly I would like to congratulate the great achievements of advanced material families, especially the great celebration today for the these three journals. Today I'll be talking about some permeable type of soft electronic. That will be a continuing topic of Martin's talk in the first talk in the morning, and I'll talk about how and why permeable electronics are important. In the next many ways. So my research in Hong Kong has been truly focused on the development of soft electronics material, and simply because 15 years ago when I go to Hong Kong, I would believe that will be the future, and there's a ton of application scenarios of this technology. So our group has been a interdisciplinary group on the topic of soft material and devices, and we are very good at understanding and manipulating the interfaces of materials and the devices. So we always start from try to understand what is needed in the future, and we try to develop materials, soft material in particular, that can address those needs and develop the material in a way to devices and recently system level. So you'll see that there's a big part of this kind of flexible batteries that we publish most of it in advanced materials, which I'm not going to talk about today. But I think I wanted to show you 3 slides to show you that what we mean are flexible batteries. And the idea is that because all electronics, most of them will be powered by secondary rechargeable batteries, and therefore in principle, we need a lot of flexible battery to power those soft electronics in the near future. So the fundamental reason why our lithium battery nowadays are not flexible is because we use a lot of metal foils, and metal foils have very low yield strengths, as you know. So when you bend it, the bending strength is typically over the yield strength, and therefore the material will yield and things get break, right? So what we did in Hong Kong was we developed some sort of so-called textile composite electrodes that fundamentally shift the metal foils and laminar structure to a textile type of materials and 3-dimensional interpenetrative structure that allows great flexibility of the electrodes and therefore the cells. Nothing into detail, but this is what I show you, that we can have a very, very flexible cell functioning, and so you can sort of torture the cell. The size of the cell is roughly like size of a name card. You can bend it, you can fold it, you can crumble it, and the cell is quite stable. So this is a cell that we made in the lab that are powering, are actually charging, okay, not discharging, are charging the cell phone while it's being bent. And we are commercializing this technology in recent years, okay? So let's come back to the real topic about the permeable electronics. So I think if we talk about soft electronics, we can consider development into three major areas. One is kind of a starting point of soft electronics. At that time, I think we talk about wearable electronic in the 1960s, all right? That's something 60 years ago where people start to imagine if it would be miniaturized electronic devices or products and put it some format on top of a body, we can call it wearable electronics. Obviously, at that time, the computer is quite big and the function is quite small. But nowadays, we have all these imaginations on the market. We have those watches, bands, and IR, VR gadgets. And in the future, we look for something really, really thin, really, really lightweight, like imperceptible electronic that Martin talked about. Something is skin-like type of electronic, or even things that can be implanted in our body. Of course, this will also be used, for example, for robotic type of application, not only for human beings or animals or plants. But then if you ask a big question, what next, or what has been missing in the research in the last 30 years, I will say the keywords will probably permeability. The reason is because we have been using plastic thin films and elastic thin film for the research of this kind of soft electronic in the past 30 years, right? So the scientist has tried to tackle the mechanical mismatch, the device fabrication, the system integration in that ways. But think about it, the material, I mean, at least for human being application, for animal or for plants, it has to be wear in a certain way for a long period of time, isn't it? And therefore, it looks a huge kind of property related to biocompatibility over long time uses. But if our human body is covered with a big piece of plastic or elastic thin films, then the permeability comes up the problem, because these materials, the thin film of plastic, are known to be impermeable to air and very low permeability to moisture, right? However, our human body is covered with the biggest organ, the skin, with a porous structure. So the skin is porous in a way that to lose water, right? In two manners. One is to lose water in a way so-called insensible perspiration, then in a kind of vapor format that will lose water in this speed, which is way higher than the permeability of typical plastic that can offer. Second things that probably everybody knows, perspiration using liquids, so sweating. Okay, so we can actually sweat at different positions of our skin at a speed of 1700 grams per meter per hour, which is, again, very large. So if we do sports, we lose lots of water, yeah? So, and again, if we do sports or do use daily activity and wear, and does not allow the skin to get rid of water normally, then we have so-called inflammation, skin inflammation, and for example, we feel itchy, we feel swollen, and that's type of symptoms of skin inflammation at a very early stage. And therefore, permeability, it seems to be quite overlooked in the last many years, but it is crucial for long-term use, comfort, and health concerned. And therefore, in the last couple of years, I think there's a few so-called permeable breathable electronics is being emerged, and I think this is old data, and this year definitely is more than 300, 400 papers with this kind of keywords. So how to make the electronic permeable? I think the answer is very simple. Just get some pores or holes, right? You can punch pores, or we can produce material essentially with porous structures or structure in another certain way from the bottom up. And this is a kind of perspective that we summarize 2 years ago, talking about the two major streams, how to make permeable electronics. One is from the upper version from the electronic community, that you start from a rigid to flexible to stretchable, and then get some holes to permeable type. Or you start from something even more old-fashioned, that from a wearable type of view, that we can functionalize the fibers that we wear every single day, right, and assemble the fiber in a certain way that to make devices and build up into systems that allow us to have permeability and wearability. And of course, at the end of the day, I believe two technology will merge and then produce something very, very fancy and useful. So today I'm going to showcase how these two things work a little bit in our lab. I'm going to first talk about how do we actually produce some kind of functional and fibrous conductive materials and build up into a device and even system level. So that was kind of an old question when I actually started in Hong Kong. And the important question is how do we make very robust fibrous conductive materials? For example, if I want to coat some very conventional metal, for example, copper or nickel, on top of a fiber, how do I do that and make it very, very easy to be produced, reliable, and reliable in a way that when we use them, right? So over the years, we developed technology we call the polymer system metal deposition. Basically, the idea is to use polymer as a modifying layer or a functional layer that grafted on top of a fibrous substrate surface, and this polymer is designed in a way that allow absorption of inorganic salts, for example, palladium-containing salts, and then allow a further deposition of metal from there. I'll give you a very, very brief, simple example of those that, for example, if we be able to grow this quaternary ammonium side chain polymetallic polymers, we can absorb this palladium anions, and therefore you can use it to catalyze the so-called city growth of copper, for example, or many other metals. So by using this kind of pressing pulse, we can essentially deposit many metals of interest into essentially any single substrate that we encounter with in the last many years. In combination with all the printing technologies, we can pattern them in a submicron scale all the way up to many meters, right? So these are all quite good. And then the most important key message in this polymer system metal deposition is that we form this in a nano-composite interface between the soft substrate and the final metal. And this interlayer not only provide a chemical environment allow you to grow the metal, but also provide a kind of a mechanical isolate, we call it strain isolation kind of interlayer, which is roughly about 100 nanometers thick, to stabilize the metal that are deposited on top of the soft substrates. Now, we can come back to this very simple model. So what we did basically is that we insert the green layer into the top metal layer and the bottom substrate to prevent the cracking in a certain way. Why we believe it's very important is because this green layer is very thin. Okay, think about a scenario. What we want to do is produce something conductive on top of fiber. We want it to be as thin as possible, and so that we maintain a fiber shape and flexibility, and so that we can build up devices, right? So according to the theory that later on we discover, the material requirement of this green layer to enable to improve the stability of the golden metallic layer, the material has to fulfill two major properties, okay? And if we can define the material into two major properties of the modulus, which is the hardness, or the elasticity, which is the yield strength, we found that, okay, I'll just give you the conclusion, that in order to stabilize this metallic electrodes, this green material should be very hard, so it has a very high Young's modulus. At the same time, it should be very elastic, so have a very high yield strength. So most of the material does not fit because the metal is known to be hard but not very elastic. Polymer knows to be very elastic but not very hard, right? So it's difficult to find those material. And luckily is that the material that we produce using this nano-composite layer will fulfill both requirements. And that's not sample number 4 over here, which is under this TEM image. So we form very high density nano-composite layer, and the yield strength over here is roughly 3.8, similar or even higher than the polymer. And the Young's modulus is roughly 39 to 40 gigapascal, is similar to some metal, right? Some soft metal. So in this sense, if we're able to insert this sample 4, okay, in the middle of the metal layer and the soft substrate, we can actually delay the cracking, right, by 100%. So the yield strength was roughly about 0.7 to 0.8 without it, and then if we insert it, we can actually delay it to about 1.7%, which is remarkable. Thinking about we didn't do any engineering of it. We just insert 100 nanometer of material on top of the two layers. And this is quite universal for all sorts of different kind of metals and even ceramics and even thin film devices, I will demonstrate in that paper. By the way, it was unlucky things that the paper was rejected by Advanced Material after review. That was considered one of the top papers that we published in the last 5 years. So okay, coming back, after we spend so much time, but what we show you is that we'll be able to modify these things on top of fibers of different kind of shapes and produce kind of even washable metallic textiles. We can combine with thermal drawing process to make continuous long filament. So what I want to show you is that we can modify on short staple fibers and very long filaments. And once you produce this, for example, long filaments, and you draw it another times, and we can get multi-filaments, and once you get multi-filaments, you twist it a little bit, we get yarns. And once you get yarns, you can weave it, you can knit it, you can structure it using all the mature textile technologies that we've been using the last 200 years, right? So we have sort of almost infinite possibility of combinations of permeability, conductivity, or even stretchability, right? So we can tune this or using all these very fundamental fibrous building blocks to tune the final properties of it. So how can we make a device? I'll give you a very one simple example. This is the simplest device ever probably produced. So this is things that we work together with Professor Yofan Hu in Peking University, working on a technology called TENG, a triple electric and nano generator, which originally proposed by Professor Zhongling Wang in Georgia Tech almost a decade ago. The idea is simple. So we have two electrodes that are waved across each other, and that's it. Right? That's it, okay? No more, furthermore. So what we did was we prepared the electrodes, we weave them across each other, and this material and this device is so sensitive when you actually bend it, they will generate electrical current, and this current, when you read it, for example, in this way, then you know how much the device deforms. So if we tape it on top of the chest, we know how fast and how much you breathe, inhale and exhale. So we use that as kind of a so-called sensor, self-power sensor. But it's just a simple idea demonstrate that we can actually use fibrous material as a fundamental building block to make future wearable electronics using 100% textile materials to make future wearables using via very, very traditional, textile processing that many years ago, right? So, and then nowadays, if we advance the manufacturing technology by assembling of all the other chips and wireless communication, we can even make this kind of electrochemical sensors in a system manner. So this is one piece of textile circuits that we develop in the lab, and then we put every single chips down, and we can monitor, in this case, the potassium or in your sweat, and we can do continuous monitoring. This is kind of one sensor channel system, and then later on, in a similar time that we integrate 5 different kind of channels so we can sense simultaneously the potassium, the sodium, the lactate, the glucose, and the pH in the sweat and in a continuous manner, and then you can deliver this signal wirelessly to your cell phone so you can monitor what happened during exercise. So this is quite powerful of making all this textile circuits and that. And later on, we found that if you be able to manipulate the liquid movement within this textile, you can actually also helpful for doing some kind of long-term wearing. For example, we do sweats, as I said, so you'll be able to create some structures that allow you to manipulate the one-way transfer of sweat from inside out, not just from outside in, all right? Just from inside out, and so that allow you to evaporate the sweats more effectively. So this is just one example out of many examples that we did. For example, we can come up with this kind of a gradient cross-sectional honeycomb structure that allow the sweat only goes from one way to the other. So this is kind of a process where you show you basically trick is also similar to the control hydrophilicity and hydrophobicity, that the liquid can only transfer from one way to another, not the other way around, and therefore you can absolutely dry your skin during exercise if you want. So taking that kind of idea into a wearable, so we can do, for example, in this case, we can have a so-called one-way sweat diode, right? And diode is electrical kind of idea, but in this case, we use follow that kind of idea to a liquid or sweat transfer. In this case, we can suck the sweat from your skin to the outside. And if you build the whole system with all this functional layer and all the electronics, in this case, we demonstrate this is an ECG kind of patch that you can stick onto the chest, and then right over there. So you can offer this kind of wireless continuous monitoring of your heartbeats and ECG signals without intimating your skin, and at the same time it stay very stable during walking, while in comparison I think all the wires didn't really work because there are huge signal variation and interference during all your so-called exercise or movements. Another one is I want to talk about it. What I show you is that we can do things, but then all of them are not in very high density and multi-functionality, right? So things are big, simply mostly is because of the limitation of the fiber size itself, which is typically about 10 to 20 microns. So we will never be able to make something really small and high density when we need high density arrays. Yeah, so therefore we are also at the same time looking for systems that allow us to make high density electronics. We want to learn or use existing manual microfabrication technology like clean room fab, for example, that you can produce 1 micron precision circuits for high-density integration. 1 micron for soft electronic, I think at least nowadays, or the next maybe 5 to 10 years should be enough. At the same time, we want to offer high stretchability that's similar to skin, and therefore is good for wear and for implants, and to offer permeability. All right, so that will be the typical things that and difficult things that we challenge ourselves. The lucky thing is that 3 years ago, actually 5 years ago, we published 3 years ago, that a very smart postdoc find this material that potentially should fit our idea. We named this material liquid metal fiber mat. Basically, it's a porous liquid metal electrode sitting on top of porous elastic fibrous mat. Okay, that we did. And we use that for a permeable, stretchable electronic platform. This is how the material look like. It's a porous piece of mat. On top is a liquid metal, which is gigantic gallium indium alloys, typically used in the lab. And below is a blocopolymer, SBS, probably one of the oldest blocopolymer ever commercialized by human beings. It's porous. I'll show you the structure later. And then property of this fiber mat is that one is super stretchable. You can stretch up to 25 folds of its original length. So my hand is not long enough to do this, show you these experiments in real scale. Permeability is superb because the entire material are porous, thin films, and the resistance is really low. The conductivity is really high because we use metal, pure metal on top. Okay, so this is how it was made. It was made in a very simple way. We use electric spinning to produce the microfibers, which is not nanofibers, microfibers, so it's very strong. We coat the materials with liquid metal by braiding or printing, and then we kind of so-called activate the porosity by stretching. So once we stretch and release over large deformation, the liquid metal, when it sticks on top, it has to break up, right? Because deformation is so large that you'll never be able to survive without breaking. And so they will break up, and then when it comes back, you will heal, and you break and heal and break and heal. At the end of the day, you simultaneously form this kind of a two-dimensional porous network structure from a top view. At the cross-sectional view, if you do a cross-sectional view over there, we also observe the kind of a buckle structure, just like our human skin buckles in a Z direction. So in the combination of the XY polar structure and the Z direction buckles, then we'll be able to have this kind of long range reverse dimensional change without breaking the conductive pathways, which allows high conductivity and stable conductivity over long deformation changes. And again, the good news of this material is that it's quite biocompatible. We ran through this in vivo, in vitro tests following the IL standard. This test is very important, quite striking. So what we did is that we had 6 samples, yeah? And the number 1 and 2 are permeable samples, conductive, non-conductive. Number 3 to 6 are thin film samples. All the material that used to fabricate these samples are biocompatible material. You can eat it, no problem, okay? We don't die. Yep, but then after cover the skin with these 6 samples over 1 week in a kind of humid summer in China for 1 week, all right? So under the skin underneath sample 1 and 2 didn't see obvious change. Under 3 to 6, obvious reddish color and very strong itchy feeling according to the subject, all right? And that means there's inflammation on the skin. And therefore, it tells us that even the biocompatible material are not necessarily good for long-term wear. Actually, it's something that happens to us daily, okay? For example, I am a little bit allergic to latex and rubber. So if I wear rubber rings and do sports for a long time, and then that position will typically become kind of itchy, yeah? So that's actually something happened to us. We didn't realize that. So following that track, we further developed some technologies to make micro-scale patterns, right? Because our idea is to make micro fine structures. And again, it's very challenging because we are using a super soft, highly porous, highly stretchy, and very, very rough substrate, right? And then we want to make some 1 micron structures of it. And we still want to maintain the stretchability and porosity during all the usage. So we developed finally using a kind of a transfer and wetting kind of idea that we fabricated every single microstructure, but silver, by the way, not liquid metal, on top of a hard silicon wafer. We transfer this microstructure onto the fiber mat using this electric spinning and dip this whole patch into a water bath because we had this kind of dextran sacrificial layer during the fabrication, and therefore when the dextran is dissolved in the water, the silver get attached to this kind of SBS fiber mat. And the nice thing about silver is that it will react with gallium indium in the alloying process. So silver will alloy with indium and silver will alloy with gallium. And therefore, when the silver passes through this area, they will only react and stay on top of the liquid metal. When you pass through this area, you only react and stay on top of the silver covered area and de-wax from the rest of the area and form these nice patterns. So this 2 is just to show you how things were done. The transfer process is very easy. This is a 4-inch wafer, typically the biggest sample we can handle in a microfab lab in the university. So this whole thing can be peeled off very, very easily by hand. Of course, the student need to be skillful and be patient. But you will see that the transfer is very nice because the wafer is so clean that simply, we did the calculations, it was 99% success rate if you can really do it well. Okay? And then we have a high density of things. And for example, this is a 3 micron with white liquid metal lines that are floating on top of this fibrous substrate, right? And these are still stretchable, and certainly the whole things are permeable. We did a little bit experiment on the implants, and what we found is that after 32 weeks, okay, after 32 weeks of implants, we didn't find any obvious inflammation on the tissue surface. In comparison, in our own control experiments, we found that for the typical PDMS thin film or PI thin films that with gold, there is obvious inflammation on the tissue surface after about 2 to 3 weeks of implants, showing that our material has pretty good biocompatibility. The device died, the device didn't work, but then the material coverage didn't actually give extra burden to the tissue. So then, by using this technology and this, microfabrication methodology together, we'll be able to build in a three-dimensional the integrated circuits. Yeah. So we integrate things in a three-dimensional and produce the first kind of so-called stretchable and permeable electronic skins. Three-dimensional integrated skins. Yeah? So we can integrate all the units together and then power it, for example, by inductive kind of a power or using a battery, and we can power the entire system to enable different functionalities. And the key thing in this work is that apart from these materials and the patterning technology, we also need to link everything in a three-dimensional manner and also use this kind of a hybrid solder to enable long-range stretchability. At the same time, it's sticky enough so that every connection remain intact during the large deformations. So as I said, we can use wireless communication, for example, through Wi-Fi, or through this battery-free but much closer near-field communication technology. So this is my last few slides to show you that our technology now has been doing a clinical trial in the inpatient, outpatient, inpatient, actually intraoperative environment, and so this is for the I believe is outpatient, healthy people, okay? But we show you that this is our device. There's no skin irritation. This is what standard tests will produce to your skin after about 10 seconds, actually. This is actually in the operation room for the real subject actually are doing the operation because it's heart surgery, right? So our device is actually next to the normal ECG. This is the patients that was done after in the ICU ward post operation, and then we're using our wireless one to monitor the entire heartbeat and ECG signals. So I would like to conclude is that what we did was that we try to use fiber as a building block using top-down and bottom-up approach to make functional materials, and then we assemble them in a certain way that we like. We pattern them, we're using hopefully a advanced technology, and then we'll be able to produce in three-dimensional, high-density and multifunctional kind of electronic circuits that in the future, nowadays still low density, in the future multifunctional high-density circuits in the future that can be used for many type of applications. This is my last slide. I would like to acknowledge all the heroes over here and the funding agency, and thank you.
Thank you for this nice talk. Do we have questions? Yes.
Thank you for this very beautiful talk. I have a question to the liquid metal. Gallium is known to produce corrosion in conventional materials, and liquid metal embrittlement is one of the keywords for it. Do you see an influence in long-term application of the liquid metal in contact to conventional electrodes that those fail?
Right. So the liquid metal is a kind of an evil metal as well, right? Because it can corrode majority of metals, and that's one of the major disadvantages of application in the electrical field. But it's also a great metal. People use it for cooling purpose and many other purposes in the electronic field. So kind of a balance. So I think in our application or our kind of idea is that the use of liquid metal is very small comparison to the chips that we use or apply to, and therefore the corrosion is extremely limited. And also the material is actually tethered by the porous substrate, and therefore is hold rather than kind of free flow liquid that corrode the material itself. So in that sense, over a long testing that we have over the last 3 years of different kind of devices, we didn't find the corrosion being the major issue of device failure. It's rather than other major issues. It doesn't mean that it's not an issue in long term, which we don't know yet, but according to the results we have, it's a minor issue, if it is an issue. Yeah.
I think we had one more question.
Thanks, Professor. Very nice talking. And you also show so many amazing practical application of your sensor. And I want to know, how did you attack or stick those sensor on human skin? And the adhesive materials also have a promotable ability, or will they affect the fiber sensors' promotable ability?
Okay, great. Thank you. Right, it's an advanced material paper published in 2003, which I didn't put it here. Right, so basically what we did was after we published the 2021 paper, that we didn't publish any paper in 2023, is to actually, oops, it's not here. Anyway, so this is, if you think about this, is the device kind of interface. At the device or the mat to the polymer to human interface, we actually do another electrospin of glue. And please check, do a little bit search of my name in 2003 advanced material. You should be able to see that. So we would do an electrospinning of that glue onto there, and it's a kind of porous glue. And when the glue is in contact with the skin, and the skin is normally wet, right? We have moisture and everything. You will absorb water and become hydrogel. And the hydrogel is so thin that it provides outstanding permeability to the entire thing. And so basically, the whole thing is still permeable and is sticky to the substrate. And for that kind of electrospun mat, we have 3 chemical ligands that we have NHS ligands, we have a dopamine ligands, and we have a carboxylic acid ligands that if you combine with a little bit of calcium ion, for example, then you can cross-link with whatever wet substrate. And therefore, when we sweat or everything, it actually stick on top of the skin. And we also allow some sort of underwater movement as well in a long, not short period of time, like 1 hour, it's still be fine. We show that in that paper.
Okay, another question about just this application. I mean, in this sensor, the liquid metal is not liquid state anymore. So what if I just use a metal nanoparticle and spring it on the surface of a fiber member? What's the difference, and what's the advantage of liquid metal in this paper?
Okay, so it is actually in the liquid format, all right? It's not in the liquid format. It's and now the gallium indium, we have the melting point is roughly about 15, 16 degrees Celsius. And this was tested in a room temperature like this, so it's 20 plus. It's in the liquid format, but gallium can be oxidized like aluminum, become gallium oxide very quickly when it's exposed to the air. And so the surface of the alloys is always covered with a few nanometer of super dense gallium oxide, which maintain the structure. And so it looks like solid, but it's actually 99.999% are still in liquid format in that sense. Very heavy liquid though, 7.8 something gram per cubic centimeter. Very, very heavy one. Yeah. Thank you.
Okay. I think with this we close this session. Thank you for being here. Thanks for the talk. So now we have a break, but this break has a few special points to it. So we would like to take a picture at first. And if it's not raining, perfect, so we're going to take it outside. So if you just go to the main area and then to the left down the stairs, we want to take it on the stairs because there's a really beautiful banner in the background and I think we'll be making a nice picture. And then after that, we do have some sparkling wine in the back to celebrate properly. And then if you could be please back at 4:55 because we want to promptly start at 5 o'clock again. Okay.
Okay, welcome back, everyone. This is our final session for the day. It is my pleasure to introduce a fellow alumnus of the University of Massachusetts Amherst. My next speaker is Dave Flanagan. He received his PhD from Polymer Science and Engineering at UMass Amherst and Caltech before joining Wiley VCH. He was also editor-in-chief for Advanced Functional Materials. After that, he moved on to be one of Wiley's managers for Chem Informatics program, including a award-winning AI tool for predicting synthetic roots. In his current role, he leads Wiley AI product development and is based here in Germany. So thank you, Dave.
No, thanks a lot. Can you hear me okay? I think so. All right. And can we put the first slide up, please? Awesome. Thank you. Yeah, so it's great to be here. Like you said, I started my career with advanced materials here in Germany, so it's really nice to be able to come back here and see so many familiar faces, and glad that you were able to make it, the people online were able to make it. Today I'm going to talk about something that you may have been asked about once or twice in the last few months, and that's AI and generative AI, and how does it affect publishing, and what's coming, what's new. So what we'll do is we'll start with the little informal poll. I'm afraid it'll only be here in the room. Sorry about that, but we'll tell you how it goes for the folks online. We'll try to define what's a really squishy word, AI. What does that even mean? We'll talk a bit about AI ethics. We'll talk a bit about AI and research integrity. Talk about some ways that AI is being used in research workflows today, but then also what's coming soon. And then we'll get into some, hopefully we'll have some time for some Q&A, because I think that's always one of the most interesting parts of the discussion. So, poll. What I'd like to know is, just by show of hands of people in the room, how many people have used ChatGPT, Google Gemini, things like that? So for the folks online, it looks like about maybe 2/3 of the people in the audience raised their hands. So for those folks, how many of you have used it for more than 10 hours in total, you reckon? Not 10 hours in a row, but like 10 hours in total. Okay. So maybe about, maybe about 20% of the room, I'm guessing. I think that's, I like to ask that question to start, because I think it's, when you're working with especially generative AI, it's like working with a really smart, really unreliable intern. And so you don't really know what they do and don't know. And if there's a jagged edge between what they do and don't know, it's also invisible. So you have to ask it questions and come back and evaluate the work. And I think it really takes something like 10 hours of using these tools to get a feel for what they can do well and what they can't do well and what maybe they could do well in the future. So thanks for indulging my data science urges there, and we'll move on to actual presentation. So what is AI? AI is a kind of a squishy, I'm going to say, marketing advertising term. I don't know if we have any data scientists or statisticians or programmers in the room, but you might be cringing when I say AI. When I'm talking about AI in this context, I'm talking about machine learning. AI, again, in quotes, machine learning. It's about using existing data to create systems that can make predictions about the future. So you can take, a bunch of data about, I don't know, stocks from the last 10 years, and you can put it into a table and do some ML on it, and you can, make some predictions about how a stock price might go up or down or sideways in the future. You can forecast outcomes. You can use it to help make decisions or to help automate tasks. So it's learning from the past. And you can differentiate a little bit from something like data analytics, where you're analyzing patterns in the past, looking for trends. This is more about trying to predict the future. Talking about AI is like talking about vehicles. Like a vehicle can be a boat or a plane or a car. It's lots and lots of different things. And if you just call things vehicles, then people will get confused what you're talking about. Generative AI, I think you can be more specific about. So at least in my definition, generative AI is something that touches a large language model like GPT-4. We'll talk about, I'm not going to really talk about like image generation today. I'm going to stick to text. So something that uses GPT or Google Gemini or Llama or things like that. And the way these things work at a really high level is actually pretty simple. It's about predicting the next word in a series. Like, you know, on your phone, and you're typing a message, and it's got like the 3 words, and you can pick the next word in your text message, and sometimes it gets it right, and sometimes it's hilarious. That was one of the early applications of this, and it works fine. But what happens when you take, all the text on the internet that you can get, and you put it into one of these models? And you can do things like look at what's important earlier in a sentence, not just the next word. When you combine those, something really strange and weird and magical happens, and that these things start to behave or mimic human output. So you can put in a query or a text or a sentence or a question or ask it to do something, and it starts to sound human-like. You're talking to math, but it starts to sound like it's really a conversation partner that you can do things with. So it's using that knowledge that it's learned in effect from all of the text that it can find to put into it to be able to do that next word prediction, but with these really strange and weird emergent properties. And so at Wiley in particular, we're really embracing AI as something that we want to use in our processes. We want to use internally. We want to have authors and reviewers and editors and readers be able to use AI because we think that it's a transformative tool. We need to be careful about things like, there's risk involved as well. We need to be careful of things like hallucinations and safety and ethics. But Wiley, our journal publishing program, we're not just crossing our arms and saying, no, we'll wait till all this is figured out. We want to engage with it, and we want to be able to provide those kinds of Gen AI and AI-powered tools to our customers, our users, our readers, our authors when we can. So if you take away anything from my talk today, it's this message here. It's that AI assists people. It doesn't replace people. So does everybody know the Steve Jobs' story about bicycles? So if you, Steve Jobs tells a story about like when he was like a kid, a teenager, and he was reading Popular Science back in the 50s. And the article had a table of how much energy it would take for different animals to go a certain distance. So it would take, a turtle this many joules to go a meter, and it would take a dog this many, and a person this many, and an eagle this many. And if you look at it, the stuff you'd expect to be up at the top, like birds and cheetahs and things like that. And humans, top of the food chain is just, right there in the middle, average in the chart, no big deal. But the person who had written the article had the foresight to say, what happens if I give a person a bicycle? And when you do that, then they're way off the top of the chart on how far they can get with a given unit of energy. And Steve Jobs is using that as an analogy for how computers can be like bicycles for the mind, so that way you can do more with the abilities and talents and energy that you have to get more done. And I think a lot of it applies to AI and generative AI as well. How can we use these tools to do more with who we are, what we know, what we have? So we're not talking about replacing people with AI and generative AI. We're talking about how can we enable people to do more with it. What are all the things that you think about that you'd like to have an intern with perfect superhuman recall being able to help you with? And IBM knew this back in the 1970s. This is a slide from an IBM presentation. And it says, a computer can't be held accountable. Therefore, a computer can't make a management decision. So in the same way that a computer can't make a management decision, the computer can't make the decision to accept or reject a paper. Computer can't make a decision to come up with a new line of research. The computer can provide suggestions, but at the end of the day, we believe that a human needs to be in the loop supervising those kinds of decisions, because only people can take responsibility for decisions. Not AI, not generative AI. So this is kind of a busy slide, but I just want to highlight the things that we think about when we're creating, designing AI-powered products. Like I just described, we want to be human-centric. We want to keep people in the loop. We want to make sure that humans are taking responsibility for the decisions and the output that are coming out of AI and generative AI. Transparency and trust is super important. If I have a AI that just gives me a number when I say when I ask it, is this should I accept this paper? 59% yes. That's not super useful. You want it to be able to have some kind of transparency and explainability in what the computer is telling you. Why should that paper be accepted? What are the things in it that are good and not good? Or how is it arrived at the decision that that is coming to? So that kind of transparency is super important for these kinds of systems. And so we try to be aligned with our communities, so with things like the Committee on Publication Ethics, the STM Association's Integrity Hub, to make sure that the systems that we're designing and shipping are aligned with the ethical and transparency and trustworthiness requirements that we have for these systems. And then finally, we want it to be adaptable and easy to use. We want, this is really cool stuff, and you want to have it in a place where you can use it. We're looking to see how can we incorporate generative AI into our submission and peer review platforms. We already have AI in our products like Rex that are helping you to do things like find reviewers, or to identify problematic papers, or to take information out of papers so you don't have to be the one filling in the forms in the submission form. So we want to be able to design and ship these systems so that way you're using them and you don't have to go off to some other website or some other place to take advantage of these. We want them to be designed into your workflows. So, big question I get a lot is, how can I as an author, or how should I as an editor be thinking about using these safely? So let's just take a couple of beats on Wiley's Gen AI ethics guidelines. And I'll provide a link, and you can also find these on our website. So if you have questions, or if you're working with people who have questions, you can refer back to that. The first is about transparency, so disclosure that we're using these tools. So we don't say that, no, you can't use Gen AI in a paper. We don't. That's short-sighted. That goes against everything I just said. But we do say that if you're using Gen AI, then you should disclose how you're using it. And that disclosure should be in the methods or the acknowledgements, or separately. And remember, computers can't take responsibility for decisions. So authors are responsible for what's created by generative AI. So you can have the computer help you to, rewrite your introduction so that way it's easier to read and better. It'll help you to, bounce ideas back and forth. But at the end of the day, you, the person, are responsible for what's being created by it. Really important is we don't think that Gen AI should be used to create or manipulate original data and results. So when I say manipulate, I don't mean working with a table of data to, do stats on it or something like that. I mean, you can't use Gen AI to create research data. I think that's obvious. And I think somebody in the room has considered it. And common sense. We're not talking about using it for things like spelling and grammar. We're talking about don't use it to generate a table of results, things like that. And then, of course, at the end of the day, the final decision on whether or not the use of a tool is down to the journal editor or the responsible party. This field is moving so fast, and people are coming up with new ways of using these tools all the time. So we're trying to provide these sorts of guidelines instead of trying to anticipate every possibility. Like I said, authors, computer can't be an author. The computer can't be initiating original research without being directed by a person. Computers can't be authors, therefore copyright can't be assigned to a computer. So, because you can't, computer can't hold copyright. Peer review is an interesting one. So, when we think about how you can use generative AI in peer review, we need to keep in mind the confidentiality between an editor and an author and a reviewer. So yes, you can use Gen AI tools to improve the feedback of a referee report, to improve the quality of a report. If you do, let the editor know. But it's potentially dangerous to upload a submitted manuscript into generative AI. And the reason why is, unless you've thoroughly read and understand the terms and conditions of where you're sending it, and you know where you're sending it, and you know what they're going to do with it, you're introducing some risk into the process. Because you don't know if the manuscript that you're looking at confidentially that you got from the editor is going to be used in the next training run of whatever free large language model that you found on the internet is going to be. So, think about, am I running this locally just on my laptop, or am I using something for free, or am I using something that my university or my institution has told me that it's okay to use? So, careful of confidentiality. And at the end of the day, the referee report, you're responsible for that. So just like if you got help on writing the referee report from some students in your lab or something like that, you're the one at the end of the day who's responsible for the quality of it. It's not the computer. There's a couple links on the bottom of the slide. I think we're sharing the slides after the talk. One is from STM Association, one's from COPE, and the third one is from Wiley's website. And those are links to current best thinking for Gen AI ethics. And keep in mind, this field is moving pretty fast, so we're trying to be a little cautious today, so that way we don't have to backtrack 6 months from now. Maybe we won't be talking about being careful about uploading stuff into ChatGPT 2 years from now. I don't know. But for right now, we're trying to be cautious about it and be thoughtful about it. So what about research integrity in general? So I don't know how many of you know the noted AI ethicist and occasional actor, Patton Oswalt. Okay. I got no reaction to that previously. But he tells a story about how generative AI, or any invention really, can have practical use, it can have accidental harm, and it can have premeditated harm. So he used the example of an axe. So with an axe, you can chop up some wood and build a fire. You can accidentally drop an axe on your foot and hurt yourself. Or you can chase somebody with it. And AI is analogous to that. I can use AI productively to improve the quality of something that I've written, or to research something. I can also accidentally hurt myself if I use it and hallucinate a bunch of references that don't actually exist and claim some hypothesis that I have. Or I can use it for generating paper mill papers at scale. So there are, when we talk about AI, and generative AI, and especially things like generative AI detection, we want to think about what's the intent of how the person is using it. Are they using it for something good, or for something that would be not so good? So we're using AI in our paper mill detection tools, for example. So we're trying to identify problematic papers ahead of time, so that way we can screen them out and find them, not publish them. So we do things like look for similarity between our papers and known paper mill papers. We look for things like, does it look like that this text has been generated by generative AI? And I'll say a word about that in a second. Or does the content of a paper match the journal that it's in, or the special issue of the journal that it's in? All these things by themselves may not be definitive, but together, when you combine these signals, it provides more of a look at whether or not a paper is potentially problematic. Just to spend a second on Gen AI content detection, a lot of people, talk about this. It's a difficult problem, and we think we've solved it for a limited set of cases. For things like abstracts in a certain set of subject fields. But if you talk to any high school teacher, you'll know that being able to detect Gen AI generated essays at scale is a pressing problem. So a lot of people are trying to sell solutions like this. I would just say ask questions of who's trying to sell that to you, because I think that being able to generate it being detected at scale is a difficult problem, and being able to just look at that on its own isn't super useful, because you don't know what the intent of the person using it is. So another example of where we're using it right now is in referee finding. So I don't know if anybody in this room or online is a journal editor. If you've ever had any problems trying to find someone to referee a paper, so we're trying to make that process a little bit easier. We're trying to use AI to help you identify not just related referees, not people who work on the same topic, but also who might be available and who may have reviewed for your journal before, or may have some other connection to your journal, and be able to try to use AI to predict who's the best potential referee for this paper right now. And our goal in that is to not only reduce the workload on editors, not only to reduce the amount of time it takes to get a paper published, but also to reduce the workload on referees. Because I don't know about you, but if your inbox is full of people asking you to referee papers, and most of them aren't that related to what you're doing, wouldn't it be great if you were just getting a few more targeted referee requests instead of a ton of untargeted ones? So that's how we're trying to use AI to improve the reviewing process. So what's next? I guess just generally, we try to think about what are all the different decision points that go into publishing a paper, from conceiving a paper to submission, review, online publication. And anytime you have a decision point, that's a potential place where you can have the computer assist you in making the decision. So things like being able to navigate potential conflicts of interest, being able to consolidate the feedback that maybe 3 reviewers gave you on a paper into something that's more manageable and easier for the editor and the author to deal with. So we're going through and looking at working with our authors, with our editors, with reviewers, to figure out where can we use AI to help and give more bicycles, so that way we can make the process easier, more efficient for everybody. I'll just give a quick example of something that we're looking at. So this was developed by Lisa Wiley and my team. So imagine that you're an editor and you say that a paper should be revised. You get the revision back, and usually what will happen is you'll have the original paper, the revised paper, the original referee reports. The author will have a response to those referee reports. So you'll have a stack of paper that's 20, 30, 40 pages long. Computers and Gen AI is great for summarizing. So one thing that it's pretty good at doing is summarizing those referee reports, summarizing the author response, summarizing the original papers, and putting it together in some kind of report so that way the editor, for example, can look at it and say, actually, the author, responded to everything that I asked them to. They didn't respond to they either didn't respond to or didn't worry about, these couple of things, but that's okay, because I'm okay with that. They said that they responded to this criticism, but they didn't make any changes, so they forgot to make the change to the revised paper. You can take a lot of work like that and compress it down, and you still have the person in the loop, you still have the person checking it, but we're trying to make their lives a little bit easier. So, to conclude, we think that Gen AI models should become more and more powerful and reliable. I tell people if you try something today and it doesn't work, come back in 6 months and it might work with GPT-5. You don't know. We're trying to stay in sync with our communities so that way we're not too far out in front saying all kinds of space-age science fiction stuff, but still trying to embrace these tools and move the conversation forward. Ethics and safety, it should be designed into our products the same way that security is designed into our products. So it's a consideration from the beginning. And we're trying to address the needs of our editors, authors, reviewers, and readers, because you're the reason why we're building these tools. So I'll stop there. I don't know if we have time for questions, but thank you very much.
We do have a little bit of time for a question or two. Does anyone have any questions? Then I'll ask a question because you mentioned this a couple of times. Yeah. So you mentioned the word hallucinate quite a bit, and there might be people who aren't familiar with that word. Can you talk a little bit about what hallucinations are and why generative AI might hallucinate?
Sure, yeah, thanks. Yep, so hallucinations, it's probably not the best term, but it's the one that's stuck in the community. ChatGPT isn't a search engine. ChatGPT is trying to predict the next words in a sentence. So when you ask it something, it's not going to necessarily go out to the internet and do a search and find a fact and come back with it. It's going to come back with the average response for that particular string of words that it saw beforehand. So, especially in things like scientific publishing, we don't want to rely on Gen AI as a search engine for doing things like finding references, because the references that it, quote, finds might be something that it came up with out of thin air, that kind of hallucination. I didn't do a good job explaining the technical part of that, but maybe that's the outcome.
That's great, thank you. Are there any other questions? Then let's thank Dave for all the great work.
Thank you.
Stefan is here, excellent. It's my pleasure to invite our final speaker of the day, Stefan Hecht, who made it, thank you. Stefan is the Einstein Professor for Organic Chemistry and Functional Materials, perhaps they're advanced, at Berlin's Humboldt University, and a founding director of the Center for the Science of Materials in Berlin. His research interests are at the interface of chemistry, physics, and material science, with a particular focus on developing photo-switchable molecules for remote control materials, devices, and manufacturing. He is also the co-founder of Zolo GmbH to commercialize zoolography as a novel and potentially disruptive 3D printing method. I hope I said that right. Hey.
Hey, perfect.
All yours.
Thank you. Thanks for having me, and thanks for waiting for me. The cab driver was awesome. And it's the first time in this building. It's very nice with all the flags. It reminds us that science is international and a lot of fun. There's a back and a next button, so I assume I push the next button? Yeah, perfect. So don't worry, we can make it in the next half an hour. So I will tell you a little bit about our avenues in photoswitches, so molecules that respond to light. And I think it's one of these cases where we see, and you see this in many people's work here, is where we really can take the knowledge that we get, fundamental knowledge of molecules. We try to understand a little tiny detail, and then people might think, so why? And we can take it and we can really use it for something useful. Very brief intro, I zoom in very quickly. Obviously, light is the only source of energy on this planet. I mean, we always got to keep this in mind. There is a closed system, and the only source of energy that's coming in is light from the sun. And then we need all that energy, for example, to recycle materials, right? This is very important. And then there's different strategies. Nature has found its solutions to use light not only as an energy source, but also as a source of information. And of course, we're using light also. It's in your pockets. It's working as we speak. It's broadcasting, this one also. Without telecommunication, this would not work. And of course, then we zoomed in because light needs to interact with some sort of matter that could be, of course, also inorganic. But I'm a very naive organic chemist, so we like to play with molecules. So although this is a very unusual remote control, the molecule for me is a molecular nano-sized remote control. Yeah, so this is how I view this. This is all you have to take, and then we can take all the advantages of light, and then we can take all the know-how of the chemists. We tune the molecules in order to do something nice. And photoswitches are molecules that respond to light reversibly, so they recycle. They're green in a sense. It's actually the first time I pitched that the photo switch is green. So anyhow, it just came to me. And then there are switches that, like the retinal that you just saw, that actually is responsible for you still seeing this image. This is trans isomerization. Classic Drosophila of the organic chemist is the azobenzene. You can then play around. You can use, I don't wear blue jeans, but you can turn indigo, a blue dye molecule, into a useful photoswitch. And then there's also these other photoswitches, diaryl ethenes, that undergo very large electronic changes. So we use them a lot together with my dear friend Paolo in the back. It really depends on what you want to change, what properties you want to change, which process you want to optically control with a remote control, which switch to use. So I think they're very complementary. That's why it says it in the slide. What you got to keep in mind is the switch has to be different in both switching forms. If the switch is not different, then it's completely useless. I mean, you can, maybe publish a paper, but nobody will care because your switch does not have large property changes. So it's very important to keep in mind that we have large changes in properties, in polarity, in acidity, in the ability to transport charge, in the catalytic activity. We see this later. So I briefly show something here. We put these things into rubbers. This is basically PDMS. This is the stuff that you guys know. It's a seed. It's a very low TG polymer. And if you put this, you make a film, published in this house, handed by someone of you maybe. Then you can cut the film. This is the hands of Micha Katan, who is now a junior group guy, does really exciting stuff with molecular motors. And then you irradiate this with light at the cuts. And then you put the stuff together. Here you see here were the cuts. And then the self-healing is accelerated. 30 minutes is still not super fast, but much faster than many other people. And then you pull on it, and then basically it's much more stable. It ruptures on the side now where it was not irradiated. And so basically what is happening is that we have a light accelerated healing cycle. And then you have these issues with materials to get light into a material. It's a big drawback of light, that light can usually not penetrate very far. Anyhow, so we played around with this. Then we also played with Albert scanning. So here you see a very successful molecule, fluorinated azobenzene, that responds to sunlight. And here you see this oscillating, not with a really high frequency, but at, I think, a day somewhere in February in Eindhoven. So you can imagine there was not a lot of sunlight. And in the back is a regular azobenzene that doesn't carry the fluorine. So this is really, really important. Anyhow, so we were then working with Albert and his team, and Dick Brewer is also very important for this, to make coatings that are self-cleaning. So they move and they move dust particles away and whatever. It's very difficult. Last but not least, I do this. Paolo maybe talked about this. I don't know. He probably has better stuff to talk about. But here we started this a long time ago to put diaryl ethenes into a matrix of a very good polymer for conduction, so P3HT, and also together with a very gifted other scientist here, with Emmanuel Augiu, who is now in Canada. And here you can see that you can really get non-volatile behavior. So you can, depending on the switching state, you can basically turn on or off this transistor. And the cool thing is, that's nice about molecule and films, that if you now bend this, the information stays, but on the x-axis now is not time, but bending cycles. So I've never seen the machine, Paolo, but 1,000 times bending sounds like an application for some automated thing, you know, some gear. Poor grad student. Anyhow. And then last but not least, we put this into organic light emitting devices. So these are transistors, but basically they can emit. So these were high resolution displays. You can read and write information. And then you can also do it in three primary colors. So green worked best, that's why you see green. But also red worked quite well. As always, blue is a little bit more difficult, right? Anyhow, and in every case, we had to tune the photo switch for this. All right, and then you can keep on going. I think there's a lot of fundamental questions still to be asked. Some very fundamental thing is, how can we efficiently switch? The quantum yield, catalytic amplification, we stumbled upon this, that you can use holes or electrons that can catalyze the isomerization of these switches. So therefore, you can get, because it's a chain reaction, a quantum yield of higher than 100%. So you can be better than 100%, always good. And then fatigue resistance, something that is very, very important, because I think the main drawback of molecular materials is fatigue, right? It's, when we look around here, it looks very darn inorganic here. And it's 20 years old, Neville told me. So there's a reason. So I think organic materials come in handy when it's about adaptiveness, responsibility, about change, dynamics, and other things. The most important thing I always find is very challenging and frustrating is you optimize a molecule in solution, but nobody cares, because a material is not a molecule in solution. A material is actually something where things assemble, things have to form an interface, and then oftentimes the lovely switches don't switch anymore. So this can be very, very frustrating. So we try to shortcut, learn about molecules already in the solid much earlier anyways. And you see some parts of molecules. So this was my longer intro. And of course, you guys know this. There's many promises are being made. And this is always, I think it's important to have a vision. I'm not sure if it was a hallucination, but a vision. And there's also this German saying about, if you have a vision, you have to go to the doctor or something. But anyways, I think the vision is important. You have to have some goals. If you have a hallucination, you definitely have to go to the doctor, by the way. Or you should drink something, whatever. And so I think this is important. But the problem in these fields is always that if you keep promising things too long, at some point people are fed up. They will not buy it anymore. And they will move on to the next topic. So I think there is a lot of potential, but if you really look carefully, what application has come out of, I would say, yeah, almost a century of research in photochromism, photochromic lenses. I mean, they look pretty fancy, I think. I put this in, A, because I really like the hairstyle. It's very diverse. Also, it looks really cool. And I keep telling people that I have to get one of these glasses, but I'm too old school. Anyways, so I think that was very frustrating because there's a lot of potential. So not by design, but by a little bit of imagination, I really like this quote. It's actually very important, the second part of the quote, I think. It gives an aspect to science which is non-rational, and I really like this. And you know what? ChatGPT, try it. Anyhow, so I'm very relaxed with machine learning. I have a problem calling it intelligence, but we discuss this later. So we stumbled upon something. We got inspiration, not hallucination, not vision. We got an inspiration from this paper by Alex Lippert, who described a volumetric display. Very beautiful. This is work where he basically uses a projection to switch on a fluorophore, then it is a fluorophore, and with a different wavelength, the fluorophore is doing what a fluorophore does. It emits, right? So you can see, I don't know, here's the molecule, some figures, whatever. There's his lab, there's a moving horse. Well, you can do this. So we were thinking, hey, it would be really cool if we could do this, but we would actually use the second photon to permanently put the information where it is, because it's a way to localize a chemical reaction. This is very important, and you can use two wavelengths. And this is how zoolography was born. Zoolography, and now we get into vision, or into science fiction a little bit. I'm a big fan of Star Wars, and zoolography is, to put it in one sentence, is the action is where the sound is. So where the two lightsabers meet, this is where there's really, the two photons are there, and this is where we can do chemistry. And here's some initial movies. This was in a 1 centimeter cuvette, relatively simple, not easy to visualize this. This is a little bit faster now playing, so this is 8 times faster. Here we print a ball in a cage within a minute. Classic cuvette. It's very difficult to visualize this because the refractive index is pretty much not changing. And so you have to use very bright light. As a Berliner, you have to print a gate. This is now almost 5 centimeters. It's a little dusty because in the beginning, you do things low-tech. Here you see it's also still relatively simple. And in the middle, you see this kind of light sheet here. That's very fundamental and important for this. Why is this important? Let's see if the sound works. This is now the important part for the people in back.
This is terrible. Computer, another cup of coffee, black.
Yeah, I'm glad the coffee outside worked better for me. Thanks. And
you can add replicators to your list.
But what the important part here is, I'm not joking. I think this is very useful, and I said this recently. When I was a kid, I read a lot of Jules Verne, and I thought it's amazing what this guy had come up with, and many of these things are now true. If you see a replicator, you also think that's completely crazy. You just materialize something there, a computer, a cup of coffee. But the idea of materializing digital construction plans is super important. And I tell you, we will get there. The question is just when, and there will be limits to what we can print. Maybe it's not the coffee. Maybe the coffee will taste terrible, okay? But certain things we will definitely produce when we need it and where we need it, okay? And the digital construction plan is no problem, also thanks to artificial intelligence and machine learning. So the designs are out there, but the chemists and the scientists, we have developed tools that can produce this. Yeah, and it's really amazing what has happened in the world of additive manufacturing over the days. I see these people that can, for example, really 3D print high temperature titanium or whatever. It's amazing what they can do. And so this was really important. If you now think of light, which gives you this added advantage of printing relatively fast, light in the context of materializing in 3D printing, one has to say that 3D printing is actually 2D printing over and over again. It's not all happening at the same time. It's not the eierlegende Wollmilchsau. The Germans understand this. So we really have a process, and the problem is in these traditional processes, you layer material, yeah? I mean, you see this, you do something with a nozzle, you print 5 times, you have 5 times the thickness, and then this is the classic piece of people who do 3D printing, they always print this punchy, and you see it looks pretty ugly. And of course, the same is also true for stereolithography and also for digital light processing. You have a layered process. And this is not good for the material. Yeah? The great advantage now of xylography is that we can really have no layers. We have a very fast printing process, which is the most important thing for anyone to invest in technology like this. Time is the most precious thing we have. I get back to this. No support structures. Here you see 3 floating lenses. This is in a high viscosity resin. And very smooth surfaces, something we did not really plan for. But because the printing process is very smooth, you can really get very smooth surfaces, which is very important for optics, if you print optics. And printing lenses is huge because artificial intelligence, telecommunication, optical communication, we have lenses everywhere, okay? So it's really important. So this is how it works. It's actually super easy, I think. Here you have a light sheet. Okay, so this is something that Martin Rigeli, the co-founder, is very good at. He makes relatively thin light sheets, so we're talking down to microns. And you see already the difficulty is to keep a homogeneous intensity throughout the cut through the material. I try to show this that it gets thinner here, so the intensity decreases because of the penetration issue, right? So this is something that, of course, limits the size of the object. We're not going to build a house like this. This would also be a waste of resin. And once you have this light sheet in this aquarium, in this built volume, then you project a slice of an object, here the Brandenburg Gate, and then during the printing process, this thing is actually coming towards the projector. So you print forward, so the light doesn't have to go through the object again, okay? So how do we do this? We simply move the vessel to the left, okay? So away from the projector. This is how it works. Now the good news for a chemist. The good news is that we obviously need a molecule that only if it sees the blue photon and the red photon does the job. This is good. So, here you see, you see this in a movie. You see the light sheet now applies in a short, so in the short vessel, it's an elongated vessel, and it's a little bit of a quest. What is being printed here? This is actually real time. This is now not 8 times faster. You can also watch it on some YouTube. You see the projector, which has certain intensities. And this is obviously a brace, yeah? So this is a very important size that you know, this is where it's obvious you need individual changes and can be printed relatively fast. The challenge here is, of course, to make the material the way that you want to put it in your mouth and it lasts for a while. And it's not so trivial. But coming back to the chemistry, so you basically, and this is the good news for the photo switch dude, you need a photo switch. You need a photo switchable photo initiator, yeah, or a dual color photo initiator. You put this in a high viscosity resin, and then you can cross-link, start the polymerization, solidify stuff. And chemistry-wise, I try to keep this not too chemical. There's a lot of stuff we learned. Over the years, we mostly base the stuff on spiropyrans. Spiropyrans are photo switches discovered or developed in the 50s in Israel, actually, at the Weizmann Institute. And the beauty of spiropyrans is you can really make them very easily. You can make grams of the stuff. It's also something that oftentimes we underestimate. If you want to do something practical, you've got to be able to make the stuff in large amounts. And you can really do this. If you now substitute the spiropyran, for example, with this acceptor here, you put an acceptor there, but the important part is the acceptor here, then the thermal half-life gets relatively short, meaning this does not live for a long time, it goes back. And if you now think of the principle of the light sheet, then when the light sheet is going through the resin, we make sure that behind the light sheet, the stuff is automatically deactivated, right? This is really, really critical. And obviously, this guy now absorbs invisibly, so then the projector, the beamer, as we Germans say, is doing it. The most important part is, why is this faster? We need 2 photons, but it's 2 one-photon processes. This is linear. This is not 2-photon photopolymerization, as developed by the guys at KIT, for example, Wegener's group, which give much better resolution, but it's so slow. Okay, here you see fast. Yeah, I said something about fast. So this is digital light processing. This is a cube 3 by 3 by 3 centimeters. This is 6 hours and 5 minutes, and this is 15 minutes. Here you see the resolution. The resolution is even a little bit better on the zoolography, just to give you a feeling for what you can do. I should bring this. It's really impressive to have this tiny piece in the hands. This is the important part for the smoothness. So here in DLP, what you do, this is 300 microns. This is a very simplistic slide, sorry. You basically glue layers on top of each other, right? If you print very smoothly, you don't really have the layers anymore. So you can really think of lenses. This is what you see here. The lenses at certain, you can print certain types of objects. You can print lens arrays, very interesting. And obviously they're transparent. Here's again a comparison. This is DLP, printed and polished. And this is S printed, I mean, this is not ideal, but this is in the beginning, right? So there's a big interest of people to go towards printing lenses, even in the consumer area. So I mean, this lens here is not large, so it's totally the size that you could print. Okay, and then the most important thing, this is without support structure, so you can really print these free flowing. There's many advantages of this thing. Here you can see this is a printed aneurysma. So the reason is that surgeons, when they do the surgery, which hopefully they don't have to do with any one of us, but they often use a model. And they then test of, can I access it this way or that way? This is a very interesting market for rapid prototyping, by the way. But also in terms of printing hydrogels. So this is perhaps the biggest challenge, but also at the same time the biggest opportunity is to print hydrogels, so for tissue engineering. But coming back to the advantage, we can really print very complex objects. So we can move from a soccer ball and we can print it, and in the soccer ball is another soccer ball. Yeah, so this is 80 seconds printing time. Here's the soccer ball inside, and obviously this has to be also printed fast so that it doesn't sink in the other ball. Much more interesting is now the fact if you can print assembled objects, time again is in your favor, because you can manufacture a complex part much faster. Think about a watch. Usually the Swiss watchmaker makes all these individual pieces and then assembles it. We don't have the precision of the Swiss watchmaker yet, but in principle, we could print gears. So here's a very simple demonstration. There's an in and an outlet in a cuvette, 2 axes. We print the wheels with the distance is a little bit larger to make sure that it doesn't get stuck during the printing process. So there's room for improvement. And then you suck the liquid through and then you see. So this is a very simple demonstration, right? But the important part is print it at once. This is not printing axes, assembling them and whatever. So for an engineer, this is a lot of good news. Materials, I think this is the largest frontier, making the right materials for this. So here's a CT scan of a patient. You can see that we can nicely reproduce the inner features. Of course, not at the size scale of this patient. And then you can post-process this. You can UV harden for another 5 minutes thermally. And then photopolymers, right? You see some disadvantages, slightly yellow. This is the initiator that's left over. But there's also a cure for this, because this can be photochemically processed afterwards and then it gets clear. So there's a lot of tiny problems, but they're all very important. I think the good news is that there is a lot of room in terms of the material. So you can print very hard stuff. You can even print glass or ceramics. But then, again, you have to rely on what people have developed. Yeah, you have to sinter the stuff. You have to think of the shrinkage problem. If you put something in an oven at 1,000 degrees, obviously, you're going to lose some stuff, so you have to compensate for this. Then the whole photopolymer stuff, you can print something that is elastic, yeah, so the feature that you saw. But I think probably the biggest potential is in printing soft stuff. Because hydrogels, we can now print them in the presence of cells, so the initiator is not toxic anymore. We have to play around with this. This has a huge potential, because then you can basically have your resin vat. You don't have to push your cell through a nozzle. You can structure this, and then later on use that construct to regenerate your tissue, all the stuff that you're familiar with. Another unique feature, you can print and flow. You can make this into a continuous process. This is something we published last year in Advanced Materials with a colleague from Aachen, with Matthias Wessling. And really the genius idea that they had is to change the flow profile to make the velocity at the edges faster, so that there would be no UV hardening at the windows. And then you can simply print and you make objects, and they just flow basically out. It's a very, I think, important thing if you want to really go into a production mode. The second important part, I would show you a movie, but I'm already, it's my last slide, is printing in microgravity. So I started with Star Trek and with Star Wars, and this is very important because actually every manufacturing technique is tested at the space station. Yeah, so all of the printing techniques. Think about an inkjet printer in outer space at zero gravity. Maybe you know these movies of how a candle glows or burns in outer space. It's pretty interesting. If you haven't seen it, check it out. It looks different, obviously. But the same is also true, I guess, for a drop. Your inkjet printer is going to suffer. Okay. The good news is the lithography gets better in outer space because we can print in any liquid, because there's no gravity that pulls our object down, right? On this planet Earth, which is, I like planet Earth, but there we have to print fast, because otherwise the object sinks. Okay, so we have to print in very highly viscous resin. So this is very important. And then there's a lot of development now to print on top of objects. So to combine microscopy and printing into a process where you can really integrate several materials. We all know one material is not going to solve the planet. We need many materials and integrate them. So this is the thing. I don't like this photo. This is so much better. This was the 1.5 meter thing. So this was an important photo because we had the first cube built. Here is Martin. Martin is the co-founder. He is a really great physicist. So he knows all about light sheets and photons and stuff. Then we have chemists on the team. Yves was a former PhD student. He makes the photo initiators. Niklas is the materials guy. He's really involved in bioprinting. And then we have a bunch of people who really assemble the machine. We have a software engineer, and the guy who's not in the picture because he's on a call, he makes sure we get seed money. And so this was a very critical time because in COVID it was very difficult to raise money. Yeah, but we got funded, so things are fine. The company is growing, so it's actually bigger, much bigger now. I'm very happy with my team. You saw some of the work before. It's wonderful. I really think the word wonderful is. I'm very indebted to them. It's a lot of fun with the young people. I'm only the facilitator, and then I go to events like this. Then there's people who give money, but I also have prepared a slide, don't worry. There's people who give money. Thank you very much. Then we also have a materials science. I really think it's important that we overcome boundaries. Organic chemistry, whatever. Yeah, it's science. And there's a question, and we have to work together. It's so much fun. With this Solo team, you saw it's a small group of people, but you have one particular problem, and you focus on it, and you can really move very fast. So I think it's important that we get to teach the next generation that we should not think in these barriers. And as always, there's a good Mark Twain quote for this. But my last slide is this slide, which is to you guys. I had to looking for. I really like this quote by Gibran, and it had the word "advance" in there. So I thought this fits well. Thank you very much. I think Wiley for setting a stage, and I think also facilitating the career of many young people. I still remember. I met him a while ago, Peter Gülitz. Yeah, I'm sure you know Peter. But I still remember this. I was a young guy. My first paper, I sent him the manuscript, and you know, there's a lot on the line. This is important. So you really have an input. It's amazing how this thing has been growing. We're going to discuss the future of publishing, I'm pretty sure, over a beer or two. But I find it so important because knowledge is the future. We really have to continue to develop a culture where knowledge is a value and where we have clear standards for what a fact is and what some whatever other stuff is. And this is increasingly difficult. So it's important that people who know what to do take care of it. So thank you very much and good luck for the future. It's not going to be easy.
Thank you, Stefan. I think we have time for one question. Is there one question?
Oh, yeah.
Thanks for the talk. How small can you go?
Yeah. Longer answer. So obviously the size, so you're talking about resolution, depends on the size of the object, right? So if you print a larger object, the resolution is going to suffer, and it depends on how fast you want to print. So resolution at the moment, I think we went to 10 microns. Going below 10 microns, then you go to smaller objects and you take more time. You can do it, but this is not what people are interested in. The idea is to go for applications where the resolution is sufficient, but the speed makes the difference. Yeah, so it's not there to compete with 2-photon, I think. There are some ideas, also of co-founder Martin, we have something to send to someone from you soon, to go below the diffraction limit, but I think this is academic play. Yeah, it's so small. It's small enough.
Any other questions? I'm going to go here.
Thank you for this very nice talk. Even though I disagree with your point that you do 3D printing and not 2D printing over and over again, because it's also layer by layer. But my question is, well, what about color? Can you print different colors in principle, or at some point?
I answer your question, but I still come back to your comment. The layer thing matters, because your material, if you layer, is not isotropic, and then your lens is not going to be a lens. Okay, you need a continuous homogeneous material. So the smoothness by which you layer your material matters a lot. Okay, the first comment. But now coming back to colors. Colors is difficult. You can generate colors. You can also decolorize, but of course then you print something that absorbs. So it's a lot more tricky in the order of the process. Yeah, I'm thinking what would be a nice thing also for chemists to come up with is schemes by which you introduce the color later. So you basically print a precursor that thermally you treat, and then there's a lot of thermochromic materials out there. There's a lot of stuff already known. I think it would be nice to integrate this, yeah? But at the moment we try to avoid the color, because also many consumer applications, they actually want colorless stuff.
Thank you, Stefan. Let's thank Stefan one more time.
Perfect.
Okay, we're nearly at the end of our program. I just want to say on behalf of Ulrika and myself that we had a great time moderating the session and listening to all the talks. It was excellent. I would like to thank our editors-in-chief, Kirsten, Yolka, and Sandra. Oh, right there, okay. And also Jose. In addition, can we also have all of our speakers please return to the front? And with that, I will hand over to Jose.
Alrighty, I'm
well, as people start moving forward, I am going to be very quick because I know that I'm now standing between you and your dinner and getting home, and it has been a long day. But first, I want to thank, on behalf of Wiley and on behalf of the amazing advanced team that's been behind this event, firstly, I want to thank all the participants, everyone who's made it out in person, everyone who's joined us online. It's been a tremendous event. Thank you for your support. I would, and of course, I always have to thank the same people because you are authors, our referees, our board members, our readers. You are our community. Thank you for your continued support. A real quick word of thanks to our amazing organizing people. I'm not going to mention any names because there are so many. I'd be here for the next hour, and you've done a wonderful job. So thank you for putting this together and for looking after all our speakers. And last but not least, our speakers themselves. So thank you very much for flying all the way from other side of the world, near and far, battling traffic, trains, making it literally at the last minute. Thanks, Stefan. Thank you for the amazing presentations you've put through today. And thank you again for all your support for our journals, because this here would not happen without your contribution. So thank you very much. Have a good evening, have a good trip home, and enjoy the rest of your stay in Weinheim. Thank you. And as literally a last minute thing, a small token of appreciation for our speakers. Thank you very much.